Let's start with Bitly. It's the easiest one to begin with of all the systems that we'll be discussing in this video. So at a high level, what is Bitly? Bitly is a URL shortening service that converts long URLs into shorter, manageable links. It also provides analytics for the shortened URLs. So ideally, as we keep discussing, I should list down the requirements, break down into functional and non-functional. But given the breadth of the content that I want to cover in this video, I have listed down way before. That's fine. The main intent of this is to just to understand if someone throws a questions of this requirements and puts us in a situation to reason up to build a system which supports this requirements. Yep, so it's very clear here now. The requirements, the functional is user should be able to create short URLs from original URLs with an optional options like they can provide the custom aliases and the expiration date for the short URL. And the other functional requirement is user can access original URL by browsing through the short URL. And non-functional is, alright, the shortened URLs, whatever we will be providing, they should be unique. There should not be any collision between multiple original URLs, and the redirection of the shortened URL to original URL should be less than 100 milliseconds, and we should give high priority for availability. That is, redirection service should always be up and running, giving higher priority for availability than consistency of the data. And the last requirement that we should satisfy is we should support 1 billion URLs and 100 million daily active users. So these are the requirements that will be thrown at us and has to build a system which supports this and reason up for the choices that we will be making and to drive the conversation through various phases of the system. So once we have the requirements clear, we should identify the core entities that are involved in this system. So looking at the requirements now, we can straight away say that the core entities that we'll be dealing with is original URL, short URL, and the user entity. So that's the second phase. We should clearly list down the core entities. So the second step is going to be listing down core entities. It's not needed to list down right away all specific columns, its types, and the sizes of each column. So if you can see here, original URL, that is the actual original long URL that the user wants to shorten. And the second one is the shortened URL that the user receives and can share or browse. The third entity is user, which really represents the user who created the shortened URL. So once core entities is clear, that is going to lay the foundation for the next phase, which is the API phase that we'll be discussing. So this sets up a contract between the client and server. Actually, this is the first point of reference for high-level design. It is very clear. Each endpoint is going to serve one of the functional requirements that we have. So to shorten a URL, we will need a post endpoint. So, and I'm just naming it as something like short_URL. So this endpoint takes in a long URL along with the optional options like custom alias and expiration date. Taking this as a payload, it will return the short URL. So this is the endpoint which helps us to achieve the first functional requirement. The second one is the get endpoint, the redirection one. So we'll need a get endpoint which takes in a short code and redirects the user to original long URL. So simple one takes in short code, let's say example ABC123 or whatever, and it redirects to the original URL with HTTP 302 status code. We'll talk more about status code when we are going into the high level design. So next phase is high level design. So this is the phase, the fourth phase, where we'll try to go through one by one of our functional requirements and try to design a single system to satisfy them. Once we have this system in place, then we will try to layer on depth via our deep dives. So let's talk about the first user flow. So first user flow is basically users should be able to submit a long URL and receive a shortened version. So here the core components that I have listed down here is the client. The client is basically, that's where users interact with our system through either a web or mobile application. And the other component here is the server. This is our primary server, which receives a request from the client and handles all business logic like shortening, URL creation and validation and other stuff. And then the third component I have listed down is the database, which stores the mapping of shortcodes to long URLs as well as user generated aliases and expiration dates. So to reiterate on the flow, ideally when a user submits a long URL, the client sends a post request to short_URL with a long URL, custom alias and expiration date. The primary server receives the request, validates the long URL just to ensure the URL is valid, and also make sure that this URL is not existing in our system, which we can confirm by querying the database. So once we make sure that URL is valid and it is not existing already in our system, we can just proceed to generate a short URL code for that. For now, let's not talk about how we are going to shorten the code. Let's just keep it in a black box, kind of like abstraction layer. We'll talk more about that in our deep dive sessions. So, and consider also if user has specified a custom alias, we can use that as a shortcode and then process that and try to insert into our database, storing the shortcode, and finally we can return that shortened URL to the client. So that's how ideally the flow for our first functional requirement is going to look like in our high level design, talking to each component. So you can see we generate a short URL, saving to DB, and we do validations, and then now listed down the fields that we'll have in our database: short URL code, original URL, created time, expiration time, created by, and other user related entries. So at a high level, this is more than enough to just to highlight what fields we'll be storing in a database. Let's talk about the second phase now. Second functional requirement: users should be able to access the original URL by passing the shortened URL. So now our short URL, which we return in our first flow, it is live and user can access that original URL by using the shortened URL. So this shortened URL exists at a domain which we own. Okay, for example, we can say it is like os.ly or anything, something like that. So short URL would look like os.ly/abc123 or whatever it is, and all requests to that short URL will go through our primary server, which we have here in the center of the screen. So the flow is going to look like this. The user is going to access shortened URL. The following process occurs. The user browser, which is a client, sends a GET request using our shortcode endpoint to our server. Let's say, like I said, /abc123. Our primary server is going to receive a request and it tries to looks up the shortcode in our DB. If shortcode is found and isn't expired, then we try to return with the 302 redirect status code. So here to talk about what is this 302 redirect code, and why not 301 redirect code that should be returned. So to at a high level, 302 redirect is basically temporary redirect. This always ensures whenever user is trying to browse through that short URL, it goes through our server, and if this happens, we'll have more control on making that URL expired, or maybe keep track of some analytics like number of clicks, geographic statistics and all, though it's not in part of our requirements. But to have a more control on such operations that we can perform, it is recommended to return with 302 redirect. And also this helps browser to not cache a response, so that is very important. 301 permanent redirect, this lets the browser cache a response for the first time, and further visits will bypass our server, which definitely is not going to meet the requirements that I just specified, and it's not going to be in our control if you wanted to invalidate, or if that short URL is changed, because it will be cached and it will be stale data that the user will be still trying to redirect to, or it can receive an error. So that's why we always try to redirect with the 302 sections. So this is the second user flow of trying to access original URL by using the shortened URL. I think now it should be clear how the flow is going to happen when user provides short code, and now we are going to deal with our system that we have designed. So let's jump to the deep dives. So deep dive is basically whatever we have each point in a non-functional section. We'll try to take one point at a time and discuss how we are going to achieve that. So the first thing, like I said here, each point in non-functional section, we'll try to discuss one thing at a time. So we should ensure the shortened URLs are unique, making sure there's no collision between whatever the original URLs that we are going to receive. So how are we going to achieve these constraints? That is unique shortcodes, and try to keep it as short as possible, and the generation should be efficient. Let's try to brainstorm the approaches. So let's discuss on how we can achieve making sure that URLs are going to be unique. So the brute force approach that we can straight away think through is whatever the long URL that we'll be receiving. So here let's maybe focus on the first n characters prefix of a long URL. So here shortcode will be just first n characters of a long URL. Let's say the long URL that we are receiving is www.google.com/test, and the I'm considering it as a 6. So www.go is going to be our shortcode. So this is not going to work, and it's going to clearly violate our unique constraint. Why? Because let's say we are receiving one more original URL, www.google.com/hi. The first 10 characters here, it's going to be www.go. So it's a collision between this URL and this URL. So our system will really not have a clue to which original URL it should redirect the user to. So it really violates the unique constraint, and this is not the option. The other option that we can think of is random number generator or hash function. So it's basically we'll try to use a standard math.random or crypto functions for increasing unpredictability to generate some random number, or use hash functions which always returns deterministic and fixed size characters. Once we get the random number from either of the random number generator or hash function, we try to encode using base 62. So base 62 is basically, it's a alphanumeric characters like A to Z of lowercase, A to Z of uppercase, and 0 to 9. Once we encode using that, we try to take first 10 characters and consider that as our shortened code. and usually n is determined based on characters needed to minimize collisions. I'll talk more about it on our deep dive. Here let's take in as example, the input URL is going to be something like this: google.com test, are you there, something like that, and random number, it's going to generate some random number, and I'm going to pass this random number to this base62 encode function, which gives us some code, and I just try to take first 8 characters. And this is the approach we can consider. But there is a challenge in this approach as well. So let's talk about the challenges. So here, as URLs increase, the chance of collisions dramatically increase as well. So this is a standard birthday problem. It's a kind of a paradox. So to at least explain to in a simple way, I can say something. Let's say let's just picture there are 365 lockers in our gym or school, or in any sports academy that you're visiting, whatever. So every person will try to put his books or bag in a random locker. Now after only 23 persons, the chance that 2 people putting books or bags in a same locker is already about 50%, even though most lockers are still empty. That surprise is called the birthday problem. So the same math applies to our the 8 character base62 code as well. So that A to Z caps and smalls from 0 to 9, they will start colliding after roughly, let's say 17 million URLs. So after that, we should check for duplicates or use longer codes. So to avoid that collision, we need high entropy. High entropy, again, it's nothing but we need more longer short codes. It is against our constraints. We should try to keep our code as short as possible. That's the ultimate solution that we're trying to provide. So as we keep increasing the short codes and the chance of collisions increase, detecting and resolving collisions involves too many database lookups, adding more latency, ultimately leading to trade-off between uniqueness, length, and efficiency. So we should try to fight with any one of this trade-off and compromise on the things. So even if we don't want to take any chances for the collision that is going to happen, this is not the approach that we should take. So the ultimate solution for us to achieve the codes that we are going to generate are unique is to proceed with the unique counter with a base62 encoding. So it's basically we try to maintain incremental counter for each new URL that we are going to receive into our system, and we encode that counter using base62 and store that in our DB. So to achieve this unique incremental counter and also maintain atomicity, the best choice is going to be Redis. So this is going to help us maintain unique counter and make sure that URLs are short codes are unique. So this again saves us for not checking for additional checks if the short code is already present in our DB. And also one more thing, the question that can come up is, should we really worry about the length of this short code as the counter keep increasing? Let's say the counter is at like 1 billion value. I don't think we need to worry, because 1 billion counter value, when we try to encode, it hardly gives us 6 characters, which is still smaller or shorter code, and it supports the requirement that we have 1 billion URLs. So let's say we wanted to support 3.5 trillion unique URLs, the short code is going to be of 7 characters. So this is most optimal and the approach to achieve our first non-functional requirements. And it satisfies, but it's not a concern. It's a more of a challenge in a distributed environment, how we are going to make sure that synchronization is present in Redis counter. We'll talk about that. So after we introduce this third approach, the system is going to look like this. The Redis counter is part of our primary server, which keeps track of the unique counter as new URL keeps coming. So this is the new addition to our system design. Yep, that is the first non-functional requirements. That now next is, how do we ensure redirects are super duper fast? By now it should be clear for you, the system that we are designing, it's read heavy, maybe in the ratio of 10:1 or 100:1. Hardly people try to create a new URLs, shorten new URLs. People will be trying to access that new URLs, trying to read that. Okay, so that is why the system that we are designing is more of a read heavy system. So ideally, if we user tries to look up for a shortcode, we try to match for every shortcode in our 1 billion records in a table. That is, we just do full table scans, which really adds a lot of latency and violates our constraints, and also it becomes bottleneck as we scale to our system. So that's not going to achieve the performance or the requirements that we have listed above. So how can we achieve that? How can we make redirects are fast and achieve the latency that we have listed down in our requirements? Let's talk about that approaches. The first thing we can straight away think of is adding an index on the column that we are frequently trying to query. The frequent column that we are trying to query is the shortcode. So we'll try to add an index on that thing, usually a B tree in our SQL database, PostgreSQL or MySQL. So let's talk about how that is going to work. Let's say I have inserted the values into a DB with the short URL code and the original URL, and ignore the other columns for now, ABC1 to 3 and the URLs. And this index is going to maintain in a sortable list. So this because we added index on this short URL code, it's going to sort, and then median becomes a parent, and then all the values less than the parent will be as part of the left child of the parent. All values greater than this parent will be part of the right child, and so on. It will be recursive. So this is how ideally, just for visual purpose, the B tree is going to look like, and each node is going to maintain a pointer to hold record the info in a DB table. So now let's say user tries to query select star from table where shortcode URL is equals to like something def and all. So it is going to find that node in this tree in a big O of login times, and once we find that, it's directly going to access that record in a table and fetch that. It's avoiding full table scan and giving us the result way faster than it used to be. Or that's one approach. In Postgres, there is an hash indexing concept. So basically it's nothing but having an n buckets and trying to place shortcode into respective bucket based on the hash value calculated. So let's say I have bucket 0 and I put this hash value of this shortcode is 0. So I put that into this bucket 0. Same applies bucket 1 and so on. And if there are multiple things, will be kind of a linked list that will be here stored, and then this will be pointed to respective row in the table. And this is how the lookup for a specific shortcode will be way faster. But the challenge here is, if we try to follow this, is here solely relying on disk based access, it possesses challenges. And let's reason up why this is going to pose a challenge for the requirements that we have listed above. So typically solid state drive SSDs can handle 100,000 input output operations per second. So for our daily active users, which is 100 million daily active users, let's assume there are 5 redirects per day. They're like 5 redirects per day, and so calculating that, 100 million daily active users multiplied by 5, it is going to be 500 million redirects per day. So per second, so 86,400 seconds, let maybe 10 power 5, so approximately 5k redirects per second. So this is like ideal traffic we assumed, but this is not always going to be the case. So peak time, let's say, always consider like 100 times or 10 times of actual traffic. So actual traffic is 5k plus. So if it's 100 times, it's going to be 500k plus redirects per second. So it's very clear, these many redirects per second, the SSDs cannot handle the traffic at which it is throwing at our service. So database really struggles to handle, and this causes us the timeouts and the latency issues, and as well downtime on operations like URL shortening. So it's a good, but not going to support for the requirements that we have listed down above. So then what can be the next approach? So the next approach that we can think of is adding an in-memory cache, Redis. So this basically what we do, whatever or frequently accessed short URL code, we try to maintain a mapping for that short code to long URL in a Redis, and this it's going to improve our latency, because let's talk about the time it takes to access a memory, time it takes to access SSDs, and time it takes to access hard disk drive. So here MET is memory access time. So it's 1,000th of a millisecond, which is way faster to access a records in a memory based store. And SSD level access time, it's 0.1 milliseconds, and hard drive access time, it is 10 milliseconds. And operations per second that memory can handle, it's millions per second. SSD, it's roughly 100,000 input output operations per second, and hard drive can handle 100 to 200 operations per second. So this clearly, the numbers that we have laid out, it's going to handle the latency that we are going to be needing, which is less than 100 milliseconds for redirections. So if we introduce this in-memory cache, and how it is going to look like in our high-level design, the component is basically here the Redis cache that at the top, we will have key to original URL mapping, key let's say df456, and the original URL will be stored it in this way. So how the flow is going to look like, we first check cache whenever the client is sending a request to our primary server. If it is present, we straight away return to the client. If not, we check DB, then return to the client, and then store it to our cache. So the next time the user tries to query, we straight away return from this Redis. So increasing the response time dramatically. So this is how the updated system design is going to look like. That is the second approach. The last approach that we can really think of when we have the leverage of trading cost and complexity for performance. So the CDNs, we can leverage CDNs and edge computing. Whatever the short URL domain that we have, it can be served through CDN with the points of presence geographically distributed around the world. So whenever users trying to access whichever the CDN is near, that will try to serve from that CDN edge location. And even by deploying the redirect logic to edge using Cloudflare workers or AWS Lambda at the edge, redirection can happen without even touching our origin server. But the downside of this is the problem. Yeah, even I forgot to flag some challenges here. It's the method that we are in favor of for the requirements that we have listed above. The thing that we need to carefully be cautious about is cache invalidation. Basically, whenever deletion or updates happen in our DB, we should make sure that they're updated in our cache. That's one thing. And cache needs warm up time. So initially, if you request, there'll be nothing in the Redis cache, so they have to go through DB, and that's one thing we need to worry about, and that's not of a bigger concern. And then cache eviction policy and size. So whenever cache becomes full, we should have some eviction policy like least recently used and all, keep making sure that eviction policy is properly implemented, and so on. So yeah, the downside of this now CDNs and edge computing is this. Same here, cache invalidation, and the biggest concern is consistency issues across multiple CDN and edge locations that we'll be having. And also setting up edge computing is really configuration and cost overhead, and also debugging and monitoring is way harder in CDNs and edge locations than in our servers. So these are like very important points to consider if we decide to go to this approach. And here we really need to trade cost and complexity for performance, but this is very leastly preferred approach, and it's hard to implement as well, given the complexity for configuration and the cost that is involved. So the approach that we'll be going with is adding in memory cache Redis, which really meets our requirements. So this is the thing. Fine. Now the other point in our non-functional is how can we scale to 1 billion URLs and 100 million daily active users. Let's talk about roughly the database size now. The fields that we have currently is short URL code. Let's assume this is 8 bytes, and original URL, which is like 100 bytes. Created time, let's say 8 bytes. Custom ls 100 bytes. Expiration date 8 bytes. So roughly summing up, it is close to some 200 plus bytes per row. And also consider we'll store some user metadata, and cumulative it's around 500 bytes. And we should support 1 billion URLs. So 1 billion rows multiplied by 500 bytes is summing up to 500 GB. So in reality, this single database easily handles this. Even if we hit this limit over this size of the data, we can shard data across multiple servers, which is very rare to happen. Now we know this system is read heavy, which we are trying to handle using cache Redis cache and trying to meet the latency that we have. And for writes, let's say we have like 100k new URLs created every day. That is roughly around 1 writes per second. So Postgres easily handles based on the input output of operations per second number that we saw. It can easily handle, though it is in hard drive disk or SSD disk, it can easily handle 1 writes per second. But the problem here that really comes is single point of failure. If we are maintaining in a single database, the question is, what if the primary database that we are maintaining goes down? So that is the question that we should proactively think through and discuss on that as well. So there are two options. One is database replication. So it's just maintain replica of primary database, and whenever this database goes down, this replica will replace the primary database, and the services will still keep running and it will be functional. The other option is database backup. It's basically we periodically take snapshots of the data in the primary database and store elsewhere, and whenever this goes down, and this will replace the primary database. So these are the two options we can think of to avoid single point of failure. But again, just caution, adding this or maintaining this adds complexity to our design. And the other question is, what if our primary server, which we are handling all our URL creations and redirections in a single server thing. So given the traffic that we are estimating it to receive, it will be really hard to handle, and it will be really hard to scale if we are trying to handle writes and reads in a single server. So the best way is split this primary server into read server and write server. So read server basically handles our get endpoint, which is the redirects, and write server handles our post endpoint, which handles the creation of the new URLs. And this way it really makes us easy to horizontally scale individual servers. Here mostly we need to scale more of a read servers than write servers because it is a read heavy system. So this way we try to delegate the respective functionality to different server, and load will be equally distributed. And now the issue when we try to split this primary server into read and write server is we should try to maintain a centralized Redis instance for write service. So let's say we are trying to horizontally scale write servers. Let's say there are 2 write servers, and to maintain a unique counter for all of the requests that will be parallelly flowing in through each of the server, we need to have some global counter. So that is the Redis, which ensures the atomicity and the number is unique for all the URLs that will be coming in streams for each of the write server worker. So whatever I discussed now, after implementing this global counter, the final design is how it's going to look like. So the client, and here I add in an API gateway. So the main functionality of this is going to be route the user's request to correct microservice. If it's a get endpoint, redirect that request to this read service, and if it's a post endpoint, route that request to write service. And this write service now should communicate to our global counter, which is the Redis thing, which maintains the counter of the unique number of URLs that we will be getting into our system, and then they will be connected to database. And this is all part of the previous design that we had. Additional thing that is added here is the API gateway to route to correct microservice, which we split our primary server into write server and read server, and then the global counter for maintaining the count for unique URLs. And the other point to really highlight here is, as we keep scaling write service, and if we have to make a network call to Redis for every new URL that is streaming into write service, it's going to have more network calls. The better way to avoid the network calls is to follow the approach called counter batching, which drastically reduces network calls. So this is more of a like, let's say there are 2 write service instances, and the Redis counter count starts at like 1000, and worker service 1 requests first batch. Let's say the counter value is at 1000, and this will increase that counter directly by 1000. So the counter will become 2000, and the value of the initial thing, the 1000, will be sent to worker service 1, and worker service 2, which is parallelly requesting the batch of 1000 from this global counter, the number will be increased from 2000 to 3000, and the initial value will be passed on to worker service 2, 2000, and they will have a local batch of 1000 counters in each of a server, so they can process 1000 URLs at a time in a one network call. And whenever the batch is exhausted locally, they can make a network call to Redis later and get the latest count that is present in Redis. This way the network calls for Redis and the efficiency of the worker services will be dramatically increased and makes our system way performant. And this is how one of the technique to reduce network calls. So finally, to sum up, this is the system that we can propose to meet the requirements that we have initially listed out. I think at least it gave a brief idea of how we can think through and flow through the phases and of designing each component at a time and reasoning up for the choices that we make of all the approaches that we discussed. So let's discuss the another system design, which is a Dropbox or a Google Drive, and we'll talk more about how we can satisfy the requirements for that system as well. So now let's talk about Dropbox or Google Drive. We all know what Dropbox or Google Drive is. A simple cloud-based file storage service that allows users to store and share files in a more securable and reliable way, and they can access files from anywhere on any device. That's what a Dropbox or Google Drive does at a high level. Now let's have a look at our requirements, functional and non-functional. The first thing is user can upload file. So the user can upload a file, and user should be able to download file, and he can share the files to whomever he wanted to share the file with. And users should be able to sync files across devices, can be a mobile, web or desktop. And the non-functional requirements that we should meet is we should give high priority to availability than consistency, making sure the files which they have uploaded, it's always there no matter what happens to our servers. And the other thing is we should support large files like 100 GB, 200 GB and so on, and they should be very secure and reliable. They should not be accessible to unauthenticated users and so on, so restricting the file access to very specified users. And of course we should guarantee the user experience is best and latency is as less as possible. Like for example, when user is trying to upload larger files, it should feel it's very fast to the end users. So these are the functional and non-functional requirements that we should satisfy while we are designing the system. So looking at this, it's a simple and straightforward. We can identify the core entities, which is a file and the metadata that we need to store about that file, and the user who is going to perform all of this. So these are like the core entities that we can identify looking at the requirements. Just a simple the file is basically the raw data that users will be uploading or downloading or sharing, and the metadata is basically that is associated with particular file, like information like file's name, size, MIME type, and the user who uploaded it and all will be stored in this file metadata, and the user basically the user of the system. So these are the three core entities. For now we are just listing it down, irrespective of the columns and the Vagera stuff that will be storing. We will discuss more on that as we go deeper into our design. Yep, now we are clear the what are the entities and all. Let's talk about the third step, which is APIs, basically the system interface that the users will interact with. First thing is uploading a file. So we might have an endpoint, something like this, post endpoint called files, and the request that the payload will have the file that the user wants to upload and the metadata related to that file. So this handles the uploading. The other endpoint that we could think of is downloading a file. The endpoint is going to be something like get and passing in the file ID to this endpoint, and we give the users the file and file metadata along with the file. Okay, so these are like at a high level the initial endpoints. These endpoints might change as we keep progressing in our system design. And the third endpoint that we could think of is share file. Like we discussed earlier, it's basically each endpoint for each of the functional requirement that we have listed down above. The share file endpoint it's going to be a post and file ID and the share, and to which users the file has to be shared is something like maybe user ID and all is going to be in the form of the list. So this is the third endpoint that we could think of. And the other endpoint we can also think of is basically we need a way for clients to query for changes to files on the remote server. This way we know which files needs to be synced on local devices, which is our the fourth functional requirement. So it can be something like get endpoint files slash file ID changes, and we return file metadata, and accordingly we can sync the files which have changed. So these are the 4 endpoints that we could think of as of now. Now let's talk about one requirement at a time. So let's deep dive into high level discussion. First point, we know users should be able to upload a file from any device. So that is the thing. So let's try to talk users uploading file flow. In here, whenever we start talking about user uploading of file flow, there are 2 things that we need to keep into consideration. One, where are we going to store the raw bytes, which is basically the file that the user is uploading, and the other is where are we storing the file metadata related to that file. So these are the 2 things that we need to consider when we discuss about uploading file flow. For storing metadata, we can use NoSQL database, something like DynamoDB. Why DynamoDB? Because our metadata is very loosely coupled and structured, so it's better to go for it. Or we can choose Postgres as well, but it's not much of a question here which one to choose. It's more about our choice. So let's go with the DynamoDB or Postgres. So I'm just trying to go with the DynamoDB for now. So it might look something like this: the file metadata like ID and the name of the file, size, MIME type, and uploaded by. So this is like simple document schema to get started with DynamoDB. So that is the choice that we will make to store the file metadata. Alright, now we have chosen where to store file metadata and all. Let's talk about where we are going to store the file. The first point, which is where are we going to store the raw file that the user is going to upload. Let's brainstorm and discuss the multiple approaches and then agree on to the final approach that satisfies our requirements and meets our needs. So file store, the thing that we can directly talk is directly uploading it to our primary server. So what do I mean here is directly uploading to file server. It is going to be simple. Basically we can take the file and try to upload that through our API gateway to our primary server, which is the backend server, and store that file in our local file system. We try to store that file in our local file system, and then once that is stored, we try to update our DynamoDB, which is a file metadata DB. So this is a like simple approach which we store in server's local file system itself. But the downside of this approach is as files grow, more local file system is needed, and we need to keep adding a more local file system support or more servers. Okay, fine, assume that we have added more primary servers. The other downside is this: if server goes down, all the files that we stored in that respective local file system will also be lost. So that significantly goes against our reliability. We need to make sure the files that the user uploads are reliable. So if the files are losing in this way, if the primary server goes down, it's not reliable. So this is not the solution that we need to go ahead with. Okay, so this is one approach that we can think of. All right, let's talk about the second approach now. Storing file in blob storage, example AWS S3 or Google Cloud Storage or Azure's blob storage. Okay, so this flow is simple. We try to store whatever the file that is being uploaded by the user in our S3 bucket, where the actual raw file will be stored. Simple and straightforward. Here, the things that we need to worry or be cautious about in this approach is we need to integrate this S3, which is the blob storage service, with the primary server. The thing that we need to handle is whenever the metadata is saved in this DB, we need to make sure that the file is also stored, and whenever the file is stored, need to make sure the file metadata is also stored. So there can be cases where file is uploaded but metadata is not saved, and metadata is saved but file is not uploaded due to some issues. So that is the first challenge that we need to make sure we take care. And the other problem, which is of a bigger concern for me, is it's technically we are uploading the same file twice, meaning the client uploads first the full file to primary server, and once primary server has the full file, we upload that to our blob storage service. So which is redundant, and it's not a good approach at all, because it's of more time to the users, and also doing redundant ops in our server consumes more resources, and it's not ideal for a long-term solution. So this is also not a solution to stick to. Let's talk about the third one. The third one is, why can't we upload file directly to blob storage instead of relying on primary server to upload it to blob storage? So let's talk how that's going to happen. So how this going to happen is, we need to leverage a concept called pre-signed URLs. So what are pre-signed URLs? Those are the simple URLs that give user a permission to upload a file to specific location or bucket in blob storage S3, and we can generate that pre-signed URL and send it to the user so they can upload a file. So let's talk about the general flow, how this is going to look like. User is going to pass a request to this primary server through our API gateway to request a pre-signed URL, which gets the URL from this blob storage S3 and saves file metadata into our database with status of uploading and all, and then returns that pre-signed URL to client. And this client now uses this pre-signed URL to directly upload it to S3 via put request, which is how it is designed to upload the file to S3. Once the file is successfully uploaded to S3, we will send a notification by leveraging a concept called S3 event notification to our database to update the status from uploading to uploaded. So that's how we completely delegate the responsibility of uploading a file from primary server to directly client itself. So there we completely avoid a bottleneck and also the number of steps that the file needs to go through, which drastically improves the performance of our system and provides a best client experience as well. So this is the thing. So the flow initially in the API to upload files will now have 3-step process. One thing is we try to request for pre-signed URL from primary server, and along with the metadata that gets saved in our DynamoDB, and then we leverage pre-signed URL to upload file via put request to blob storage from client itself directly. And once uploaded, S3 event notifications will update our status in our metadata DB. So this is a simple and the approach that we can completely rely on, and this is the approach that we should choose to meet the requirements. So that is how we are going to satisfy our first requirement, like user uploading the file and make sure we give better experience to the user. Now let's talk about the second requirement, which is users should be able to download the file. So the downloading file flow. So let's also discuss the multiple approaches that we can think to achieve this requirement. The first thing is trying to download directly through our file server. This is a simple thing. Is directly we download from blob storage to our primary server, and then once a primary server has gotten hold of the file, we download from that primary server. That's like a 2-step process, from blob storage to primary server and from primary server to the client. Again, here redundant downloads. It's first we are downloading to primary server and then to a client, which is not a way to go and discuss, because we completely want to delegate to client itself rather than relying on primary server. So then the next option is basically downloading directly from blob storage. So here we will directly allow the user to download the file directly from S3. So same way here also we can use the pre-signed URLs to generate the URL that the user can use to download file directly from this blob storage. Like with uploading, the pre-signed URL will give the this pre-signed URL will give the user the permission to download file from specific bucket or location in S3 for limited time, which we can have a control on. The flow it's going to look like this. Here you see the download that we have. We try to download via pre-signed URL directly from S3. So I request pre-signed URL from backend. So this is the step that we have, and try to get the pre-signed URL and then use the pre-signed URL to download from S3, which is a simple way to directly download from blob storage instead of relying on this primary backend server that we have. And the challenge here is this: if let's say users are globally distributed across the regions, and if our blob storage is in a single region, it will still be a slow for a user who is far located from that user, and this goes against our the requirements. Basically they should be able to download as fast as they can, and less latencies is what we should guarantee from our system. Okay, to guarantee the latency is going to be as minimal as possible, it's the next approach that we need to talk about, which is downloading directly from CDN. So what is this approach is, here we try to cache the file closer to users region. So to briefly talk about CDN, a CDN is basically a network of servers which are distributed across the globe that caches files and tries to serve them to users from the server which is closest to them, which reduces latency and speeds up download times. So here is the thing: whenever user requests a file from S3, we use the CDN to cache frequently accessed files and serve that file from that CDN so that it feels way faster for a user who is trying to download the file. Same like S3 pre-signed URLs, we can generate a URL that the user wants to download the file, the thing, and cache it near the CDN, and this will give this URL also ensures security and gives user permission to download a file from specific location in the CDN for a limited time. So this is how we can try to address the issue of the latency and meet this second functional requirements. But however, there are some concerns too. The challenge is to be cautious of. CDNs that we are trying to add are not that cheap. They're expensive, and we should carefully handle which files know to cache and for how long. So basically, to make sure that we are not caching all the files, we should only cache frequently accessed files and have a proper cache invalidation to remove files which are either deleted from blob storage or from file metadata db, or the things which are updated. So this is something, the cache control, the invalidation and updation is something that we need to carefully design when we are trying to add a CDN into our design. Okay, so yeah, with this approach we can satisfy the second requirement. The user should be able to download file and it should be way quicker and way faster. Let's go to our third requirement, functional requirement. User should be able to share file to multiple users. And here as well, let's talk about multiple ways how we can achieve this. First thing, we try to add a share list to our document schema which we had earlier. Here I try to update the share list like to the user IDs that I want to share, and based on this, whenever user tries to open a site, we try to just check against this list and see to which users the files have been shared with, and showcase accordingly if the user ID is in this list. The problem here is getting a list of files for a user is easy because we can directly query on the ID which is all indexed on and get that thing. But I mean, because we have the uploaded by, and we can just filter by this and get the files that are belonging to a specific user. But getting the list of files that are shared with them is very slow because we'll have to look up through each document shares list and try to get the user IDs and all. So this way we need to scan the entire share list of every file and see if the user is present or not. So this makes way slower for us to query the files that have been shared with. So this is again not going to meet, and it's going to affect the latency and experience of the user. To avoid that and maybe to speed up the fetching the share list, what we can do is we can try to cache to speed up the querying of share list. So maybe in a cache the key might look to this user ID, these are the files that have been shared with. So now we just need to look for that user ID key and get all the files that have been shared with. Again, this approach also comes with downsides. What is that thing? We need to make sure that we sync the share list inside our metadata DB and in the cache. So that is something we should carefully think about the logic. Make sure the contents in the share list in our metadata DB or in a cache are consistent. So yeah, to overcome this, what is that we can do is basically we need to maintain user to file list mapping in the same database and update both the share list and shared files mapping in the same transaction. That is what our third approach is. We try to create a separate table for shares. It's kind of like we know the normalization that we all learned in our colleges. So we try to normalize the data, that is user ID to file ID mapping. So this way it becomes way clear which file the user is having access to. So but this solves the issue of syncing, not to worry about syncing between cache and the file metadata DB. The query is a little bit slower when compared to direct memory access, but that's fine. That's a trade-off we are willing to play with, because the consistency is very important for us than the this one. So that's the one trade-off which we are willing to make a decision. Okay, yeah, this is how we can try to make sure the file sharing is also well taken care of and meets our requirements. The fourth functional requirements in our this system design is users should be able to sync files across devices. So this is something which is way trickier, and let's talk about this. There are two directions that we need to keep addressing. That is the bidirectional. One is local to remote and another is remote to local. So remote is nothing but our cloud, and local can be users mobile desktop or whatever client is. To get started with, let's consider remote is something is always considered as single source of truth for the file to take the update from or update to. Okay, let's talk about first thing, local to remote. So this is whenever user updates a file on their local machine, can be either Mac or Windows or mobile or whatever, we need to sync these the changes in the local to our remote server. So as we said, we consider remote as a single source of truth. So it's important that we keep this one as consistent as soon as there are some changes in our local. So to do this, we need something called client-side synchronization agent. Let's talk about that. For us to achieve that, we need to monitor the local folder, whatever, let's say maybe for folder name can be something like Drive or Dropbox and all. And how can we monitor local folder is basically just leveraging OS specific file system events. So if it's a Mac OS, we can rely on this FS events, and if it's Windows OS, we can rely on this file system watcher. So when it detects a change in this particular folder, it queues the modified file, the one that has been updated, for upload locally, and then it uses our upload API to update our remote server along with the metadata. So the one thing here is, if there are multiple writes. Which one to consider? To keep it simple, let's consider that always the last version is going to win, meaning we always consider the last write is something that is the thing needs to be synced up with the remote. It's not the most optimal way to think of. We need to version that and maintain those versions in our remote servers, but maybe we can not worry about that versioning for now. Maybe you can consider that as like how to scope for this discussion and just go ahead with this last right wins. And that's how we can try to sync the changes from local to remote. The other direction now, remote to local. So now each client needs to know when changes happen on our remote server. They can pull changes down to their respective local folders. So there are two main approaches that we can think of. One is polling. What is this polling? Client periodically checks, asks like, has anything changed since my last sync? Uh, mm, then the server would query it. The server would query this database and see if any files that the user is watching has updated at a timestamp that is newer than the last time they synced. Okay, this is simple but can be slow to detect changes, and it wastes a lot of bandwidth if nothing has changed, because there will be continuous calls, and which is wasting a lot of bandwidth. The other approach is WebSockets or server sentiments. Here the server maintains an open connection with the client. It maintains open connection with the clients, and then it pushes notifications to client whenever some change occurs. This is more complex to implement, but it really provides it really provides real-time updates. So which one to consider for our approach? Best is to make this hybrid, meaning we try to leverage both of them. Mostly the users are worried about the recent files that they are uploaded. So for recent files, user expects real-time updates or the things need to be synced locally. So for that we can leverage the WebSockets or server sent events for real-time updates. And for the files which are way older, where the access to that files is very rare, and for that we can rely on polling, since immediate updates are not critical to the end users. So this is how we can make sure we leverage this hybrid approach of syncing from remote to local. So after this is how the design is going to look like. For local to remote, we watch changes locally and update remote in the client uploader, the downloader. I know they can be the same, but just for representative purpose I have just added a couple of boxes here. And for downloader, we try to poll for changes in remote and try to sync the thing. So yeah, this is how we can make sure the syncing happens bidirectionally and makes our system consistent. And that is how we are going to meet the fourth point, that users can sync files across devices. This is the design, how it's going to look like. Okay, right. Now let's talk about the potential non-functional points one at a time. That is the deep dives. In that the first point is, we need to support larger files. User can come with a 100 GB file, 200 GB file, and he should still be able to upload that with, like he used to, with a smaller file. And how are we going to give him the same experience as he comes up with the bigger file? So one is progress indicator. That is, we need to let the user know that the upload is happening, and something with like percentage and how long it's going to take and all. And also the other thing that we need to give the user an option is for resumable uploads. Basically this is we should support the user to pass and resume uploads. Like if they lose some internet connection or they close the browser, they should be able to pick up from where they left off, rather than all the way doing it from scratch. So this is something that we need to keep these two things into consideration and try to design our system. Okay, assume, like, we don't have this, and why can't we make that happen just via single post request? There are challenges. Let's try to discuss about them. It's important that we know the limitations and why we are choosing this one. So why not a single post request? It's because web servers and clients have a timeout settings. So by default they will have some cap on how long they can have a connection. So let's take for example, the 50 GB file is something that the user wants to upload. So let's estimate how long this might take to get into our server. Assume the network speed is 100 megabits per second, and the 500 GB 50 GB file over 100 megabits per second, it is going to take 1.11 hours. How? Let's see. 50 GB, let's convert into from bytes to gigabits. So 1 byte is 8 bits, so 50 multiplied by 8, it is 400 gigabits. And now this gigabits needs to be converted to megabits. So 1 giga is 1000 mega, so multiplied by 1000, it's going to give us the 400,000 megabits. And now we have 400,000 megabits. Let's try to divide this by the 100 megabits per second. So this gives us 4000 seconds. So converting into minutes, approximately 66.67 minutes to hours, it's 1.11 something closer to that, or 1.6 or whatever it is. Okay, so this long is what it's going to take for a 50 GB file over this network speed to get into a server, which is nothing that the user can wait, which is very bad user experience. Even you or me cannot wait for that long, and is just going to not use our service anymore. And another thing is, most browsers and servers will have a limitation on size of the request payload. Max, let's say 2 GB, but here our file is 50 GB, which is clearly not supporting our requirement. And another thing, network interruptions, like either users may lose internet or something, or as such, which completely provides bad user experience if you choose a single post request. That is why we need to address this and break down into chunks, which is an option, like chunking on client side, and able to provide a progress as each chunk gets successfully uploaded, and that is what provides a good user experience. So let's talk about one thing at a time. Yeah, the chunking, like let's say we have a 50 GB file, so I'm going to break down into chunk of like 10 MB or 20 MB, depending upon the network speed and bandwidth and all, and we try to update each chunk and update progress on the our side, so that user gets a track of the percentage of the upload that is completed and how long it's going to take to upload the whole file. So that's how we are going to address this progress indicator. And the other thing is resumable uploads. How are we going to ensure this is going to be supported? First thing is we need to keep track of each chunk status in our metadata DB example. So we had this one way before till status. And additional thing is chunks. Let's say we have like 3 chunks. For chunk 1, what is the status? Is it uploaded, uploading, or not uploaded? So we need to maintain at a chunk level the status, so that when a user tries to resume the upload, we can check the chunks list and see which chunks have been uploaded, which have not been uploaded, and then we can start uploading the chunks that have not been uploaded. This way the user doesn't have to start all the way from the full file. Okay, all right, so this is how we ensure the uploads are resumable. Now the other question is how to keep these chunks in sync in the storage bucket. So we are in our metadata DB, we are just maintaining the status of the chunk, but actual chunk is stored in the S3, right? And we need to keep in sync between the storage service and our metadata DB. How? Let's discuss about that. There are 2 approaches that we can think of. First thing is the client takes the file chunk set and uploads the chunk directly in S3 that we have, and S3 responds to each chunk with a success message. So here client uploads to S3, S3 responds with success. Now on each success, the client sends a patch request to backend to update chunks field and that respective chunk. So it's more on relying on client to make a patch request to our server and update metadata DB accordingly. So downside is that itself, relying on client to update backend, it's something that we should not consider, because a user can maliciously update backend status through just patch request without actually uploading that to S3 which is a corrupt entry that we are allowing into our metadata DB. So this downside, the challenge, just makes really hard for us to go ahead with this approach. The other thing is it's better to rely on the by default S3's event notifications. So what happens here is we can rely on S3 event notifications. On each chunk upload, we can trigger the Lambda function or send a message to our simple notification service topic, which we can use this to send a message to backend when chunk is successfully uploaded and update the status accordingly in our file metadata DB. So this is more reliable than the patch request. And now all right, that this is going to ensure the synchronization issue. The other question now we can come up with, or the thing that we need to discuss, is how do we check if the file that the user is trying to upload is already uploaded, is already there in our system, and assume like we somehow figured out that logic. Now we also need to make sure which chunks of that file have already been uploaded and which chunks have not been uploaded. Okay, so to answer both of the questions, the approach that we need to rely on, of course we cannot rely on the file name. I can have the same file name uploaded multiple times for a different file content, so that's not the way to keep track of the unique file identifier. So the approach that we can rely on is something called fingerprint. So to just give an idea of what is fingerprint at high level, it's simple mathematical calculation that generates unique hash value based on the actual file content. uh, mm, Ideally that hash value is generated using cryptographic hash functions such as SHA-256, and we take this as a unique identifier of the file and check against our DB, and if that file unique ID exists, we know that the file is already there in our system or is been uploaded before. For a chunk level also we need to maintain this fingerprint. So this way it ensures that we can at least have a logic to query if the file has been uploaded before or not, if the chunk has been uploaded or not. Okay, so the flow is going to look like when we try to tie all of this together. Client chunks file like 5 to 10 megabytes, and we try to calculate fingerprint for each chunk and along with the full file. Okay, and yeah, client sends a get request to file metadata DB for the file with the given file ID, which is the fingerprint, just to check if the file ID exists in our DB or not. So let's assume it exists, then we resume the logic of resumable uploads. If file doesn't exist, then client will post a request to /files pre-signed URL concept, which we just discussed, to get a pre-signed URL for the file, and the backend will save the metadata DB with the status of uploading, and chunks array will be a list of a chunk fingerprints with the status of not uploaded. Then client uploads the chunks to S3 via the pre-signed URL which we just gave to the client, and after each chunk is uploaded, S3 notifies backend and backend marks that respective chunks as uploaded. And once all chunks of a file are uploaded, we mark the file as uploaded. So this is how the approach is going to look like when we try to tie all of this together. So this is here the simple approach. That's how it's going to look like. We try to chunk file and client and calculate fingerprints for bigger files and make sure we support this large files. So that's how we can support larger files upload. By default, AWS provides us multi-part upload, which out of the box has all of the support for chunking and the status updates, progress and all. But it's good to know this is how it's done behind the scenes, and we can leverage AWS multi-part upload. Yep. All right, so that's one of the things. And now the other thing is we need to make sure the uploads downloads are way faster. So how are we going to make sure? We already made sure that we break down into chunks and leverage a CDN to cache a file closer to the user, which really makes faster for downloading. For uploading, we made sure chunking and resumable uploads, making sure it's way faster, and also we can send chunks in parallel depending upon the available bandwidth. So this makes uploads and downloads faster. So it's already taken care. We can not worry much about that. The other thing is, apart from that, how can we make sure it's way faster? For syncing, the one, instead of trying to sync the whole file, now we have introduced the concept of chunking. We can just identify chunks which are changed and only sync them bidirectional, the remote to local and local to remote. Okay. And another way to make our system way faster is compression. So we can compress file on client, before trying to send it to our server or storage service. So here the question is which files to compress and which files not to. So let's say, like, if the file the time it takes to compress a file is way higher than the time it takes to send and upload it to our server, then that's obviously a scenario that we need to go uh, uploading file directly and not go for compression. A good example here is, for images, I don't think there's going to be much significant differences, so no need of compressing there. But whereas for text files, PDF files, we can choose compressions. It is going to reduce the size of, like, let's say 5 GB 10 GB file to 1 GB or 2 GB, which it's good for us to reduce the file size so it can be uploaded way faster. And once it is uploaded to the server, we can decompress on the server, and just the vice versa. So yeah, the algorithms that are good for compressing is Czip, Brotli, and Z standard. So most adapted one is Czip, or we can just choose the Brotli or Z standard. But it's also the thing that we need to consider when we are choosing the compression algorithm is it supported in the most popular web browsers or not. Okay. And another is, if we have introduced encrypting for security purposes, it's better to compress before encrypting, because of not introducing in unpredictable random number, and also for much higher compression ratio. So this is how we can make sure the uploads, downloads, and syncing way faster, apart from a CDN and the chunking and resumable uploads that we introduced above. The additional thing it's a good to discuss on. And now the last thing, we need to make sure the file is secure whenever we are in trying to transfer over the network, or when we are storing in a blob storage service. How do we make sure? There are three ways. One is encryption in transit. So yeah, whenever we are trying to share a file over a network, make sure it's always encrypted. So the HTTPS, which we normally consider. And the encryption at rest, it's simple. We can just leverage S3's encryption feature, which will encrypt the file using a unique key and store the key separately from the file. This way, even if some user gets access to the file, they won't be able to decrypt it without the key, which is stored separately from the file. And we do already have the access control, the shares list, so we restrict the unauthenticated users from accessing that by using the shares list. So we limit that. And the question is, what if some authorized user shares a download link with an unauthorized user, maybe over a public forum or so? This is not much of a concern, because anyhow we always give pre-signed URLs within a timeout. Even if they get an access to it, will be expired after 5 minutes or so. So it is not of a big concern, and that pre-signed URL, it's going to take care of that unauthorized users trying to access the content of our authorized user. So this is how we can make sure the file is secure and it's not easy to tamper with. Yep. So yeah, concluding, this is a brief discussion on our Dropbox or Google Drive high level system design discussions. Though it's not much, but at least, given the couple of points in our requirements, we try to reason up the choices that we made and why we made, and made it clear. It's going to the ultimate design that we have, it's going to support and satisfy the requirements. So this is the end of this Dropbox or Google Drive discussion. Next, let's discuss on something like local delivery systems that we normally see, the Blinkit or Zepto, and how can we at least take a couple of minimal requirements and think through and reason up for the system that can support them. Blinkit or Zepto, we all know what they do. They deliver day-to-day goods typically found in their own dark stores or convenience stores via rapid delivery. So that's what they do at a high level. And let's have a look at the requirements as usual, breaking down them into functional and non-functional. So here the first requirement is user should be able to query the availability of items by geography, something that can be delivered to them in 1 hour ETA. The second requirement is user should be able to order multiple items at the same time. So these are the like two minimalistic features that we will try to focus on. The others which I just added, they are not in the scope of this discussion, which are payments or purchases. So OS is basically an indicator of out of scope, and driver routing, search and catalog APIs, and the cancellations, returns and refunds. They're good to discuss or good to have them, but I don't think they're necessary for us to discuss in this video. And coming down to the non-functional, users can connect to any dark stores or distribution center, whatever we call, within 1 hour. And the latency whenever they query for availability of items, it should be less than 100 milliseconds. And the ordering should be consistent, meaning we should not let multiple users order the same item. So need to make sure it is consistent, and we need to support more than 10k dark stores and more than 100k items in a catalog. And let's assume the traffic or the volume that we are going to receive for the system is in the order of 10 million per day. So these are the functional and non-functional requirements that we need to keep in mind while we are designing the systems. So looking at this functional non-functional, we can clearly identify the core entities, and let's go to the core entities section. So the core entities from the functional non-functional requirements, it is the item, the inventory, dark store, order and order item. So here item you can just consider that as a simple class or representation. The physical instance of an item will be in inventory, which will be located at dark stores. So we'll try to sum up all of the inventory to determine the quantity to a specific user for a specific item. So this is the inventory thing. And here, like I said, item is basically just the representation to a user in our site or an app, kind of like, you know, sneakers or lace or whatever the items that they want to order. The dark store, it is actual physical location where items are stored. We will use this to determine which items are available for a user. So basically this inventories that we have will be stored in this dark store. And the order is nothing but a collection of this inventory which have been ordered by user. So order item. So it's a simple self-explanatory. So these are the core entities that are identified from our above functional and non-functional requirements. Once we have clearly defined these core entities, let's not worry about each of the columns and all, like we discussed earlier. As we go deeper into our design, we will try to expand on them. The third section is the APIs, the system interface where clients try to interact. So it is basically each endpoint for each of our functional requirements. Since we are going to talk about two features, we will have two endpoints. One first endpoint is querying the availability. So this one, given a location, the latitude and longitude, along with some keyword, they can search by the items keyword. And let's also add a pagination for the results that will be displaying to the user with the page size and page number. Given this param, we return list of items. So for just the purpose of it, assuming we'll have name and quantity, so we return list of items to the user. So this is one endpoint, query availability. The other one is to place an order, so which is a simple way for an user to place an order. So here we take latitude, longitude and items that the user wants to place an order for, and the return type is going to be either order object or the failure message. Okay, so these are like simple endpoints that we can think of currently for our functional requirements. Once we have this APIs clearly defined, let's now go deeper and try to discuss one point at a time from our functional requirements. So the section is the high level design. The first thing is users can query availability of items. So here we can break down into two steps. First is we need to find the dark stores that are close enough to deliver in our in 1 hour ETA, which is our requirement. The other is, let's say somehow we found the dark stores. Once we have a list of the dark stores, we need to check inventory and return union of all of the items to the users. So those are the two steps that we need to fulfill the first functional requirement. All right, let's talk about the point one. How do we find nearby dark stores? We can build a simple internal service which maybe takes latitude and longitude and then returns list of dark stores by querying let's say dark stores table within 1 hour. Yeah, and then we can return that to the user. So this is like something we can calculate the distance using simple Euclidean distance and then return that list of dark stores to the user. This is how it will look. Nearby service trying to query our dark store table and return that based on the Euclidean distance that we calculated. Maybe I can have the structure of the dark store table as a ID column, latitude and longitude. The second step is this. Now we got the dark stores and we need to now check inventory and return union of them to users. So let's try to create an availability service which handles requests from users for availability given a specific location. So this tries to query our item table and the inventory table which will have a structure of this type: item having ID column, name column and description, inventory item ID and DSID and quantity. So this will query based on the dark store ID that we have and try to join both of the tables to get the name and description and return from this service to the users. So this is how we first find out the dark store, and using that dark store we try to join the items and inventory table by matching that dark store ID and only get the name and descriptions list. That's what we need to do this both operations in less than 100 milliseconds. So that's the something that we need to take care. So how can we make sure the steps that we discussed just now, it's going to happen in less than 100 milliseconds? So maybe let's try to recap on the how the flow is going to look like. So we make a request to the availability service with users locations, latitude and longitude, and any irrelevant filters if he has passed on. Then this one will make a request to nearby service. So here this is what, so this is how it's going to look like putting it all together. So user makes a request to availability service. This fires a request to our nearby service with the user's locations, latitude and longitude. The nearby service will query this dark stores table and return a list of the dark stores to availability service. Now with the dark stores available, the availability service will query our database, the primary database, with those dark store IDs and join the both item table and inventory table with our required columns, the name and description, and then we sum up the results and return them to our client. So this is how it's going to look like for our first functional requirement. This is something the flow will look like after breaking down into two steps: finding the dark store first and then the respective inventories from those dark stores that we found. Let's talk about the second requirement. We'll talk about that latency in our deep dives. I'll come back to that. Let's at least now discuss at high level, and then we'll deep dive into the specific component that we are interested in. The second thing is user can place an order. The important thing that we need to consider for this requirement is we need to make sure it is strongly consistent. That is, we should not allow two users ordering the same item. So how are we going to make sure that this is achieved? So one thing, there are a couple of ways that we can think of. One is we can have two databases with a distributed log. So how is this going to work? Let's say we have orders and inventory tables. Maybe orders we can have something like NoSQL database, and inventory in a Postgres database, relational database, whichever works best for them. So that's one thing we'll have complete control on, because we are trying to maintain two databases. So the flow is, when an order is placed, we try to log relevant inventory records and then create an order record, decrement the inventory, and then release the log, so that we don't let others to access that resource and make sure that it is logged. So this is how the flow is going to look like. But the problem with this approach is, what if the first step, order is created, that is, we have created order record, but somehow server is crashed. If server is crashed, we cannot perform this operation, which is decrementing the inventory. So if we can't perform that, and let's assume that subsequent user places a request, the same request, and we try to create a record, and he might try to order the same one, which isn't the case, and that is the thing that we need to handle. So that's one thing that we cannot handle in this situation, and we can handle, but we need to be very cautious for that one. And other thing is, there's a high chance for deadlock. So let's say there are two orders having overlapping inventory, meaning, so user 1 is trying to buy item 1 and item 2. User 1 is trying to buy item 1, and user 2 is trying to buy item 1 or item 2. So both are trying to buy item 1 and item 2. Let's say first user 1 has a lock for item 2 and user 2 has a lock for item 2. Now user 1 is trying to wait to get hold of item 2, and user 2 is trying to get a hold of this item 1. Both are waiting for respective item to be unlocked, and none of them are releasing, so it will be a deadlock. They are going to wait forever. So that's something which causes a challenge for us if you try to follow this approach. The other approach is singular Postgres transaction. So it's a simple approach, which it's simple. We try to put orders and inventory table in a singular Postgres database, and we can leverage ACID properties of our Postgres database with an isolation level of the serializable. So this ensures that the entire transaction is atomic. That means even if two users try to order the same item at the same time, one of them will be rejected. This is because transaction will fail to commit if the inventory is not available. So this is how it's going to look like, the order, and we try to perform all of those operations in single transaction. Yeah, and the cautious points is tightly, we are just trying to tightly couple this inventory table and orders table, so we cannot have a control to independently scale them. That's fine, because we are trying to address the deadlocks and consistency issue, which is very important for us than scaling individually. And also we cannot have our own choice of storing them. So for example, let's say inventory, we NoSQL database works best for that. For orders, Postgres might work best for that. So that choices we cannot make. So those are like the simple things that we are not much worried about, but it's good to have highlight this challenges. So putting it all together, this is how it's going to look like. The user customer tries to talk to any of our services through API gateway. So the user makes a request to our order service to place an order, let's say for items 1, 2, 3. The order service creates a singular transaction in our database, which is our Postgres leader. This transaction first checks the inventory for items 1, 2, 3, and if any items are out of stock, the transaction fails. And if all items are in stock or in inventory, the transaction records the order in orders table and updates the status for inventory items in this table 1, 2, 3 as ordered, and a new row will be finally created in this orders table. So, and transaction will be committed. So if the transaction succeeds, we return the order to the users. Okay, so this is how it's going to look like. Users tries to place order, and we try to write the transactions to respective tables in our Postgres database, and if transaction is successful, we return all the way order to the user. So this is how we make sure the consistency is taken care of by leveraging the transaction and a serializable isolation level. So that's how we are going to handle that. Now let's talk about the deep dives. One thing is the availability lookups. That is basically whenever user is trying to search for an item, we are not considering now the traffic and drive time issues. We're just calculating based on the Euclidean distance, based on the user's latitude, longitude, and whichever is something that is near and can be delivered in 1 hour, we are just returning that. So there's not much of a logic. How can we incorporate traffic and drive time is something we can discuss. So currently, like I said, we do have a simple SQL distance. That is what we input latitude and longitude to our dark stores table, and just written nearby dark stores. So here we are not taking into account traffic or road conditions or other things, and also it doesn't take into consideration of the fact that we might have multiple data stores in the same city. That's one thing. So now the other approach is introducing travel time estimation service against all data stores. So how this is going to work is, since our dark stores are rarely going to change because they are buildings, or we can sync periodically, like let's say every 5 minutes or 10 minutes, from our dark store table to memory of our service, and then we can use a travel time service to find the travel times from our input location to each of our data dark stores by iterating over all of them. So this is how it's going to look like. The flow, we keep periodically syncing dark stores to memory of nearby service, and then travel time service is going to leverage that and also taking the input and try to calculate based on the logic that we'll have in travel time service. So assume that's a black box for now. And the disadvantage of this is basically we make too many queries to travel time service and unnecessary queries for all our dark stores. We don't want to do for all dark stores. So to avoid that, the third approach is this: we try to call this travel time estimation service against only nearby dark stores. So it is we can maybe just sync only the dark stores which are nearer. Maybe let's say we fix it by radius, let's say 60 kilometers or miles, which is most optimistic distance that can be covered in an hour, which is our requirements, and accordingly deliver the item to the user. So this is something we can only calculate the travel time against nearest dark stores. That's how we can address this availability lookups, trying to incorporate traffic and drive time. Okay, yep. So this might not be that elaborative, but it's just to give you an idea. So and later we can discuss on this if it's needed, or you can do your due diligence and search on the go and understand how it can be done. That's one of the deep dive. The other deep dive is the latency issue. So we need to make sure the items that the user is trying to search for, we are showcasing in a very less response time. So assume the order that we mentioned in our functional requirements or non-functional, it is something we receive 10 million orders per day. So assuming each user makes 10 queries per day, so let's try to convert this 10 million orders per day to seconds, and it is 10 queries per each user. So it sums up to 1000 queries per second. So and this is orders. So assuming out of all the users that are visiting our site or mobile application, only 5% buy, that is 5% of them make an order. So if 5% is 1000 queries, so then whole users queries is going to be divided by that 5%. It's going to give us 20k queries per second. So this is the traffic that we need to handle and make sure our system delivers the results in very less response time and less than 100 milliseconds. So how can we handle this scale of very high read heavy traffic? This can be addressed using two approaches. One is we try to introduce a cache. So we try to add a cache for our inventory. So this is how it's going to look like. Our availability service now will have a Redis attached, where it can this service can query cache for given set of inputs, and if cache is having that content, it will straight away return the results to user. If we miss that, we'll do a lookup on this underlying inventory database and then write the results into our cache. Maybe we can set our time to leave as 1 minute so that results are fresh and not stale. So this one way we can take care of that. The other, and again the challenge here is, we need to make sure the Redis is always in sync with the actual data that we have in our database. So that's one thing. The other approach is leverage a concept of read replicas and partitioning. So we try to have a one master write Postgres instance and others are all read replicas, and also we try to partition by region IDs. The thing here is, since we only read inventory from nearby dark stores, we can group them by region IDs. So let's say pin code, first 3 digits of a pin code. Then we can partition our inventory data based on this region IDs. Now this means that our queries will mostly go to 1 or 2 partitions rather than entire inventory table, which improves our performance way faster, right? So yeah, this is how we try to address read heavy systems by having additional read replicas. Along with that, partitioning by region IDs and query only certain records of inventory table, and this will make sure the query results are within the latency constraints. Though there might be little consistency to our read replicas, but that's fine if the user is if user is receiving stale data for a particular period of time. It's not of a bigger concern for a user. So that's how we can address through cache or read replicas and partitioning. So after putting it all together, the downside of this is basically we need to make a choice on size of replicas and carefully manage partitioning of data, and partitioning by region ID in this case, and accordingly have a good discussion on these points and accordingly design our system. Now putting it all together, this is how it's going to look like. The read replicas is what we are going to go with instead of the caches, along with the sharding. So this is how it's going to look like after introducing this read replicas and sharding techniques. So this is how our final design for the requirements that we stated above it's going to look like. User talks to all of our services through API gateway. So we do have here now the availability service to serve the list of items that the user wants to see in our products catalog list, and then we have internal service to find the dark stores, and the other service which is order service where user can place an order. And here it's basically our Postgres leader where we are trying to have all of our tables, items table, inventory table, and orders table. So this is how we can address the requirements, and like this there are other points as well which we have not discussed, but you can just Google it on, learn it on the go, and try to add those solutions also into the systems. Yep. And next let's move on to a news aggregator system, something like Google News, and we'll discuss more on that now let's talk about Google News Aggregator. At a high level, what it does is a simple digital service that aggregates and displays news articles from thousands of publishers worldwide in a simple scrollable interface, so that users can stay up to date on current events. So that's what it does at high level. Let's have a look at the requirements, functional and non-functional. The first point is users should be able to view news from many publishers around the world and then they should be able to scroll infinitely so that they can have look at n number of articles from publishers around the world. And whenever they try to click on that article, it should redirect the user to that respective publisher's website. So those are like core functional requirements that we need to keep in mind when we are designing this system. Non-functional is we should give high priority for availability than consistency, and we should handle minimum of 100 million daily active users and should be able to handle a peak traffic of let's say 500 million daily active users. And the other point is the latency to load feed should be less than 200 milliseconds. So that's very important for best user experience so that they can stick to our application. So these are the core functional and non-functional requirements that we should satisfy. So looking at this, now we should be clear what are our core entities. So let's go down to the core entities section. The core entities is the article and the publisher, the user. So article, so basically this represents an simple news articles with attributes like ID, title, summary, its thumbnail URL, publish date, publisher ID, region, any other media URLs. So this is our actually core content entity for our functional requirements. The next one is publisher. It's basically the one which represents a source for our article with attributes like ID, name, URL, feed URL, and or region. For now maybe those are the things. And then the user, who represents the system users with attributes like ID and region. Though attributes we don't have to discuss it right now, but once we are clear what are the core entities, then it should give us a solid starting point for us to proceed to next phase, and then slowly expand the respective entities as we deep dive to specific sections. After core entities are clear for us, let's go to the APIs section. So in here, the API section, main one that we are going to have for now is simple feed endpoint. That is the one which tries to get the aggregated feed of all news articles with query param like the page number, and then the limit, and then the region, and then we return the list of articles, and that will be displayed on the home page of our website, and users can scroll through that. So this is a core endpoint that we will be trying to focus on in this system design question. Now that we are clear, let's go to the next phase, which is discussing high level section. So this is where now we'll try to discuss on each of our functional requirement point and expand on that. The first point is user can view a global aggregated news feed from thousands of publishers. So that is a thing now we should expand on, and how are we going to achieve this? So for this one to be accomplished, there are two steps. One is we should collect content from publishers, and once we collect content from publishers, we can serve them to our users, which is basically the feed. So how are we going to achieve first point so that we can facilitate the second point? So let's discuss on that. The first point that we are going to mainly focus on here is data collection service, which is very, very important. So this data collection service is basically a background process which tries to continuously gather content from thousands of news sources and populate our database. So what this does, so the core entities that we have in this data collection service is data collection service and the S3 to store the thumbnails that we'll be getting from all the external publishers, and also saving the content or the metadata of those articles into our database. So how does this work ideally? So data collection service, it tries to poll the RSS feeds of external publishers, like let's say every 3 to 6 hours, based on each publisher's update frequency. So those the external publishers, like whoever we are talking about, like thousands of news sources worldwide that actually provide content via RSS feeds or APIs. And once we try to get the content from those publishers by polling, we store the collected articles and publishers and metadata into our database. So the article table might look something like this, with the ID, attribute, title, summary, thumbnail URL, publish date URL, and other stuff for now, and publisher ID, name, URL, and RSS feed URL, last scraped time and all. And this is where we store the metadata, and the any thumbnail URL of that respective article will be stored in this S3, and we'll just store a reference to that URL in our article table. So this is how it's going to look like, the data collection service workflow. The data collection service, it queries the database for list of the publishers and then their RSS feed URLs before querying each publisher one after another. So once we get the list of publishers from our database, this data collection service tries to extract article content, metadata, and downloads any media that is associated with that article as a thumbnail from this external publishers, and stores these thumbnails in our S3 object storage, and saves the article data in our article table. So that's how the flow is going to look like. So there is an RSS thing. So what is that is basically that is a really simple syndication. That is simple XML format that allows publishers to syndicate the content to other websites and readers. So it's a common format actually that major publishers support, so that others aggregators can leverage and populate their website. That's the RSS thing, and this is how the whole of this data collection service is going to look like. Okay, so the question might be here, why are we storing the thumbnail URLs in our own storage rather than leveraging their remote URL? It's basically we want to have more control on the thumbnail URLs, and so that even if you want to customize, resize, or do some optimization, and not to rely on the server's availability, we are delegating it to our own S3 object storage. Yep. So now that we have this data collection service and articles table populated and all, we can serve it to users feed. So this is now it's how it's going to look like, the feed service. So the data collection service, like I said, it's a background process which is not exposed to users. It is more of an internal service. So here client makes a request for our feed get endpoint with the region, let's say Asia and limit 20, and that will be processed through our API gateway, which takes care of routing and other things, rate limiting and all. So here we have a feed service. So this feed service, it tries to handle the feed request that user sends by querying our database for relevant articles, which is populated by our data collection service based on this user's region, and format the response and return accordingly to the client. So that's what this feed service does. Yeah, this is how first we try to accomplish the step 1, and then that facilitates the step 2, and collectively we can achieve the first functional requirement. Yep. And this is more of not exposed to users, because this is more of a write heavy, and it's more of a background a processing service which is not needed for an end user. So that is why it's more of the internal service, which helps us to which helps for the feed service to query the articles table. That is the first functional requirement. Simple. Client sends a GET request to this endpoint, an API gateway routes the request to our feed service, and which queries the database. Database returns data including all the metadata and media URLs, and this feed service formats and returns the list of the articles to the client. So that's how it's going to be very simple. So that's the first point. Now let's talk about the second point, that is users can scroll infinitely. So basically users expect to continuously scroll through their newsfeed without manual pagination. So this requires us to handle pagination server side, so that we can load new batches of content as users keep scrolling. So it is simple. What we do is, whenever user tries to load their feed, they send a request to our endpoint with this page number, like here the page 1, which indicates first page, and this feed service queries for the first 20 articles, which is the limit in that specific region, maybe ordering by publish date. And the response includes articles. Along with that, the additional pagination details, which is the total pages and the current pages, current page that we have written. And now the client somewhere stores the current page number for the next request. Now as the user keeps scrolling and reaches the end of the current content that is in, the next subsequent request is going to be like this, with the page which is the current page which we returned previously, and the limit is going to be 20, and the feed service will calculate the offset, which is basically how many rows it should skip, which is the 20 rows that it should skip, and then from there the next 20 rows, it's what it should return for the page 2, and it will be calculated by feed service, and it will return to the user, and it repeats as user keeps reaching the end of the scroll. So this is how we achieve using offset pagination logic, so that it doesn't seem like a manual pagination to the users. So that's how we'll accomplish the second requirement, which is simple. And the third one is, user should be able to redirect to that respective article in the actual source publisher's website. So already we have the link for the article, which is given by publishers while we were trying to poll and store it in our articles table. So the browser it handles it for us, so we don't have to worry much about that. Those are like the main core 3 functional requirements that we need to satisfy. So this is how we did. Now let's talk the specific components of our high level design and see how we can achieve the non-functional requirements as well. So that's the deep dive section. So the deep dive section, so there's a big problem in the 4.2, the functional requirement that we have just discussed. The logic that we have added is offset pagination. So whatever I have highlighted here, this is the problem. So with our current offset pagination, there is an issue when there are new articles are constantly being published, and let's say this is a simple example. Let's say the user is on page 2 and the new articles gets added to the top of the feed, and as they get added to the top of the feed, the content shifts down. So now when user tries to request for page 3, since we are just having a logic of offset based, user might see the same duplicated articles which he has seen before, and or he might miss the new content entirely, so which frustrates a user, and that's not the good way for us to go ahead. And because they should stick to our platform, and we should guarantee a good experience for them. So how are we going to fix this situation for the user? So there are a couple of approaches that we can fix this. The first approach is timestamp based cursors. So here what happens here is, we try to, whenever a user requests their initial field, we return articles along with the cursor, which ideally represents the timestamp of the last article in the response that we sent. So that is what we return. And now for subsequent request, the client includes that cursor, kind of like the last published art which we have returned in the response. So the query looks something like this. So the published at should be less than the cursor timestamp which we returned in the response. So it always makes sure that he receives older articles than the cursor timestamp that we have sent in the response. So this makes sure that users doesn't see the repetitive content or articles that they have seen before in the above response. Alright, but the challenge that comes if we choose this approach is, let's assume, what if multiple articles have identical timestamps? Then we might miss them if they have exact timestamp as a cursor. So that's one of the limitation where users miss articles that were published at the same time as their cursor's boundary. So we should handle that. So to handle that, that is what the next approach is: composite cursor with article ID. So this is like more a sophisticated solution which tries to combine the timestamp along with the article ID, which are like totally ordered cursor. So with this we create this composite cursor which includes the timestamp and then the article ID. This makes sure that even when articles have identical timestamps, as the article ID provides the tie-breaking solution. So that problem which we saw in the previous selection is resolved by this article ID introduction into this composite cursor one. This the query looks something like this. We now will have the composite key published art along with the article ID, and we check if that is less than the cursor timestamp and then the cursor ID, and order by this published art descending order, article ID descending order, and try to limit this. So this is how the query is going to look like, and there should be a composite index on these two fields, the published art and the article ID. So this is how we tackle the problem that we saw in the previous approach. And here just the couple of points that we need to be cautious about is the cursor generation that we just introduced the composite key. We should make sure the logic for that and the way that we parse is carefully taken care. And also now, since we are introducing additional indexes on the new columns, more storage space is needed to store that. So those are like two things that we need to keep into mind. The other approach is the monotonically increasing article IDs. So what this does, this is way simpler than the composite cursor approach. It basically achieves the same result, but instead of using random unique IDs, we can try to use a time ordered IDs, which guarantees they are unique as well as the sortable identifiers. And if we use this UL IDs instead of the random unique IDs, we don't need additional identifier whenever we try to query. So this now it will be just, if we can add an index on this article ID, we can just check if the article ID is less than the cursor ID, and that's when it's going to give us the same result as it gives us with the composite cursor. So this is a simple approach, but the one caveat here is, for distributed systems we need to carefully coordinate this unique ID generation across multiple instances. So that's the only thing. So this is the good approach for us to go ahead with, which is way simpler than this composite index. So that with this, how we try to improve this pagination consistency and efficiency, and make sure that user doesn't see repetitive articles and then they don't even miss new articles. The next point is, how do we make sure the latency that we listed in our non-functional requirement, which is less than 200 milliseconds, and we populate the feed for the user. So currently the user base for us is something 100 million daily active users. So assume at least each user is going to make 5 to 10 queries or requests per day. So they are roughly 100 million multiplied by 5 or 10, they come up to 500 million or 1 billion requests daily. So for this amount of traffic, our DB definitely struggles to meet this latency of 200 less than 200 milliseconds. So we need to think of the approach, how do we overcome this. So whenever we say something related to latency, the first thing that really needs to come to our mind is cache. So that is what, so we try to introduce Reddish cache with time to live, which is a simple thing. So here what we do is simple, we try to cache the articles in a sorted set with the key as the region, like this, something like this, feed US or feed Asia, feed UK, and then we'll store all of the article IDs related to that region, so that whenever user tries to query for that feed, we check in the cache. If it's there, we just written that it guarantees the latency is always going to be less than 200 milliseconds. If not, we try to read the database and then store it in Redis and then return to the client. So this is how this is a simple classic read through cache pattern that we implement here. And yeah, for the next pagination thing, we can just query using this Z reverse range by score. Score is here nothing but the timestamp or the of the article. So this one will help us achieve less than 200 milliseconds, but there's a challenge even with this approach as well. So here the challenge is, the first time user is trying to query the feed service, there will be a cache miss. So that still require expensive database queries, which we discussed in the above approach. The database cannot handle, so it is going to give a bad user experience for at least for initial queries. And also the TTL of 30 minutes always shows a stale content for users at least for at least up to 30 minutes. Only after that they will see fresh articles, the new articles that are being published once we invalidate the cache and then query freshly from DB and store back in cache and then return to the users. So this is one more challenge. The other is, so assume during the cache expiration periods, all users requesting feeds for a region hit the database simultaneously, which is kind of like bombarding the database at the same time. Hundreds of concurrent expensive queries will definitely overwhelm the database. So this results in drastic performance degradation. Maybe it can last several minutes while caches are being repopulated. The user experience here becomes really inconsistent, with some requests being fast, that is cache hits, and others being very slow. So this inconsistent behavior is something we should definitely avoid for best user experience. So this is something that we should not at least agree on to begin with. So the other approach here is real-time cached feeds with change data capture. So this is something that solves the problem which we just discussed. Here what we do is we try to pre-compute. So here what we will actually do is we try to pre-compute and cache the Redis for each region using this change data capture for immediate updates. Now we are maintaining pre-computed feeds in Redis as sorted sets containing article IDs and essential metadata which is organized by region. When new articles are published, this CDC triggers immediately update the relevant regional caches without waiting for TTL expiration. So this ensures that users no longer have to wait for the TTL time of 30 minutes or so, and they don't receive stale content. They receive new articles and up-to-date content with this CDC change data capture thing. So that is this. So without TTL, each regional field now the problem here is if there's no TTL, there comes the problem of how many are we going to keep at a time in a Redis, not to take off all the memory. So for that what we do is we need to find a way to prevent this unbounded cache growth. So what we can do is we just try to maintain only recent n articles. Let's say here maybe 1k or 2k articles per regional field. When adding new articles, we use this zadd to insert the article with its timestamp or score. Then immediately we'll try to call this remove range by rank to trim oldest, preventing oldest articles, preventing unbounded growth. So this ensures that Redis is also balanced storage wise, and the articles are also up to date. Hardly users will not exceed or scroll more than 2000 articles. So this balances both of the issues that we just encountered in the previous approach. So this is the one that we need to stick to achieve this latency of less than 200 milliseconds and also real-time updates to the user's feed. And there is again a bit of points that we need to be cautious of. So one thing is it's more complex to handle the change data capture infrastructure that we discussed. On every change we need to update our cache, trigger and update our cache. It's something because we need to have additional message queues and worker processes and all, which additionally increases our storage costs, but they are very negligible compared to the performance boost that we are getting with this approach. So yeah, so this is the approach that we'll stick to achieve this latency of less than 200 milliseconds for our feed. All right, now the third point is how do we ensure the articles that appear in feed within the 30 minutes window of the actual publication from the publishers. So currently what we are doing, the data collection service is trying to poll every 3 to 6 hours and then of each publisher and populate our database, and then that will populate the feed based on the user's query. This is something very infrequent. So they see users have to wait at least 3 to 6 hours for them to see the publications, and that is not meeting our requirements. So we need to tackle this problem. So how are we going to achieve this? There are a couple of approaches for this as well. One thing is we can increase the RSS polling frequency. That is currently now what we are doing, we are trying to query every 3 to 6 hours. We'll try to introduce a tier based polling system. So here if I just expand here, I'll introduce a tier based polling system. So it is something like the ones who are very high priority publishers for us, kind of like major news outlets or breaking news sources that are very popular, and they have a big user base already. So we group them under high priority data collection service, and we try to poll that every 5 to 10 minutes, so that we get those major publishers articles into our feed as early as possible. And then others will be grouped as mid level priority data collection services, and that we try to poll every 30 minutes. And others, new publishers who doesn't have that much popularity among the users, we can put them under low priority data collection service, where we try to poll every 2 to 3 hours and accordingly feed our database their articles. The issue here is this: it adds significant additional infrastructure challenges and cost implications. Maintaining separate service for this each of the high priority, mid level, and low priority, and it's something that is not a minor thing to take care. It's something of much of an infrastructure overhead. So that is where we should be little bit careful. And let's say assume we have at least now 10k publishers. So assuming we have 10k plus publishers, so and we are making continuous polling every 5 to 10 minutes, 30 minutes, 2 to 3 hours to their servers. So if we are making to a newest publishers who doesn't have that frequent articles, and it is like making too many requests for few articles for those new publisher servers, and they might block our IPs because we are unnecessarily eating them, and it is something that we need to take care. So which is not good point, not at all a good way to to proceed with this approach. And here we are still reactive. It is something we are always asking the publishers and not the other way around. We are still continuously asking them to do you have a new article published, do you have a new article published, and all. And other point is, most new publishers who like we just discussed, who have fewer user bases, they might not even have these RSS feeds for us to provide these articles. So these are the points that we need to take care. So this is not the right approach for us to go ahead with this increased RSS polling frequency. So to mitigate the challenges, at least that we saw, the other approach that we can think of is intelligent web scraping. So here this approach, what it does is, it at least tries to solve the problem of the publishers who doesn't have their RSS feeding servers. So for them, we need to add this web crawler approach. So what this does is basically this web scraper, it will try to navigate to publishers home pages and their category pages, looking for new article links, searching for elements with classes like in their respective DOM pages, article headline or story link, news item, and extracting URLs, titles, any metadata or publication timestamps. And this once we get that, we collect that and populate our database. So here for each target website, we try to maintain a fingerprint database of previously seen articles, usually like the URL hashes and all, so that we make sure that we don't add duplicate entries into our article table. Yep. So that's how we detect the duplicate thing, based on the hashes, and make sure that we have unique articles stored in our table. So again, same like we had for this RSS, we'll have the same way for web scraper as well. Whoever having high traffic or more number of articles being published, we try to scrape this every 10 to 15 minutes, while smaller sites might only be checked hourly or maybe weekly or something like that. So this way we try to club both of the approaches. Whoever is providing RSS feeds, we follow that approach. Whoever doesn't have RSS feeds, we try to follow this web scraping approach. And now the challenge with this approach is this: the web scraping needs significant maintenance, because they might constantly change their websites. The DOM might change, the pages might change, and since we need to take care of all of this, we should constantly monitor their websites and see if something is changed, and accordingly maintain their a standard format and the classes, the IDs in our database accordingly, so that we can scrape the right content that we need for our table. So that's one downside with this approach. So even to avoid this, there is one thing that we can completely shift to push based from pull based. So as of now, it was all about like we asking their publishers, do you have new articles, do you have new articles all the time. So it's now, let's look the other way around. So if any new article gets published in their servers, they let us know through a webhook concept that this new article is published. So we'll be listening on a particular webhook, and once the publisher hits that webhook, we accordingly update that region with that article, and it will be populated like that. So let's discuss here. What happens here is we introduce here this webhook service that we have. Let's say something like slash webhook slash articles published, that publishers can call the moment they publish an article containing some article metadata or even the full content payload. This way, instead of us trying to find new articles, we can rely on them telling us about their new articles. Yeah, this is how. And also one point to consider is our webhook infrastructure that we'll be building should have high availability, because all of our publishers will be trying to rely on this endpoint to let their new articles be published or into our news feed. So the endpoint should handle all of the incoming webhook payloads, and also extract the article data and immediately queue the content for our processing through our standard ingestion pipeline that we had, the data collection service. So we need to implement webhook in such a way that it is taken care of all these situations that we just discussed. So yeah, and again, there is going to be only a few publishers who implements our webhooks, and then we can process their content through webhook service. But there will be someone who might not encourage this approach, and then they what we do, we have a fallback RSS approach and web scraper approach that we have. Like this, we can have a balanced approach handling all of the publishers. So this way, with the hybrid approach of webhook service and this priority based polling via RSS or the web scrapers, we make sure the content from all of the majority of the publishers will be there on our platform. The only primary concern here is basically whenever we try to build webhooks, we need constant coordination with publishers team, so that we let them know like this is the endpoint that you should add, and this is what you should integrate into your server's code and whatever and the stuff. That's the only concern that we see. Leaving aside this is the most adaptable solution to go ahead with to achieve this requirement, making sure that it the new articles gets populated into our feed within less than 30 minutes of the actual article publication. That's the 5.3 point. The next point is how do we handle media content, which is the thumbnail URL, the image that we showcase for each of the articles efficiently. So I think this is more of a straightforward point, because we already if you've been watching this video from beginning, there are already multiple places we'll always be talking about the media storage. So yeah, just the name and then better on the optimal way. So the name is we try to store this blob store directly in our database itself as binary data, and that is not at all recommended. You all know, I think if you're into this video you must be knowing that. So that affects significantly our database performance, and it makes our database slow, backups are enormous, and memory will always be occupied by our binary data of the images rather than actual structured data. So this is a big no. That is another thing. The other thing is we try to leverage the blob storages like S3 or GCP or Azure Blob Storage. We try to store in S3 and reference them their URLs in our database or columns, which we already have it in our design if you have observed in our above design. Now the problem here is just the latency that we have listed down. So global users who are not closer to the region where our bucket is located in, so they will receive, they will see high latency issues, and also more S3 egress cost is going to pile up on our side. So how do we avoid this? Is basically introduce a CloudFront CDN with multiple sizes. So this is straightforward to basically mitigate global users experiencing high latency whenever they are loading thumbnails from very far S3 regions. We can use a CDN, which is CloudFront CDN, to serve the thumbnails. We store thumbnails here in S3 and serve them through CDN to end users for global distributions. So we can generate multiple thumbnail sizes, can be like, for mobile one thumbnail size, for desktop one size, for laptops one more size, and so on, so that it gives good appeal for our website and for user experience as well. And based on the device and the screen density, CDN will pick up the right image and serve to the client. The challenge here is the one storage costs is going to increase a bit for multiple thumbnail variants, because we are now trying to store 3 versions for each thumbnail: mobile, desktop, and laptop. And to be honest, that's very negligible when compared to the performance gain that we are providing for the even for the distance users as well. So this is how the design is going to look like if we introduce this CDN here. And this approach, S3 plus CloudFront CDN, make sure that the media content to the even distance users will be very, very fast and meets the latency requirements that we have listed above. Okay, yep. And the next point is, how can we handle the traffic spikes during very peak hour? Let's say something every morning people try to stay up to date to the news, or if there's something election and there's something news about celebrity, or there's a World Cup or something like that. So that is the time when the traffic to our site will significantly spike. So this in our overall design, if you see here, the feed service, the application layer, let's assume like the single server can typically handle like 10,000 to maybe a 100,000 concurrent connections depending upon the response complexity and hardware. So one server will definitely won't cut it. So we need to horizontally scale this. We can do this with simple horizontal scaling and auto scaling groups. Since this feed service is stateless, we can easily scale it horizontally, and there's nothing much of a concern for us when it comes to feed service in the application layer. Going to this database layer where actual data is stored, if you see the read that is happening is mostly happening through the caching of from the Redis. So this is something because we have the CDC, which whenever there is an entry into this database, change data capture will trigger and update the cache and all. So whatever the user is trying to read is mostly trying to read from the Redis. So this is something that we need to consider. This layer is something we need to consider. How can we scale it up and make sure even during high peak traffic time it handles very smoothly? So that is the point here. The only thing that we need to worry about here is Redis scaling. So others, horizontal scaling of our application layer will be taken care, and database is something we don't have to worry about. It's just the writing that's happening, which is very less when compared to the millions of users than the thousands of publishers that we have. The Redis scaling, how we are going to do is we will try to add a read replicas of this Redis thing. Yep. Now each regional Redis master gets multiple read replicas to distribute the query load. Since let's say we only have 1k to 2k recent articles per region, each master can easily store all of the regional content without complex sharding. So the scaling challenge is purely about read throughput. So let's walk through the scaling math. So with the 10 million concurrent users during peak traffic, each Redis instance handles roughly around maybe let's say 100k requests per second. So we need to meet the 10 million, we need at least 100 more total Redis instances to handle the load. So realistically, we might not need this for many per region. Only some regions are more popular than others, so we can scale up and down accordingly per region. So this is not much of a concern. So how do we set this up is straightforward. So write operations like new articles, cache updates go to this master, which is the master that we have, and the read operations for feed request are load balanced across our new read replicas that we have on the screen using maybe round robin or least connections algorithms. This will be taken care by the Redis Sentinel, which manages the cluster. So if master fails, any of the read replica will take over of this place and gets promoted to master automatically. The replication lag, that is whatever gets written to master to read replicas, is typically under less than the latency that we have written down, which is 200 milliseconds. So it meets our requirements. That is not of a it's basically perfectly acceptable for news feeds where users will not notice such small delays. So this is how we try to scale this Redis, and once we have this Redis scaling integrated, this is how our design is going to look like. The cache now will look like this. Master will receive all our CDC, the change data capture writes to new articles into this, and this will eventually update our read replicas, and whatever the queries that are coming to the feed service will be hitting this read replicas, and then that will be provided to the client. Yeah, so to sum it up, this is how whole of our architecture is going to look like to handle all of this news aggregator service and to meet the requirements. There is one additional point maybe we can discuss. It's good to discuss as well. So here, how do we facilitate category based news feeds? We normally see sports category, technology category, politics, and other categories that we normally see, travel and other stuffs. So how can we facilitate that category based news feeds? Right now it's just the region based feeds that we are showcasing in our actual feeds to the users. So let's discuss that. The how can we achieve that is a simple. We do database query filtering with introducing new category column. So we try to add a new category column and we filter feeds by region plus category. Now in real time, maybe the query might look something like this. Region is something US or UK, and category will be something sports or technology, and query will be leveraging this region along with this category, and the composite index will look something like this. Now region, category, and publish stat. This is how we try to filter at the database query layer and return the results. So since we are trying to do at the database level, again there will be significant performance issue at scale for each category, especially during peak requests. So maybe assume like we have 25 categories and assume we have 10 regions, so it will be something like 250 different keys that we need to cache in our Redis, and it becomes really hard to invalidate and perform other operations in a cache. So this is something we cannot consider. And now to mitigate those issues, the other approaches, we try to pre-compute category feeds in Redis. So right now what we are doing, we are storing in Redis with the key like feed colon the region name. Now we'll maintain separate sorted sets with something like feed category name along with the region. So this way whenever user tries to query along with the category, I try to directly query this sorted set of that category and return to the users. So this is something introducing additional sorted sets for each of the category. So again the problem here is if we have more categories and let's say that 25 categories and 10 regions, so we are introducing additional 250 plus sorted sets per each region and multiply by 1 to 2k articles of each, so which is much of a higher Redis footprint. So it's going to occupy most of the memory, and also to invalidate and the performance issues when we're trying to do a cleanup articles in multiple feeds, it adds complexity, and under high publish rates this really hurts read latency. So this is something again maybe it's a overkill trying to maintain a separate sorted sets based on each category and region. And to really keep it simple, what we can do is we do in-memory filtering. So in-memory filtering is simple. We can include right now for of this feed and the region name, we are including just the article ID. So instead of just article ID, we'll try to keep all metadata of an article, something like this: ID, title, description, URL, category, region, publish stat. So now when we try to fetch based on region and we also get the category from the user, we just do in memory filtering of this category and only return the list of the articles matching that category, which is very simple and faster, and also a lot of memory saving when compared to the second approach. So this is how we can handle the category filtering, maintaining the same latency as we used to before. So this is one additional point we can discuss. So this is how we can design a news aggregator within the requirements that was given to us. Yep. And next, let's try to move on to something like BookMyShow or District app that we normally use to book tickets for an events or movies and other stuff. Now let's discuss about BookMyShow or District or Ticketmaster. We all know what are they. They are simple online platform that allows users to purchase tickets for movies, concerts, any other live environment shows. Okay, that's the application we use in our day-to-day life. So when it comes to a system of this kind, the simple requirements that hits us is basically these are the functional requirements. So users should be able to view the events on that platform, and then we can query for specific events from that date to specific date, and other query patterns that we can add. And then we should provide an option to users to book a tickets to specific movie event or whatever it is that they are looking for. And then like I would say these are like top 3 high features that you should be part of when we think of a system of this kind. And other things good to have is like look at the history of the booked events that I have made on that platform, and then other admin flows like not for the users but for admins to add an event, venue, and other related details. And let's say there is a very popular events for example, Coldplay and other artists performers who are very popular in that specific region. Then we need to have a feature of adding a dynamic pricing for that specific events based upon the demand for that event. Okay, so these are the simple functional requirements that we have. And talking about non-functional, these are the non-functional points. First is we should make sure that system prioritizes availability for searching and viewing events, because that should be the place for users to look for specific events and by searching it. And then the second important thing is there should be consistency for booking events, meaning we should not let users book this same ticket so that it leads to chaos, both of them turning up for the event for the same seat. So we should make sure that there's a consistency, no double booking. That's very important point when it comes to non-functional. And then how do we handle the scale and the traffic and make sure that our services are not degrading when it comes to performance. So that is handling a popular events. That's the second functional requirement. And the search results that the user expects should be very fast. Maybe latency, we have a threshold of less than 500 milliseconds. So whatever they're searching for, instantaneously we should be able to return the results. And and this is a read heavy system, meaning assuming 100 to 1 ratio of read write operations. So we need to make sure that how can we design a system such that it handles more requests than writes. So these are the strong foundation for this system design discussion: functional, non-functional, and we are clear what are the requirements that we should meet when we are designing this use case. All right, so once we have a clear idea of functional, non-functional, we will definitely get at least a high level overview of the core entities that are involved to get this functionality working. So thinking of core entities, these are the things that we can think of. Core entities event. So basically this entity stores information about an event. Examples like date, description, name, type, and performer or team involved. So kind of like it acts as a central point of information for every unique event that's going to happen on our platform. And the second entity is user, which is a straightforward. It just represents the individual interacting with our system. So I think it's you or me, whoever is interacting with the platform. And the other entity we can think of is performer. So it usually represents a band or an artist, an individual. The key attributes can be like is performer's name, a brief description about him or a band, and maybe an additional links to their works or references or profiles. This entity keeps track of all that info. And then the venue. So is it which stadium it is, which location. This is actual the place where we'll try to store the physical location where that event is going to be held. And kind of attributes we can think of is address, the capacity, and what is the seat map structure of that specific venue, and all that seating arrangements, everything, so that we can plan from this entity. And of course the next entity is ticket. It is self-explanatory. It contains information related to that individual ticket. So basically for every seat, whenever event is added into our platform, for that venue, for every seat we need to automatically create a ticket entry in tickets table as well. So that is for this. So it ideally has like associated event ID, seat details like which section, which row, and seat number, and pricing, and what is the status. Is it available, is it booked, is it in progress, and all that stuff. Is it reserved, and all those things. And here this is the booking. So basically ticketing, purchasing, tracking is what we'll be maintaining in this table. It includes maybe user ID, a list of ticket IDs that the user has bought, and what was the total price for all the tickets that he bought, and booking status, is it confirmed or in progress, and all those things. So these are the core entities that we need for this, or at least we can think of when we saw the functional and non-functional requirements for this use case. So more specific individual attributes and all we'll discuss as we go deeper into the design discussion. Okay, fine. So that's the thing. And next the step is obviously the services or the API that we need to expose so that we can do specific operations on our servers. The first API is a simple get in endpoint which gives the details of a specific events. So this takes in event ID, and in return it gives us the details of the event. So can be something like union query of event table, venue details, and performer, and a list of the tickets for that event. So this is a simple endpoint. And the other endpoint that we can think of is search events. So this as soon as we user enters our application, he tries to search for specific event or performer and other stuff. So we need to take in the keyword and the start date, end date, along with that the page size and the page number, which we will try to set it from our end. So this is how it is going to look like, the query params, and then it's going to give us the list of the event objects thing, and we use that to showcase in our home page. So that's the simple get endpoint to search. Then the other one is the main thing, providing an option for user to book a ticket. So here simple post endpoint, we take in the event ID for which user is trying to book a tickets. And here after everything is successful, we return the ticket IDs, a list of strings, and then payment details from this endpoint. So these are the simple endpoints. So even we can maybe delve or deeper into it later, and split this into two separate endpoints, one for reserving a ticket and one for confirming a payment or a purchase, which is a good point, because always the payment is something we'll be relying on external dependencies like Stripe, Polar, or the other gateways which are available. So these are a simple API or system design that we can think of, the system interfaces that we can think of. Fine. Now that we are clear of what the APIs that we are going to create, the core entities and all, let's try to get into one functional requirement at a time. So that's the deep high level design discussion. Okay, so here the high level design discussion. First point is users should be able to view events. So this is the simple the workflow. So even if you see the diagram that we have, it should be self-explanatory. So what happens is basically when user tries to navigate to our website, so that is a client, let's say something like event planning, eventbooking.com and slash event and event id, they will go through this API gateway. So this is a standard way for us to handle any logging, routing, rate limiting and authentication for specific client and all that stuff, and this goes through that. And we try to take in the event ID and hit our event service. So this queries our database, ideally maybe let's say Postgres DB, and it queries this DB and retrieves the details related to that event, venue and performer. So like I said, maybe I just added briefly a few attributes: the ID, the venue ID, the linking to this venue table, and performer ID, so linking to this performer table, the list of the tickets that are available or other details from the tickets table, name of the event and description and others, created at, updated at, the standard the columns that we need we can just add in. But this is the high level the flow, how it's going to look like when user wants to view events. Okay, so it's simple. The flow is here this client is something like website or app that we have provided to the end users, and this is the entry point to any of our microservices. Maybe we right now we are starting with one microservice. Here in our case is the event service. So it's basically the API gateway. It's mainly responsible for routing to different microservices since we have one. So you will see that yeah, and then we have the database which stores tables for events, performers and venues. Yeah, I think this should be enough. So a client makes a GET request with an event ID. The API gateway then forwards to our events service. The event service then queries the database for the event venue, and then it returns to our client. So this is the simple flow of users trying to view events. And now the second point in our functional is user should be able to search for events. Okay, how this is going to look like? They need to find a way so that they can search for the event that they want to look for, and then retrieve the results and showcase it in our UI. Let's talk about basic simple flow. So here I have added additional microservice, which is a search service. So I can just right away talk about the flow. Client makes a GET request to our API gateway with search params, whatever we discussed in our endpoint here. Okay, keyword, start date, end date, page size and all. I have not added here, that's fine. Fine. And our API gateway, it accepts the request, and it forwards to our search service. This search service will query our database for events matching with the search filter params that user has given, and then he returns to the client. So this is a simple flow of search service. So basically the search service can be like simple search query with the wild card matching like and based on name and description, and then return the results to the user. So just trying to understand the basic flow of our system which meets our functional requirements. We will talk about in-depth discussion in our deep dives, and that's the second point in our requirements. And the third thing is user should be able to book tickets to events. Okay, so now the main thing here we need to worry about is we need to make sure that 2 or more users doesn't end up paying for the same ticket. That is the important criteria that we need to handle here. To handle that, we should be very careful on the choice of the database that we'll be making. So ideally take the one which suppose has it properties, and so this will make sure that only one user can book a ticket at a time. Maybe something here like, in our case PostgreSDB is what I'll be trying to look for, and we need to make sure that we do proper isolation levels and row level locking or optimistic concurrency control to fully prevent double bookings. I'll talk about that, what is that contention and how we are going to handle all that thing. But the flow, it's something it's going to look like. The additional microservices added behind this API gateway or load balancer first, and API gateway. I have not added load balancer, but that's fine. Just visualize it. So we have here the new microservice booking, and then interacting with the external payment gateway Stripe or Polar, and then I added the additional tables, so the ticket related and booking related. So ticket will have ID, event ID to which it is linked to, the seat, price and status, user ID, and then the booking ID. And booking is ID, user ID and tickets and all. Okay, fine. So the flow, it's simple and straightforward. So when a user goes to book a ticket, so here it comes through API gateway for all authentication or logging, rate limiting and all handling stuff. When user tries to book a ticket, we direct the user to booking page where they can provide their payment details and confirm the booking. Upon confirmation, a post request is basically a payment. He goes through this Stripe or Polar. Upon confirmation, a post request is sent to the bookings with the selected ticket IDs. So then this booking server checks the availability of selected tickets and updates the status inside our ticket table to booked, and then it will create a new booking record in bookings table. If the transaction is successful, the booking server, so if everything went fine, then it returns a response to the client. Otherwise, if it failed, we will roll back in our transaction, and then another user can book the same ticket in the meantime. That's the simple flow. So booking, and we do check the availability of that and get the ticket IDs, and then process through payment gateway, and if it's successful, do the booking entry, and then return either success or failure depending upon these subsequent actions. So there is an issues in the design that we have here. For example, users can get to the booking page, type in their payment details, and then find out that ticket that they wanted is no longer available, and this would really frustrate the user. And we are going to discuss how we are going to think through this and avoid this, and make sure we'll provide good user experience on our platform in our deep dives. Yeah, this is like simple rough implementation to meet our basic functionality which I have laid down above. So like I said, I'm just focusing on three high priority points. The other points is something headache ones which we can discuss later or avoid completely. That's fine. Now let's get into deep dives. So deep dives is mainly focusing on our how can we make sure whatever we have listed down in our non-functional, we are meeting that, and how are we making sure that we are hitting that criteria. So going down to this deep dives, first thing is how do we improve the booking experience by reserving tickets. So this is one of the important point that we should meet. So currently what's the situation is, right now whoever fills faster the payment details in our booking section, those users get those tickets first. It's not the user who has hit the payment page first. Even 10th user has hit the payment page and he filled it faster, then we are providing a way for him to book a ticket, not for the first user who's been there on payment page. So that is something we should address this, because no user really wanted to spend maybe 5 or 10 minutes filling out everything, and just later they find out that the ticket they were looking for is no longer available, because we provided an option for other user to book a ticket. So if you really observe this thing, maybe whenever you're doing ticket booking or other stuff, the common technique that they usually use is, maybe it applies to anything. It can be, airline tickets, event tickets, hotels, or whatever you're doing this stuff. They try to show a timer counting down for us, just saying that we have, let's say, 10 minutes or 20 minutes to book this ticket or no. So basically that's the way for us to lock the ticket for us in that time span. If we do that in that time, then that ticket is ours, or else it will be released to for other users to book it. So that's one common technique. It's implemented to make sure that user gets the ticket that he is currently on. Okay, so these are the points now we should address. So first is, ensure that ticket is locked for user while checking out. So it should be for the user who has been on the page first. So it's not for the user who is quicker. Okay, so that, how are we going to make sure? And then if user is on checkout page and user abandons checkout process, then the ticket should be immediately released and should be available for other users who are looking to book the same ticket. So that's one thing, how are we going to make sure? And if everything is went well and user completes the checkout and it's a successful flow, then we should accordingly mark the ticket as sold in our ticket table, and also had an entry in our booking table. So these are the 3 points that we try to address this. So how are we going to make sure these things can be taken care of? So let's brainstorm and discuss multiple approaches. So first thing is the pessimist locking. So in this basically what is this approach, the pessimistic locking? The database is directly utilized, to lock a specific ticket row, or ensuring exclusive access to the first user trying to book the ticket. How it is typically done in base, if it's in a SQL thing, for example Postgres, we just use a select for update statement in PostgreSQL, which locks the selected row or selected ticket row as part of the database transaction. The lock on that row is typically maintained until the transaction is either committed or rolled back, meaning till that user completes that process, that is logged and is not available for other users. So this is how we make sure that it is blocked for that user who is first to that specific ticket payment page, and makes this it's good to make sure that user can process the ticket booking. Only one user can process the ticket booking at a time. Okay, now when it comes to locking, what are the cases that we need to consider? So here, if user finalize the purchase and transaction is committed, then database lock is released, and ideally then we should set the status of that ticket to be booked. Okay, and the other not successful scenario, if users takes too long or abandons the purchase, then we need to rely on something additional application related logic, something like session timeouts to release that lock for that ticket. Else there will be very high risk of tickets that is being locked indefinitely. So this is something very not a good way for us to address the points that we discussed. So what are the challenges if we try to choose this? Is basically we will make sure if we take this approach, the transactions are open for a long time. Example, let's say 10 minutes lock duration, and which is ideally not good, the waiting time for the users. So this lock, again, the timeouts need to be handled at application level, adding additional complexity in our logic and all that things, and it does not really scale well. It really increases wait times for other users and potential performance bottlenecks if there is any network issues, and it would really mess up our ticket locking system. So that's why this approach is something not considered. It's not ideal for us to consider when we are designing a system of this kind. Let's talk about the second thing, which is a status and expiration time with cron job. So here the better solution is to lock the ticket by adding a status field and expiration time on the ticket table. What does this mean? Now the ticket can be in three status. One is it available, and is it reserved, or is it booked? So this allows us to track status of each ticket and automatically release the lock once the expiration time is reached. So what happens ideally is when let's say a user is on our platform, he selects a ticket, then the status that we should immediately change from available to the reserved. So that's what we should make at the first step itself, and then the current timestamp is recorded. Once it is entered into our table, then the flow, what is the flow that we can think of? Let's say that user finalizes purchased, and it's good. Then we just update the status, change to booked, and then we release the lock that ticket is booked. Fine. In the other cases, if user delays or takes too long to make the purchase, the status should be changed back to available if the expiration time is reached, and then we should just try to release the lock on that ticket. So here the tricky part is how are we going to handle expiration time? That is something maybe we need to rely here on the cron job, which maybe periodically queries for rows with the reserved status column where the time elapsed exceeds the log duration, and then set them back to the available. So here we are heavily relying on the cron job. So this is much better, but still there will be a lag between the elapsed time and the time the row is changed. So it's not ideal for very, very popular events. That is something, maybe a trade-off here if you choose this approach when compared to the pessimistic locking. So the challenges here is like I specified, there's still a gap in unlocking a specific ticket. It's not available to the users as soon as someone abandons it and all. So the user is missing the ticket that he wants to book, and here we are heavily relying on cron job to reset the status of a tickets or release the tickets for the user. So if this fails, it's going to mess up our whole system. The cron job is something that we don't want to take a risk on. So that these are the challenges here if we choose this status and expiration time with this cron job. Now the other way we can think of is this is just a super add-on to our status and expiration time with cron, that is implicit status with status and expiration time. So what this method says is basically just a better way of handling the second approach or the cron based solution. Here now we try to check if the current ticket is either available or reserved but expired. So the condition check in our the database transaction is something it's going to look like. We check if current ticket status is equals to available, or status is equals to reserved, but it should be expired. So that now we are trying to pull the tickets which are expired as soon as they are updated in our DB. So there's we are trying to mitigate the gap time that we saw in our second approach. So then we update that ticket to reserved with expiration time now adding plus 10 minutes, so that the current user gets even the reserved one but expired one. So there is no gap of providing the reserved tickets to the users. So this way it ensures that since we are handling it in a transaction, only one user will be able to reserve or book ticket, and no wait time for users for expired reservations. So this is something we kind of the improvement in our database transaction query. So since now we are adding a filters and on the extra status and all, the read operations are going to be much slower because of additional filters that we have. So that's something we should be willing to take a trade-off on. And then another thing is even though the specific tickets or something it is expired, we are still having this legible data in our database, which should not be there. Ideally it should be swept out, and again here something like that should be handled using our periodic cron job, which takes care. So these are like kind of the challenges, but it's a better approach if we when compared to the first and second approach which we just discussed. That's the thing. The other ultimate the approach that we can completely rely on is using a distributed lock with the time to leave. Ideally here it is at Redis. So what this approach is basically, we all know Redis is a simple in-memory data store that supports distributed logs and is well suited for this high concurrency environment that we are trying to discuss. So what happens ideally, the flow. When user selects a ticket, I try to acquire a log in Redis using a unique identifier, something like ticket ID as a key and value as the user ID, with the predefined TTL, something like, let's say 10 minutes. So this TTL, we know that it acts as an automatic expiration time for the log, so we don't have to worry about it releasing us manually. And let's talk about the ideal flow. If user completes the purchase, then the ticket status in the database should be updated to booked this in DB, and manually we can remove the log from Redis by application code. Just say redis.delete and use this ticket ID and then remove that. If it is not user has not purchased, and anyhow we are handling the TTL, so if TTL expires, Redis automatically releases the log and it will be available for the users to make a booking or purchase it, whatever it is. Here the downside is something like if somehow if Redis goes down, then we have here something like single point of failure. So that's something I think since Redis is reliable, and I think the point here to discuss on is it's negligible. And one more thing, here still there's a possibility if you users might get an error if again someone is trying to fill out their payment details and others is other user is has beaten them, then he gets the ticket first. But the chances of occurring this is very rare, and I would still argue that it's a better outcome than having all tickets appear unavailable, as it would be the case with our cron job, which we discussed in our previous solution. So I would stick for this, though these are the points, but I'm willing to argue on this point. So once we finalize the design discussion to make sure that only one user gets a ticket, the same ticket, so this is what the design is going to look like after that. So here in our booking service we have now the distributor lock, a ticket lock using our Redis, and here the key and value ideally would look something like that. So why the user ID? So when we are trying to manually remove it from, make sure that it's the same user that we try to lock for as book their purchase. So that is very important to have the value as user ID, and the TTL it's just 10 minutes, and everything rest it's going to be the same. So this is the new addition to our system design, and that's how we are going to solve the first point. And now let's talk about the second point. Second point is we need to design our system in such a way that it handles tens of millions of concurrent requests during very popular events. So how are we going to make sure that it is taken care? So this is again the design is here. Ideally we know that this is very read heavy system, so the read heavy pattern is something we are aware of. When it comes to read heavy systems, we always think about something like caching, load balancing, and horizontal scaling. So here, though I have not added it as part of our design, but maybe I can just walk you through here. So if you see here, there is additional the Redis to cache details related to event. So we might cache details something like which have very high read rates and low update frequency, something like event details. Event details, they are rarely changed, so that I can just maintain with a key something like event ID and all of the details of the event object, so that it reduces the load on our actual DB queries and all. And the caching strategy, of course, we can go with the read through cache strategy. First we'll look for the values in the cache. If it's not present, hit the DB and carry it from there and put it in our Redis cache and then showcase it to the user. So that's one thing, the strategy that we can follow on to handle that. And the invalidation and consistency, so somehow here we need to balance here with the database triggers whenever there is some writes happening to events table to notify our cache system, and accordingly we'll just update our cache, and also maybe have an ideal time to leave so that we doesn't always have a stale data in our Redis cache. So this is something, and we need to be very careful. The details can be very flexible on static data, like venue info, that's never going to change. So it should be something like can be there for longer time in our cache, that's never going to be stale. So that's how something we can handle caching in our event service and make sure that we are trying to hit this target of handling concurrent request of many users. The other thing is, since if you observe the event service is something very stateless, so since it is stateless, we have a complete free hand on our end to add more and more instances, and accordingly use round robin or least connections load balancing algorithms to distribute the traffic to respective servers. So load balancing and horizontal scaling go hand in hand, and this is how we can just handle the scale that we are talking about. It's a simple discussion, so there's nothing much to add to our design. It's a standard discussion when we try to talk about building a system designs. Depends again the scale of the user base that specific application has. And again, for any approach that we choose, there'll always be downside. Basically the percentage of downside is very significantly negligible when compared to the benefits that we are getting. So here the challenges is something, the maintaining consistency between our cache and DB system is something we need to really worry about. Sometimes it might mess it up, that's one thing. And there is, now we are talking about adding more instances and everything, so there'll be a little bit of operational overhead for managing more service instances. That's one trade-off we are willing to bet on, and that's something we're cool with. And this is how we'll try to address this point of handling multiple concurrent requests for popular events. And let's talk about the second the third deep dive point. Now how do we ensure a good user experience even during very high demands events with millions of users simultaneously booking tickets. So here, what is the important point that we should try to take care is, let's say now I have our application, obviously for specific menu, it's all going to be a seat map, like which seats are booked, which seats are available, the prices and all stuff, depending on the taste and the design of the specific platform. So how do we make sure that the seat map that we're trying to show for that specific event is always up to date and it's never stale, and so that users never get frustrated when when they try to hit a ticket and then only to realize that ticket has been booked. So how do we make sure we have real-time data onto our platform? So this is a very good discussion to have on. One thing we can think of is when it comes to real-time status updates or seat updates, straight away the thing that comes to our mind is server-sent events. So that's first approach we can think of. So here it is simple server-sent events for real-time seat updates. So we try to push updates to the client in real time. So this really allows us to update the seat map as soon as someone has booked a ticket. So basically, if some entries the status of our column in our ticket is changed, then we know someone has booked. Then we try to let the other clients know that this ticket has been booked, and we push it from our server side, and that seat map will be updated, and users can choose the tickets accordingly. So that's one way of like unidirectional communication. A channel from our server to the client without asking the user to keep refreshing the page. So this is one good approach of providing real-time updates. But still this doesn't really scale well for very popular events, meaning the users are so frustrated that they are looking for the tickets that they want to book, but the booking is they're very fast filling. So how do we take care? So there is a concept called a virtual waiting queue for extremely popular events, and this is something very thought through approach. So what happens is here is for extremely popular events, we can implement something like admin enabled virtual waiting queue system to manage user access during this times of very exceptionally high demand for that specific event. So what happens, ideally the flow looks like this. Whenever user tries to request to view our booking page, we, instead of directly allowing the user, we will try to place them in a virtual queue, and then we try establish a WebSocket connection with that the client the user is trying to browse our application, and we add the user to the queue using that unique WebSocket connection. And here, based on certain criteria, like I said, if there is some new ticket has been booked, then we know one user has left our platform, then we can let another user into our platform. So based on certain criteria, something like tickets booked or status is changed, we will try to dequeue that user, FIFO, first in first out, whoever the users that we added to our queue from front of our queue, and then we'll try to notify the user via WebSocket connection we just established in our first step, and then now they can will be notified and they can proceed to purchase tickets. So that's the second step of and at the same time we should make sure that we update a DB to reflect that this user now is allowed to view the purchasing page or booking page or whatever it is. So this is something very important approach to make sure that we doesn't overwhelm our servers, and make sure that even traffic is smooth, or the performance is not degrading and all. Yeah, I think this is very ideal approach, but the only thing is when we try anticipating more and more traffic, but people not booking the tickets, then again that gives a more long wait times for the users which are in queue. So that can lead to users frustrations, and they can choose not to book the tickets and or everything, though that can be still mitigated given best user experience, something like you are at this position in this queue, and the estimated time for you to go and book the ticket is something like that. We can showcase push real-time updates like in 10 minutes you can book, or you are in this fifth position or something like that, is something that we can provide. So if we consider this approach, so this is how it's going to look like, the design. Here in after API gateway, when user is trying to access booking page or booking service related stuff, we had in here virtual waiting queue, and whatever we just discussed 3 points, and that logic will be handled everything inside this before this booking service, either in API gateway and the workers queue, that specific section. Okay, so this is a point to make sure that sitemap is always up to date on our platform. And now let's talk about the other point in our non-functional requirement. If you remember, we have a strict boundary of meeting the search query latency to be less than 500 milliseconds. So the search result should be instantaneous, and users doesn't have to wait and doesn't have to get frustrated when they're trying to request the details for specific event or whatever stuff. So how are we going to make sure that the query results are always faster? It should not be something like, normally we write select star from events where name like wildcard matching and description or something like that. That does give the results, but it definitely beats the here the objective of us is it's not going to be less than 500 milliseconds. It's going to take time if more events are added into our table, or even if events are growing exponentially. So how are we going to take that? So let's all again brainstorm that approaches. The first approach is, of course, when it comes to searching and trying to improve the read query times, we always think of the indexing and trying to optimize the SQL query. So here we know that it's going to be more on like event name, event date, performer name, or venue location and all. So we can just try to create an indexes and columns like which we already know something that the user is going to query mostly upon. We'll just try to add an index and then we'll try to optimize queries to use like limiting and then unioning multiple queries so that we can return the results way faster. But the downside is, since we are adding more and more indexes and new columns, it's going to really make down our writes very slower, because as we do a new entry, the index needs to be updated. And also the standard indexes are very less effective for partial text searches. Like let's say if your full name is first and last, and if you just search for first, it's never going to work. It's something like full text search is something it's not handled, and that's what user usually expect to get the results for in any platform. So this is something that we cannot go with. The other approach is adding full text indexes abilities in DB. For example, in Postgres, you can add full text search capabilities, which really uses Lucene behind the scenes as a search engine, and it really helps us to avoid full table scans, and then uses even for partial text match, and it does improve upon here the downside that we discussed in our first approach. But this full text indexes really require additional storage spaces, and then it will be an additional overhead to maintain in our same database, Postgres database, and also it is not going to handle the typos in the search queries, which is really important. That's something we need to handle, and that's most expected assumption that user is going to do a mistake on. So this also beats the purpose. And the other, of course, when it comes to searching, we every time we think of is something full text search engine like Elasticsearch. So this is very standard engine that everybody tries to use when it comes to searching at a scale, because this really excels in full text search and complex query execution, and it really handles, it's very good and designed to handle high volume traffic efficiency. So at its core, it uses inverted index, which is a key feature which really makes it as a highly efficient choice for such operations. So this basically allows to quickly locate and retrieve data by mapping each unique word to specific records or documents. So this is a mode of this Elasticsearch, and that's why we usually prefer when it comes to this. And also here, if we choose this, we need to have a careful logic of change data capture, of syncing data between our Postgres database, which is a main storage layer, to our Elasticsearch, so that they are always in sync. So that is something we need to carefully handle. And also here, very important thing, we can enable fuzzy search, which really helps us to handle typo issues. So even if you change some one or two letters in a word when you're trying to search for it, just gives you result for the one that you're really looking for. And it's not more of an challenges, but it's something that we need to be careful and cautious when you are trying to take this. So that is change data capture can be very complex when you're trying to sync data between Postgres and Elasticsearch, and that something needs to be taken care. And then of course there is going to be an operational overhead, because now we need to maintain extra Elasticsearch cluster. So that's something a challenge for us. So now if we try to consider this Elasticsearch for a full text search, this is how it's going to look like. So here we have a search service. Right now we will hit our Elasticsearch, which is our search infra, and we'll try to add an index on something which we know they are going to hit most frequently on: name, description, venue, performer, date, and all. If you think there is going to be another key or something that's going to hit the most query on, you can just add an index on that. And here the CDC of trying to sync up the data from this database to our Elasticsearch and make sure that they are both are in sync. Okay, so this is how the design is going to look like when we try to introduce our Elasticsearch. So that's one point. And then now let's say that I am trying to hit the search query for the same query again and again. So instead of adding extra overhead on our search infrastructure for the same query, is there a way that we can speed up repeated search queries? Is this something? How can we do that? So when it comes to repeated search queries, the first thing we always think about is adding caching strategies. So that's implementing caching strategies. Something like straightforward, I can maintain a values in Redis, something like key. Let's say I try to search for Coldplay and the start date and end date and other query params for this key, and I got this result from our search info, something like this. So I'll try to store this in our Redis with the TTL of, let's say, 24 hours or maybe 2 days or whatever the time that we wanted to. And whenever again user tries to hit the same query to our search service, so search service will be talking to Redis, and if it is hit in the cache, then I'll just showcase that to the user instead of hitting again my Elasticsearch infrastructure and all. So this way I try to avoid repetitive queries to my Elasticsearch. But the downside here is the cache invalidation can be really challenging, because when should we update if there is any updates happen in our DB, because we have a CDC mechanism of syncing between Postgres and the Elasticsearch, right? So if something is really updated, so what should be the TTL ideally? How are we going to optimize? Something that we need to think upon that, and that's one of a thing that we need to implement and take care when we are considering this approach. And also again, if there is a frequent cache misses, it's again defeating the purpose of reducing the load on our infra. So this is something not good to in this scenario to consider to speed up repetitive search queries. And second approach is basically Elasticsearch default. It comes with node level query caching. So basically it has a built-in caching capabilities that really can be used to leverage to store frequently search queries. Then this if the caching we have, this definitely is going to help us reduce processing load on search engine itself. So the node query caching that we have is basically least recently used cache, which is shared by all the shards on node. So it helps us really caching results of the queries and all. And additionally, the shard level request cache is basically used for caching search responses consisting of complex aggregations related things. So this can also be used for adaptive caching strategies, where the system will try to give us the most frequently executed queries at a faster time than hitting the core engine to get the results that we need. The other also thing that we can consider is edge caching technique. So edge caching is basically maybe we can use AWS CloudFront CDNs to cache search results geographically which are very closer to the user, reducing latency and improving response times. But again, this is very catchy point here. So this really makes sense if the results are same for all the users. So basically we are not providing personalized search results, then only then this is considered, or else not. Though it's a bit expensive though when we go for this. So only if needed we can go for this, or else we can just add in the caching on our Elasticsearch, and that should do for this use case. And again, the challenge here is going to be the complex synchronization mechanism needs to be handled between the cache and the real-time updates that's going to be happening under synchronized between Postgres and Elasticsearch, and that needs to be taken care. And also here we'll have more operational overhead if we introduce AWS CloudFront and other things. Okay, so finally the design after considering this approach is going to look like this. A simple addition. So we are just trying to consider here the node query caching is enabled on our Elasticsearch infra. So this is the thing how our design is going to look like, and the ultimate end design is what this is going to be. So the client API gateway handling all routing, rate limiting, authentication, and then we have here for our use case 3 core services: search service, event service, and booking. And we have here a virtual waiting queue, and then splitting of reserving and confirming the payments. And the flow, this is how it's going to look like. So when we think of a system to design of a kind like a BookMyShow, District, or a simple online booking platform, this is something at least we should know. Maybe the things that we covered is just 1% of actually the systems that they exist, but this the intent is just to give us a rough idea of how our flow should be like when we are put in a position to talk about systems like this. And yeah, that's it. And let's talk about the other use case in the next one. Okay, now let's discuss about how can we design a simple distributed job scheduler. So at a high level, we all know what is job scheduler. It's basically a program that automatically helps us to schedule and execute jobs at specified times or intervals, kind of which was introduced to automate repetitive tasks, run scheduled maintenance, or execute batch processes and other stuffs. So that's what the job scheduler is about, at least a brief definition of it. Now let's straight away jump to the requirements that our system should meet. Before even that, I just want to introduce a simple analogy, or not analogy, just terms that I want to. So the two key terms is a task and job. So task is basically we will try to use that as an abstract layer, kind of abstract concept of work that needs to be done. For example, let's say that we need to send welcome email, then that would be in a task. So they are like reusable and can be executed multiple times by different jobs. So here the another term is job. So job is actually an instance of a task. So that is where actually the task will be executed with some, let's say that if the task is like sending and welcoming email, then job would be like send a welcome email to abc@gmail.com at let's say 10 a.m. Wednesday morning or something like that. So that is what job is about. So task and job. Now yeah, let's discuss about our main the primary requirements. So primary requirements, first thing that we should able to meet is our system should help user to create or schedule a job. So it can be immediate run, or it can be a future run, or it can be a recurring. So these three are the things that we need to facilitate using our system. Then another requirement that we should meet is once the user creates a job, they should be able to monitor the status of the jobs, whether is it successful, or is it in queue, or is it, is it in retrying mode, or is it in failed mode, or whatever. They just need to know the status of the job. So in ensuring that whatever the job that they were trying to execute, they will be very clear if it is delivered or not. Then other option requirement, maybe it can be pushed to out of scope or just good to have. You should provide an option for user to cancel or reschedule the jobs that they have created or scheduled. And this dependencies, so they should be able to see the dependencies of the flow of the job that was executed and all, kind of like directed cyclic graphs of the series of the steps that is executed in a job. Maybe the last 2 points we might not discuss, but it's a good to have. And yeah, that good to have. So that's the functional and non-functional. So the first thing is we should give high priority for availability when than to consistency. Let's say that I created one job and someone else immediately tries to refresh the dashboard of that status page or whatever the jobs it is, and if he's not able to see that immediately, I don't think that's going to cause a bigger issue for the users that it is going to. So my importance is like whatever the job that they have created, we should be able to make sure that it's executing the job. That is like our systems are up so that it picks up the job and completes that. Then the consistency, like this I think trade-off is that I'm not much worried about immediate showing of that job is created or not in the list of dashboard for other users. So that's one non-functional requirement. Then other non-functional is we should have a system such that be able to execute jobs within 2 seconds of their scheduled time. So that's the one of the core non-functional requirement. And another thing is the scale at which we need to handle is assuming we have a traffic rate of at least 10k jobs being created, and or something like 10k jobs needs to be executed per second. That needs to be handled. And whatever the job is going through execution phase, we should make sure that at least once it is getting executed. So that those are like minimal non-functional requirements that we should meet. So now we are clear of the functional and non-functional. These are the functional and non-functional points. Let's identify the core entities by looking at this. Like I already specified, first thing is a task, and another is a job, and then the schedule, because users need to be able to schedule this. User need to be able to schedule this, and then we of course need a user entity. So those are like core entities that we have. So core entities, first is task. Like I said, it just represents a task that needs to be executed, and the job, it is an actual instance of this task which needs to be executed like with at a given time with given set of params and all that stuff is this job entity. And the schedule is just the straightforward maybe it can be a cron expression or it can be date depending upon the job that needs to be executed. So that that is this entity. And user, it's a simple straight away represents the who user who schedules jobs and views the status of the jobs. So these are the core entities that are involved in this system design discussion that we are doing. Okay, so once we are clear with the core entities, so looking at the functional requirements, since we are targeting the first two, creating or scheduling a job and monitoring the status of the jobs, so each functional requirements will ideally need a separate API or system interface. So system interface is this. So first thing is we should be able to create a job. So it might be something simple post endpoint with a slash jobs. So there we need to like pass in the body the task ID. It can be simple like send welcome email or prepare daily report or whatever it is. And then the schedule, the cron expression is something we might expect this thing, and parameters to whom we should send this, and then subject welcome to vagera, whatever the message or subject that you want to add. So I'm just stating this as a rough body for the post jobs. We will see in depth what can be hit as we go deep dive. And the second endpoint is querying the status of jobs. So user should be able to query the list of the jobs and see its status. It can be simple query param, like based on user ID and the status, and start time and end time is something what they can pass in as a query param, and then we return simple list of job with something like job ID, user ID, status, and other metadata that we can provide to users, so that can be useful for them. So these are the simple two endpoints that we need to worry about when we are designing this system. Right, now it's clear. Now let's just step back and then clear it for ourselves. What is the ideal data flow, rough data flow of this system that we are trying to design? So looking at this, I have here a rough data flow. First is, user tries to schedule job by providing the task that needs to be executed, like task ID and schedule, is it a date, cron, and other params, like if that task needs some params and all. So that's the first step user tries to configure in the systems. So once that is sent or hit our API, the job whatever we have received from user, we will try to process in database. It can be anything, DynamoDB, Postgres, or whatever the database that you're comfortable in. So because this is simple as it, whatever standard, it can be handled by any modern database. And once that is persisted, then some worker or who can execute task, it should be picked up by that worker. So job needs to be picked up by worker and executed at a scheduled time based on whatever the param that user has sent to us. And also we need to check if a job failed or success. If failed, we need to retry, maybe using exponential backup and other strategies, so that we at least give 2 to 3 attempts of executing the task. So that is the thing. And once that is executed, we try to again update the status of the job back into our database. So this is the ideal data flow of the system that we are trying to design. So now that we are clear of rough data flow of our design, let's try to discuss with high level discussion, starting with each of our point as we mentioned in our functional requirements. The first functional requirement was we should be able to user should be able to create a schedule a job. So it can be immediate one, future, or reoccurring. What happens is, ideally, so assume this is the client. So here he tries to make a request to our schedule service. So schedule service can be something like /jobs, which I just showcased above, endpoint, where he tries to pass in task ID, which task to run, schedule when to run it, parameters, what input the task needs and all, that he will pass it to this schedule service. And then we try to store this whatever the details that we received into our job store. So kind of a database. It can be DynamoDB, Postgres, or any modern database should do. So now we have a persistent record of all jobs, and we can record jobs even if our system crashes, and we can track through status through its life cycle. So when it comes to database, that we store it in database, the once we have stored into database, now there should be a worker that needs to pull that the jobs that we have stored in our database. It can be simple, let's say maybe I'm running a cron job expression in this worker, which pulls like every 2 minutes or so, whatever it is, and fetches the jobs with a status pending. So here the execution status that we have pending. So here I think the important thing, I'll come back this worker pulling from this database. The important thing is why the structure we have two tables, jobs and executions. Why not store it in a single table? So let's say that I have only jobs table, something like job ID, so some ID, user ID, and tasks, and I have other param, like let's say scheduled at the time, and parameters like that it needs something like to, subject, and status. Maybe it can be pending when we are initially pushing. So this really works fine for one-time jobs. but it really breaks down when, let's say, if it is recurring schedules that needs to run some, let's say, every morning at 10 a.m. We need some task to be executed. So how do we efficiently find like which jobs to run in the next few minutes? We need to evaluate every single cron expression in our database, which is clearly not scalable, right? So now it really throws us inside that we need to separate the definition of a job from its execution instances. So it's simple, like let's just think of a calendar analogy. Let's say we have an event that repeats every Monday morning and all. So like we see in our calendar application, we see individual instances of that event on every Monday. So same way, so execution is just an instance of a job, every instance of a job. So it's better to separate into two tables. It's a job and the execution is each instance of a job. So that's why we split now, and this has a schedule. So here it can have params like, type, is it a cron or a date, and expression. If it's a cron, we'll have like, every day at 10 a.m. for cron, or if it's a date, we'll have a specified date, like that. Now our execution table will help us to track each individual time a job should run. Here the time bucket, which can be partition key if we are preferring DynamoDB, and inside this it can be job ID as a partition key for a quick lookup by job ID. So, and yeah, that way these two tables helps us maintain in a better way. So yeah, this, now we have two separate tables. When now let's come to worker. So when worker node is ready to execute jobs, it simply queries our database. So like I said, it can be a cron expression, cron job. Maybe it just tries to pull the entries of a database which is having execution time maybe in next few minutes, and status is pending. Only that it should pick up from store, and then process the whatever the task that it is. So yeah, this way user can try to complete a simple flow of creating or scheduling a job. So this really helps us to achieve the simple overall functionality for application. Now let's go to the second point discussion. Second is, you should be able to monitor the status of the jobs. So this is a simple, straightforward, like we discussed in the above. When the job is executed, so let's say the worker is executed, then we try to update the status in our main database in the execution status to maybe completed or failed or in progress or retrying. So based upon the condition what happened in our worker nodes and all that stuff. So this is a simple thing. But here the problem is, now with the current design, querying the jobs by user ID would require two-step process, meaning I need to first query the jobs table to find all the job IDs for a user, and then use this job IDs to look up in the executions table to find all the jobs, to find the status of all jobs. So to solve this, what we can do to monitor, to give the status of all the jobs of a particular user, I can add a global secondary index on executions table. So basically it's like a secondary index, normally if we talk in terms of PostgreSQL. So partitioning on user ID, and then sorting key, I'll try to sort it by execution time plus this job ID. So this way it really helps us to efficiently just query with a single query of to find all executions for a user, which we are already sorting by execution time. It really helps us to support pagination and filter by status if needed. So this index really helps us retrieving in a faster way to find jobs of all user. So that's one thing that we can think of to avoid two queries to a single query. All right, so this is a like simple straightforward flow that we have. So here that's what I just have to directly query execution table for finding all jobs for user instead of first to jobs and then to execution. We'll try to add a global secondary index and partition table. Partition key will be this and this, so this really helps us retrieve faster. Okay, fine. Now let's go into deep dives of discussing one point of a non-functional requirement that we have listed above. So first thing is we need to execute job so within 2 seconds of their scheduled time. Currently, what is the status of the system that we have just discussed above? I just pointed out here. So currently what we are doing, we are trying to periodically query our job store or database to pick the jobs that needs to be executed. So let's say that if we ran the cron job every 2 minutes, then a job should be executed as much as 2 minutes early or late. The most obvious is here already there. So is that limitation? We are querying the database every few minutes to find jobs that are due for execution. So the frequency here, it's clearly in the not in the 2 seconds of the scheduled time. Okay, what if we are running cron job at 2 minutes, so that's why we are able to only retrieve jobs for every 2 minutes. So why can't we make a job cron expression to 2 seconds? So if we think of making cron expression or 2 seconds or less than that, this really won't work and doesn't scale well. Why? Because now looking at the requirements, we need to handle at least 10k jobs per second. So assume for every 2 seconds we need to process it is going to be a 10k multiplied by 2, it's going to be 20k jobs, which is very huge payload to process at once. And even querying that many jobs, that is 20k jobs, it's going to add more load onto our database, and also it's not going to be that fast. It is going to take ideally a few milliseconds to just get the job data, and then it will take some time to initialize them and distribute to workers and then begin the execution of that logic. So it's not helping us to achieve 2 seconds the requirement that we have. So how are we going to do this? So what can be the thinking direction to achieve this? So we can think of in a layered approach, maybe kind of 2-layered scheduler architecture. So I have here a simple the architecture. So first layer is simple querying the database. So here what we do, just like in our current design that we had above, additional thing is we'll just try to query execution table for jobs that are due for execution maybe in the next 5 minutes, maybe leaving some buffer for some latency, network latency and all that stuff. So once we query the records from the job store every 5 minutes or so, that is watcher or polls with jobs that should be executed and all, we pull from that database and then insert into our message queue. So we'll take the list of jobs returned by this query, whatever we have queried the database, and push them into message queue, maybe something like ordered by our execution time from our executions table. So then workers, whatever we have on the nodes to configure the execution logic and all that stuff, it will then pick up the each of the job from this message queue, and then it will process them in order and execute the job and update the status back accordingly in our executions table. So this 2-layered approach really provides decent advantages by decoupling the database, this database whatever we have from our job execution. So now it's we have completely decoupled using a queue. So just we are hitting the database every 5 minutes rather than the 2 seconds and all. Load is also significantly reduced, and this queues high throughput and all, we can make sure that the jobs get executed and all everything. So we are trying to make a bit of a progress and all, but the still the problem that we have is here. Let's say that assuming we at least tried thinking layered approach. And then, so let's say that the new jobs that are getting created are expected to run in less than 5 minutes. So since we are trying to retrieve database every 5 minutes, so there are two scenarios. We would either miss the job that the jobs was created, or we would pick those jobs only after 5 minutes, in the next 5 minutes query that we are hitting the database. So that is again going against our requirement. So we are not meeting that 2 seconds execution time of the job that is getting inserted into our database. Okay, fine, that's something that's downside. What if we could directly put the job into our message queue, so that it gets picked up by worker and it gets executed? Okay, that's also a good approach. But let's say that there are already a jobs enqueued in a message queue. Let's say there are enough jobs that will take 5 minute window, and since we know that in queues like Kafka, it only gets appended, and so for it to be picked up, the jobs which are in before that needs to complete. Again, this doesn't help us in achieving 2 seconds thing. So how can we achieve 2 seconds thing? So instead of our logged based message queue, whatever we have here, log based message queue, why how can we prioritize the jobs that we are trying to insert into a queue is something that we need to look in the directions of. So thinking of that, so what needs to be done to make sure that it can be executed in 2 seconds? So there are three kind of approaches at least we can think of. First thing is try to use Redis sorted sets. So here it offers really straightforward way to implement a priority queue. So we anyhow have a execution time in our execution table. We try to sort it by execution time, and workers can query with a score. So a score is nothing but here the execution time, which is less than the current timestamp, and it gets picked up and it will be processed. So this is some way the job is always sorted by execution time, and worker will pick it up and gets executed based on the priority of the execution time. But the downside is since it's something it doesn't really work in distributed environment. So we need to write our own retry logic, handle failure scenarios, manage Redis replication and all, something adding more and more operational overhead for us, which is something that we don't want to take it on. So thinking of the second the approach is RabbitMQ. So here RabbitMQ, there is a concept of a delayed message exchange plugin for scheduling. So basically here this is a plugin, this is not a native that comes in a RabbitMQ. So here we can just say that let's say we set deliver delayed message exchange value to 10 seconds. So then the job will get picked up in the next 10 seconds. So that really helps us which one it to be picked by the worker and all that stuff. So again, the same thing here, we should write our own retry logic, cluster configuration, monitoring, and delayed message implementation and all that stuff. So the simple way and the best way for us is we could think of is Amazon's simple queue service. So it's a fully managed service with a native support for a delayed message delivery, which I was just talking about in RabbitMQ. So like I said, like let's say we if we want to schedule a job in to run in 10 seconds, we can just send a message to a queue with a delay of 10 seconds. Then SQS will deliver the message to our worker after that delay. So after that 10 seconds is over, so it will be delivered to a worker, which gets picked up and processes the task and updates the status accordingly. So this the using a delayed message delivery is something really helps us to prioritize the jobs that we need to execute and meet that 2 seconds criteria or whatever that we have. Okay, so after considering this, the design is something it's going to look like this. we do introduce message queue SQS, and we had in here the delivery delay until execution time, and that gets picked up accordingly, which will be prioritized and picked up by worker and updates the status accordingly. So this is going to be a simple flow diagram. So here user tries to create a new job which is written to a database, and a cron job which runs every 5 minutes to query the database that are due for execution time in the next let's say 5 minutes. The cron job sends these jobs to our SQS with appropriate delay values, like which needs to be prioritized first and all. Workers will pick up or receive the messages from the SQS when they are ready for execution. And then if a new job is created with a schedule time, let's say 5 minutes from the current time, it is directly sent to the message queue, and with the appropriate delay time and all. So accordingly it will be prioritized. So this way we can achieve this the 2 seconds thing with introducing prioritizing that using execution time using this delayed message delivery concept that we have. Okay, fine. That's one non-functional requirement that we using this design will try to meet using SQS. And now the second non-functional requirement. So how are we going to make sure we will be able to handle 10k jobs per second? So here it is more of like 10k jobs being able to execute or creating a jobs. So to handle maybe high job creation rates, we can introduce a simple message queue, something like Kafka or RabbitMQ between our API gateway and the API layer, the service that we have. So this basically whatever the request that we are getting, so the producer will try to put it in the queue so that it doesn't overload or burst traffic to a scheduler service, and accordingly it will be picked up by schedule service, and then we handle these traffic spikes, allowing the job creation service to process request even at a sustainable rate when it's being overwhelmed. So this message queue enables horizontal scaling of our schedule service separately, and it helps us to handle 10k jobs per second. So that's one thing. And since anyhow the database anyhow we choose DynamoDB for jobs and executable tables, so it really scales automatically, which can handle thousands of writes per second per partition, which we already have partitions key for jobs. We have job ID, and executions table we have execution time to enable efficient querying of for upcoming jobs also. So with I think decent provisioning, we should be able to handle 10k operations per second and scale easily with this architecture which we just have here, introducing this queue layer between API gateway and the service that we have. Now let's talk about the message queue capacity. Here the message queue that we have, here I just have here the quick math. So let's say that for every 5-minute window we are querying our database, right? So we need to process at least 3 million jobs. I mean that's SQS should be able to handle 3 million jobs. How? We need to handle 10k jobs per second, and that is 5 minutes 300 seconds. So 10,000 multiplied by 300 seconds is 3 million jobs, is something that SQS needs to be able to handle. So let's say that the message size of our each message is going to be anyhow we're sending only job ID, execution time, and some metadata. It might sum up to 200 bytes, and each message in SQS can handle up to 256 KB in size. So that's not an issue. So here we have 200 bytes, and we have 3 million jobs. So total size of the message is going to be messages is going to be 3 million multiplied by 200 is 600 MB. So 600 MB is something that it can easily handle. So that's not of a bigger concern when it comes to this SQS. We just need to request for additional capacity by the AWS, because since it just we need to request a quota increase. It just suppose 3000 messages per second with batching. So just need to request for additional quota and then we should be good. For the worker layers, so here it's now this the messages size, whatever we are putting into SQS, is something that we are not worried about because it's just a 600 MB and it should be good enough to handle that. The worker section, so what can we think of to scale it? So maybe it can be a simple two things. It can be either containers or serverless functions, like can be lambda functions. So here maybe it's better to go with containers with elastic container services and auto scaling groups, since it is better suited for long running jobs and they really help us maintain state between executions. And though they might need operational overhead to configure all of these things, but it really helps us achieve the requirement that we have. But lambda functions are more for short-lived and all, so it's better not to prefer that. So ECS and auto scaling group should really help us to handle this work or consume jobs and then delegate it to respective nodes. Maybe we have 3 nodes and all, and accordingly it updates the status in our table. So I think this really helps us handle the 10k jobs of introducing this queue layer between this and then and adding additional ECS containers for picking from the queue and all. So these two additional introduction into architecture helps us achieve that non-functional requirement. And the other thing is how can we ensure at least once the job is getting executed. So now here the concern is basically how do we handle the worker failures. So if worker fails to process job for any reason, we need to ensure that job is retried at least a reasonable amount of times, maybe 3 times or 3 retries per job. I think that should be decent number. Okay, there can be 2 reasons for jobs to fail. One is visible failure, meaning simple, it is there is some bug in our task code, whatever we have the logic in worker nodes, or there is some invalid input parameters for the task that is expecting and it's not. So that is something we can easily take care using maybe a retry for 3 times with exponential backup strategy, meaning we try updating status to retrying and attempt we increment the counter to 1 and then again put back into a queue and gets picked up by worker and tries to process it again and then till 3 times. If it's again after 3 times it failed, then we just update status from retrying to fail and it will not be picked up. So this way, maybe this is something that we can easily handle using try catch block and exponential backup strategy and all that stuff, which is a simple and straightforward implementation. The invisible failure. So what if like worker itself went down, the things. So now how are we going to ensure when a worker crashes and becomes unresponsive? So there are 3 ways that we can think of. One is maybe have health check endpoints. So it's simple is we have separate, let's say, health monitoring system where each worker, whatever you have, it tries to expose as a /health get endpoint. And this monitoring service, which is a centralized service, it will try to poll this endpoint, each health endpoint, and then at regular intervals, typically every few seconds, and then when worker fails to respond to multiple consecutive health checks, the monitoring service will try to mark that worker as failed and jobs are reassigned to healthy workers accordingly. So that's the simple the way to handle this worker failure. The challenge is basically really doesn't scale well in distributed systems. Maybe we have thousands of workers and it's something that we cannot poll every worker, and it's going to be a lot of data network issues and all, and it's going to be an additional infra for health monitoring itself. We need to maintain that, and the coordination between our health checker and job scheduler is something it's again going to add very high complexity into our design. So this is something that we might not think of. The other way is job leasing. So job leasing is simple strategy. So kind of, let's say here, distributed locking mechanism, like using database to track ownership of jobs. So here simple, like if worker A wants to, as I just have written down here, if wants to pick up job 1 to 3, it updates the database job 1 to 3 is leased to worker A until, let's say, timestamp expiration 10, 30, 15 seconds or on so on, like every 5 seconds. So if it fails and the expiration time is not updated and it's expired and time is more than that, then of course it will be available for other worker to be leased. And this way we can make sure that even one worker fails, it gets picked up by the other worker after that expiration time that was set by the failed worker. Okay, so but here the thing is it really need to process frequent lease renewal, that is frequent updating of our expiration times of the specific job. So let's say like we have 5-second lease intervals, updating that timestamp every 5 seconds. Then 10k jobs is going to be, at least they're going to be 50, 10k multiplied by 5, 50k lease updates per second. So again, more overhead on database. So it's one downside. Another thing is we should be very careful with clock synchronization between workers. So let's say if clock synchronization is not accurate in across it's not consistent across the workers, then if worker A is still processing, there is a chance that other worker will pick it up as well. So that is something we need to take care as well if we choose this job leasing. The other way is we can straight away use SQS visibility timeout feature. So what this actually is about in simple terms, when worker receives message from the queue, SQS what it does, automatically makes that message invisible to other workers to be picked up for a certain period of a time, let's say 30 seconds, whatever it is we have configured. Okay, if worker processed that message successfully, then it SQS will automatically delete that one, or else after that visibility timeout period of, let's say, 30 seconds or 60 seconds, it puts back that message back to SQS, and so that it can be picked up by a different queue or so. So this way it makes sure that even one worker fails, other worker will be picking it up. And this is very the design is something will be same as whatever we had before, because we have SQS already introduced picking up from the watcher. And the other thing, when we are designing this, the important thing is we need to make sure we are handling idempotency. So this idempotency is simple. So if we are trying to run the task multiple times, it should have the same outcome as running it just once. So that is what idempotency is. Maybe three again, think of in three directions. If there is no idempotency controls, like basically we try to execute a job every time we receive it, this is a huge drawback here. Is this going to lead to a lot of significant data consistency issues? Let's say that sending a welcome email, I'm sending duplicate emails to user, is something that's very not right every time we are receiving the job and sending duplicate emails to user. And also, let's say there is something related to sensitive data amount transfers from account A or account B, and if you're doing it multiple times, there might be a duplicate sending of money. And also it's something that this is something never should be neglected, idempotency things. Another is deduplication table. So the deduplication table is basically we'll try to store each successful job execution with let's unique identifier, combining with the job ID and execution timestamp. So before executing any job now, we check against this table. If we found a match, then we know that we have already executed that once, and then we just skip that. Else we'll try to pick it up and execute it. So this way we at least make sure that it gets executed every once. So though it might have additional database operations and additional table that we need to, and we need to clean up periodically, because the size of that table is going to pile up very quickly. So that's something maybe downside or challenge, not downside. The other thing is we need to design a job itself in such a way. So let's say that I'm trying to send an email to a user. I might maintain a simple send welcome email flag in my table. So after processing that, I'll just update that sent email flag in my DB, and then when I'm trying to execute that, I check against that flag. If that is true, I'll just skip it. So this way it really helps us if we can design a job itself in such a way that it's taken care. So this is the simple way of designing a simple what do you say the job scheduler, and this is how at least we can think of when it comes to job scheduler. So though we have covered just very negligible points, but it's something gives at least a direction to think towards what and all. Okay, now let's just discuss about how can we design a simple distributed rate limiter given some requirements, functional and non-functional. So to understand at high level, rate limiter I think should be straightforward. So how many requests a client can make within a specific time frame, kind of simple traffic controller for our API. For example, let's say we allow 100 requests per minute from a user, then post that we just reject excess request with HTTP status code like 429 too many requests and all. So it really helps us to prevent abuse or and protect our own servers from being overwhelmed by bursts of traffic and ensure fair usage across all users. So that is a standard way of building our own definition, or I mean the definition of rate limiter is. Now that we clear what is rate limiter is, let's just think of this is a rate limiter for our something like whatever the platforms that we have, APIs rate limiter. Okay, so the core requirements that we should first think of is how can we identify the clients so that it is trying to hit our service. So we should be able to identify clients by user ID and IP and API key. So I'll talk about this the instances, how where it can be user ID, IP and API key. And then the other functional requirement is we should be able to limit request based on configurable rules. So meaning that there should not be any code changes needed for adjusting limits, something so that we don't need additional code deployment whenever we wanted to update the rules. So that's the second requirement. Then other thing is that we should need to make sure is we all if it is something that requests are exceeded, we return proper error codes like 429 with proper meaningful rate limit errors, like how many are left the rate limiting count, and then what is going to be the waiting time. So what is the timestamp for the rate limit gets reset and all everything. So those are the helpful headers that we need to pass it in our response. Then other things which may be good to have is providing analytics and rate limiting data that we are keeping track of. And then of course we need to support storing those rate limiting data for longer time, like for further analytics and all that stuff. So that's the simple the functional requirements. I think maybe we'll try to cover first 3 points. And non-functional is the minimal latency. So whenever there is a rate limiter behind a particular service, the response that user should expect is always less than 10 milliseconds. So that's very minimal criteria for better user experience. So that's something we should meet. And then other is availability should be considered higher priority than consistency. So eventual consistency is okay, as slight delays in limit enforcement across nodes are acceptable. So we need to make sure that it's always up, then the data is not synchronized across all nodes. So that's something that trade-off. And the scale wise, we should be able to handle 1 million requests per second. That's hitting maybe let's say 100 million daily active users platform that we have. Okay, so these are like rough highly functional and non-functional points that we should be able to meet these things. Okay, so looking at this, if you see the main core entities, just at a high level we should have it is like we have clients, so the clients entity, and then we have a rules entity that we need to have, and then other is a request that will be getting as an incoming API request. So those are the core entities, so rules, clients, and requests. So here rules are simple. Let's say it specifies maybe like I can say authenticated users get 1000 requests per hour, and there is search API only allows 10 requests per minute per IP, or premium users get 10 times more than normal, something like that, or our global service has a limit of this numbers of requests per second, something low, like those examples is something that we'll try to store in this rule section. The other thing is clients. So that is like entities that we are trying to rate limit. So it can be identified by user ID. Basically user ID is something that authenticated users, and normal like anonymous users, or if it's something public APIs, we will just try to identify by IP. And if it's a developer API, we try to identify by API key. Okay, so yeah, that's the second core entity. The third entity is a request. So this is a simple incoming API request that needs to be evaluated. So it might carry something like client identity or endpoint that you're trying to access, and then timestamp, which really helps us to identify which rules to apply and how to track usage and all that stuff. So the flow is going to look like this. Request is going to arrive, and we try to identify the client from this request, and then this will try to look up the rules, which will try to help us check current usage against those rules, and accordingly decide whether to allow that request or deny the request. So this is like simple core entities that we have. Fine. And system interface, since this is a more of infrastructure component, there is not going to be much of an API services that will be exposing. So it's a simple straightforward, assuming we have a simple straight interface is request allowed. We pass in the client ID and the rule ID, and you just need to do some magic or logic or whatever it has, and give us just let us know, is it a pass or fail. So accordingly we can let it to talk to respective service, and then how many are remaining, and what is the reset time. So these are the things that we expect, at least the minimal the return response from our is request allowed. Yeah, now that we are clear, at least we have will be getting from this system interface. Let's now try to discuss one point at a time from our functional requirements. First thing is identifying clients by user ID, IP, or API key. So that's, we know that we need to identify by these things, but the question is, where are we going to identify exactly, and how are we going to achieve that? So I think this should be a simple. So basically in our architecture, where is it something that we need to place our rate limiter is something, this is more of a question thing. If there is three ways. So one is I can try to directly put in process, meaning I'll just add a rate limiter right in front of my respective microservices. So it might look something like this. So I have, let's say I assume a simple client is hitting our gateway, and we have some, let's say microservice 1, 2, 3 or whatever n. So I'm just trying to add rate limiter in front of my microservices, and then it will just know, it will just have in memory local counters and updates them and decides whether to allow or reject the request. This is extremely fast because everything happens in memory and no network calls, no external dependencies. But the downside is this here. Each server will have its own rate limitings built directly into its application code. Sorry, this is not downside, the points that I just explained to you. The downside is this. So now this service will only know about its own traffic and not about the global picture, meaning it will not have an idea of how many requests were routed to microservice 2 and microservice 1 and all. So each server will only know about its own traffic. So if there is a chance that user will get more than what the limit that we have configured. And this is actually ideal only when we have one server, because we don't need to worry about global picture. So this is something that is not considered given that ours is going to be distributed system. Okay, so the other thing is maintaining our own dedicated service. So here what happens is rate limiter itself becomes its own microservice. Basically here it's the design. So this basically tries to sit between our clients and then the microservice. So here when a request arrives at an application server, the server first makes an API call to rate limiting service, and then gets that boolean passes and other the things that it needs, and depending upon that it will just allow it to go to that respective service or deny with the 429. So it really, so this is something like it gives us more flexibility because we'll have more rich context information. Here we can control more, because we'll have an access to application code. We can really add a very complex logic for rate limiting, like user subscription tier and account status, and can really handle complex logic. Let's say we try to give more request during new year time or year end time and all, something that we can really get all of that context inside our application layer and pass it accordingly. And it really helps us maintain now only strict limits that we have, because it's a global counter, and only request minute per minute, whatever the rules that we have configured. The downside is basically it adds additional latency. Now every request that we are trying to send through our gateway to respective service, it needs to route back round trip from our Redis to service. So for every new request now it needs additional round trip from Redis. So this is something that is going to add latency. And also now we have introduced new service, which is again a single point of failure FOMO that we might have. So and also operational overhead. So what if it fails? Like, should we allow the request to go through our service, or should we deny? So that is something again we need to think of and add those strategies and all that stuff if we choose this the dedicated service. The other way is we can place our rate limiter in our gateway or load balancer. This is a more ideal approach, and that's actually preferred in most of the applications. So basically the rate limiter, whatever we have, it tries to run at the edge of our system itself, integrated mainly into our load balancer or API gateway. So now every incoming request, it will first hit this rate limiter before it reaches any of our services which are behind the gateway. And it tries to check the IP address, user authentication headers, API keys, and all those things. So here, a load balancer API gateway. And the downside is we'll not have more context info like we had when we maintain dedicated service. We only have information of whatever the HTTP request that we are getting. So that thing. And the other thing that we need to think of is, where are we going to store this rate limiting state? Is it something external again, Redis and all? I think that is something that we need to think of. And how are we going to identify clients? So for authenticated users, we can use something like authorization header in the request, like user ID. For public APIs or anonymous users, we can use IP address, maybe user agent or X forward for key in our request, HTTP request. For developer APIs, we can just look for X API key. So this is something that we can straight away use this to identify different clients that are hitting our services and all. This is a simple way of how do we identify clients and where do we place the rate limiter. That's our first functional requirement. And then the coming down to a second one, how are we going to limit requests based on configurable rules? So basically, how are we going to handle this? Which algorithms will we be using it and all? This is something, the more detailed discussion or important discussion point in this rate limiting algorithms, wherever we are trying to discuss about. The first thing is there is a fixed window counter, the algo. So basically, what is this simple? So like I think this picture itself should convey you. We try to divide this time into fixed windows. So here, let's say this is 1 minute window, and this is 1 minute window, and this is 1 minute window. And let's say we have a limit of 3 requests per minute, and here we have only 2 requests per client or whatever ID that we have. Here we have 2 requests, so we are passing it through and it is successful. And here now we have 4 requests, but our limit is 3, so only 3 is successful and other 1 is rejected. So this is what is simple as that and above figure. Then it should wait for a new time window to make a new request, and then we should be able to let them go through our service. That is a simple fixed time window, and it's very simple to implement as well, because all we need to keep track of here is the client ID, can be user ID, API key, or the user agent, whatever we just discussed in previous point. And then we need to keep track of window start time and the counter. So basically for this client ID, for this window start time, what's the counter? So if it is below the threshold that we have, we'll just let it pass through, or else we'll just reject that. So the problem here is the boundary effects. And so basically, let's say here I'm at the 59th second, and user is trying to make 3 requests, and again at 1 minute is trying to make 3 requests. So here we have now, ideally in 2 seconds itself 2 requests, 6 requests, which is something like adding more overload. And then rest of the seconds, like 59 seconds, there's not going to be any way for user to request. So that is something, boundary effect and starvation, that we need to address. So this is something that's not scalable and it's not preferable. So that's one approach we can think of. The other thing is sliding window log. The sliding window log is also like it's what it does is basically it keeps log of individual request timestamp, like for each user. So what happens is when new request arrives, we will try to remove all of the timestamps older than 1 minute ago, and check now if the count of all the log within that window is in bounds or not. So yeah, that is something. Since we are maintaining a timestamp for each user for every request, so we can just check for previous minutes window. So for example, in the above image, so here they assume this is 1 minute window, and we have 8 requests rolling per minute limit. And since we have for this 3, and here so there are more than 8. So the things that here we are just denying, and rest we are allowing, and all in the previous log that we have maintained request timestamps. So the downside of this is since we are trying to maintain every request timestamp for each user, there's going to be a lot of memory usage, because we need to keep track of all of that. And also the computation overhead for calculating all of the counter use going through the logs of that 1 minute window is also going to add additional computational expensive task for us, because we need to scan through all logs for count check. So this is something the downside. So to mitigate both of the challenges that we saw in fixing window counter and sliding window log, then hybrid approach is going to be a sliding window counter. So sliding window counter is simply, what happens is basically this is a sliding window plus fixed window. So here what we do now, instead of maintaining logs or the timestamp related count, we will just have 2 counters variables, previous window count and current window count. So what happens when request arrives, we estimate how many requests the user should have made in that true sliding window by weighing the previous and current windows based on how far is into our current window. I think maybe that might be something confusing. So here there is a simple example. Let's say we are 30% into our current minute, that is 0.3 thing. Then this 70% of the previous window is something that we need to consider, because it overlaps with our 1 minute time window with 60 seconds, right? So that plus the 100% of our current window count is what is going to be the request that counter that we need to maintain to check the if it request has exceeded that count or not. Okay, so this is a sliding window counter that we can think of to address this. how can we limit based on configurable rules? And the other the popular way is token bucket. So the token bucket is like, think like each client having a bucket that can hold maybe number of tokens. It can be burst capacity. Burst capacity is nothing but throttle. Let's say it can handle 100 requests per minute, so that's going to be initial capacity of a token. So like tokens to the bucket, which is like refilled rate to the bucket, are added at a steady rate, which is can be like 1 token per second, or whatever we configure. So whenever there are no tokens available in the bucket, the request is rejected. If there is a one for every request, we try to remove one token from this bucket, and if there's no token, we just reject the request. So let's say that initially bucket is holding 100 requests thing, and refill is at let's say maybe 10 tokens per minute, at like maybe steady rate of 10 requests per minute. So client can make 100 requests immediately, because initial burst bucket size is 100 tokens. Then for additional request, you should wait for this refill rate. Let's say it fills after for 1 minute 10, then after 1 minute again you can make 10 more a request. So it's something like that. It gets filled in this way, which it really big handles both sustained load and temporary burst. So even if it's hitting 100, because we have bucket size as a throttle value, so it really handles that burst that we have. And what we just need to do is basically simple, the number of tokens that are in a bucket, and then what was the last refill time per that client. So the thing that we need really be very strategic about is choosing the right bucket size. So what should be the actual size so to handle this temporary burst, and what should be the refill rate that tokens are getting filled into a bucket for each client, is something that we should maybe decide based on our experience on that service that we have. So now, where do we actually store this? Is it something that we store in Redis? Yes. So the flow is going to be something like this. A request a request goes to gateway with user ID, let's say ABC. Gateway calls Redis. Maybe this is trying to get multiple field values in a single query, hm-get, and this is the ABC bucket, and if we try to get tokens and last refill. And the gateway, what it does, it checks last refill time. So here whatever we got here, let's say it was 30 seconds ago, and assumes refill rate is 1 per second, 1 token per second. Then it needs to update our token count by 30. So it needs to add 30 tokens into a bucket. So because it last updated was 30 seconds and refill rate is 1 per second, and we add additional 30 to our bucket. So this Redis command might look something like this. Here trying to execute in single atomic operation, multi, then setting this ABC bucket and tokens field, the new token count, maybe 30 in this case, and last refill whatever the current timestamp was, and we automatically set expiry on this key as well, meaning if it's idle for 1 hour, let's say, we will just delete this, expire this and all. So based on this, gateway allows or denies based on the token count that we retrieve from this Redis, and update it accordingly. If it is successful, we just decrement it by 1 and then allow it to access our service. Okay. There is one problem here. While writing there is not an issue, but while reading there is an issue. So let's say that what happens is, if I try to send a request at the same time, both gateways tries to, since we have multiple gateways, they tries to read same initial token count, let's say 30, and they both calculate that they can allow the request, and both update the bucket, and though it is not the right value that it's getting updated for each of the gateway, it could allow even two requests when there is only one token left in our bucket. So that's something raising condition for reading also needs to be taken care. So to handle that, we need to move entire reading those token and last refill, and also calculating that and updating this everything should happen in single atomic operation, and the best way to achieve is Lua scripting, which is something that we can execute in our on our Redis and make sure that there's no race condition when we are trying to read, calculate and update. Everything happens in single thing. So this way we will try to use this token and make sure that we limit request based on configurable rules, whatever we have here using this token bucket, the simple logic that we just discussed. So that's one one point that we can address. And now we need to reject request when I exceed it with a very correct status code of 429 and also helpful headers. So what is the approach here? Meaning when there is exceeded, should we drop them or should we queue them? Should we yeah, that's something. Yeah, this, if it's something like very instantaneous or interactive APIs, the most preferred way is just fail fast, meaning we'll just drop it and we'll try to return something, a response in this way, like 429 status code, too many requests, and what is the rate limit, and remaining is when it's going to reset back, and when can he retry after kind of in 60 seconds and all. So we just provide you a very helpful message so that they can implement their own exponential backup strategies in their own clients and meet the whatever their business logic is all about, something like that. And should we queue them? I think this is something, it's not preferred in most of the design discussions, because it adds more complexity than it solves, it helps in solving. So something that I would avoid it to discuss or anything like that. And now let's go into deep dives and discuss one non-functional point at a time. So first thing is we need to handle 1 million requests per second. So how is it that we can handle this much of a traffic for our system? So let's try to talk the pragmatic numbers of a Redis instance. A typical Redis instance can handle at max 100,000 to 200,000 operations per second. Maybe it can be reading specific key value or writing specific just an operation. Okay, since now our each request, if you see, we prefer token bucket algorithm. We have hm get, we are trying to retrieve token count and then last refill time, and also we are trying to update that new token and refill time and all stuff. So here hm get is one operation and set is one operation. So basically for every request we are performing two operations. So it falls back to again the limit each Redis instance can handle up to 50,000 to 100,000. So now think we just think, okay fine, let's just spin up more instances and we should be able to handle 1 million requests. Let's say we are assuming at max one Redis instance can handle of 100,000. 10 Redis instances and short should be able to achieve our 1 million requests per second. But the complexity here is not about spinning up instances. It's like partitioning the data so that each request knows which Redis instance to talk to, and it will know, so that it will have right counter of how many requests are left in that time window or stuff. So how can we achieve is something which is very crucial here to make sure that the request goes to right Redis instance. So the thing that we can think of is or a consistent hashing is something that we can use it here. So since we know different clients here, for authenticated users we know we were using user ID, so we try to hash the user ID and whatever the value that we get, and then we route that request accordingly to that hashed value of that Redis instance. So it will know now which Redis instance to talk to every time, because hash value of that user ID is going to be consistent. It will hit the same Redis instance. Same for public APIs. I will try to hash based on IP address, and it will give me some value which will be always the same, and it will talk to same Redis instance. Same for API keys. So this way what happens is, I will try to have this consensus, this consistent hashing, and then make sure that it's Redis right instance. So it keeps track of different set of clients or users or buckets, and gets bucket data, and then if it is meeting that, it will pass through it, or else it will just reject it. So this way I can with the 10 Redis shards, we mostly in production real time, it's something that we doesn't really take a job of handling all separate instances for ourselves. We just delegate everything to Redis cluster, which really helps us handling this hashing, the thing that we routing and all, everything that needs to be sent will be handled by Redis cluster. So each will handle 100k requests per second, and should be able to 10 Redis shards should be able to achieve our requirement of 1 million requests per second. So that's the simple calculation of how can we say hit our 1 million requests. The critical point here is, partition data, so that each request knows which Redis instance to talk to. So that's one thing that we should really keep in mind, how we can achieve that. And the other requirement is, how do we ensure high availability and fault tolerance? Is something like what if, the Redis that we are trying to keep all our counters, last refill time, and all these stuff that we need to pick whether to allow it to service or not. If Redis shard goes on, what is it that we will be thinking of? What can we do? So there are two things which is good depending upon the situation or the requirements scenario that we are in. Fail closed is what it is. Basically, I just reject all requests that is coming in with 50, like services unavailable or not available. So I'll just not let it go through my application service. So, and then this is a fail closed. Okay. And fail open, here is basically what I do. I'll just try to allow all requests to proceed as if my rate limiter is disabled or is absent, and try allow the user to hit my application service and get whatever they want. So basically what happens here is, if burst request flow in, which made our Redis shard go down, can also result in cascading failures, meaning can lead to more load on our the servers, meaning downstreaming all of the traffic to our servers and bringing the whole system itself down. It's something that really not preferable, because it brings our whole system down, and it's something that is not expected in real scenarios. So fail closed is something that it's better way to choose, and also there can be we can choose master replica. So what we do is basically we'll try to, for each Redis shard, we'll try to maintain a read replicas of that Redis instances of, maybe we'll do asynchronous replication to that read replicas, and whenever this goes down, particular Redis instance, this comes and takes it over. So this basically will be handled by mostly Redis cluster, which they have failover strategies and all that stuff, which it will be taking care of. That's something we can handle. Make sure that high availability is there with the read replicas, and also try to follow this so that we don't lead or to cascading failures of old system fault tolerance and all. So this way we can think of and handle that. Now let's talk about how can we minimize latency overhead. So that's something very important whenever a user is trying to access a specific services. So there's a concept of connection pooling. So instead of trying to establish new TCP connection to Redis for every the rate limit check that we are getting, we can maintain a pool of persistent connections. So this, what it really helps us is eliminates the TCP handshake overhead, maybe which really might take around 20 to 50 milliseconds depending upon network distance, and allows connections to be reused across multiple requests. So this connection pooling really helps us to persist these connections, and so that every time we don't need TCP connections. This way, this is one strategy to avoid or to minimize latency overhead. And the thing, but only thing is, we just need to tune the pool size based on our request volume that it is hitting our API gateway and the services, and also the Redis response time. So that's one thing. And another thing is simple. Anywhere we talk about latency, geographic distribution. So we try to deploy a rate limiting infrastructure close to users, API gateways and Redis cluster in multiple regions. Let's say user in London is talking to Redis instance in maybe, let's say, Virginia and other places in US, will see a much higher latency than talking to the one in the same region, right? So that trade-off is something like, we can choose for quicker response times and less trying to minimize latency. Yeah, I think between regions, eventual consistency should be acceptable for lower latency trade-off. Yeah, that this might be, I think these are the two things that we can think of when we discuss on minimizing latency and all that stuff. All right, the next point is, how do we handle hotkeys? Hotkeys is nothing but viral content. We need to know what are the techniques that we will help in scaling this hotkeys viral content. So approaches, let's just brainstorm quickly. There are, like, need different strategies here. So in this case of rate limiting, there will be actually, it can also come from legitimate volume clients. So this is the scenario that I'm talking about. It can be like analytics systems or data pipelines, or maybe something apps with aggressive refresh patterns. So to mitigate that, what we can do is client side rate limiting. So we can really encourage the clients to implement their own rate limiting for smooth functioning or smooth traffic. This really prevents accidental creating hot shots, and while really helping us to reduce server load. And to be in practical, let's say we have OpenAI or other SDKs that we have, they really will have their own built-in client rate limiting logic that respects the server response headers that we are trying to send using the logic that we have created. So that's something that it can help mitigate this high volume clients. And the other thing is, we can allow clients to request batching multiple operations into single request, so that they can reduce number of reads that they are trying to hit our services. Then other thing is, introduce premium tiers. We'll try to offer higher rates for powerful users who need them, potentially with dedicated infrastructure. So these are like three ways maybe we can try to mitigate this high volume clients. The other thing is, let's say we have abusive traffic. There's no straight away we'll just block it. Automatic blocking. Let's say that, for example, that specific client had hit the rate limits, like, let's say 10 times in the last specific minute, then I'm straight away temporarily blocking its IP or API key or user ID by adding them to a block list. So this can be kept somewhere in our Redis shards and only checked in case of cache misses or not. So this way we can, depending upon like that conditions, we can just block them. And another thing is, we can go for DDoS protection, maybe using Cloudflare or AWS Shield, which can detect and block malicious traffic even before reaching our rate limiter. So this is the two approaches that we can handle this viral content or hotkeys that we have. And the last point in our non-functional is dynamic rule configuration. So far we have discussed the rating rules are static and all that stuff, but like I said, production systems really need flexibility to change without having for them to deploy their code base. So how can we do this is something straight way. There is two ways, pull based and pull based. So pool based is basically what I do is, let's say it's a simple strategy. I try to store rule configuration in some my rules table. It can be simple as I have columns like line type, endpoint, and request per minute, etc., and all that stuff. So I try to store those details in my rules configuration database, and the API gateways where our rate limiter is actually sitting. It will try to periodically poll for my database for configuration changes if there are any, and it'll try to pull the latest rows from that DB, and if it's something that is changed, it will just update the logic accordingly and then implement that configurable rules. But the downside is there will always going to be update delay. So let's say that the change that I made is 30 seconds ago, and we are trying to pull every 2 minutes or 30 seconds, so there will be delay of whatever the time that I have updated and the time it is pulling it. So there is some delay. The other, to mitigate that delay, there is a push based configuration approach. Here there are systems exclusively designed for handling this distributed configuration management. For example, Zookeeper, etcd, or we can even think about Redis PubSub. So what this does is basically this whenever there is a change in a rules, it notifies all of our API gateways that there is some change, and then it updates accordingly in that respective API gateways rule sections and all. So this configuration service, whatever we are talking about, etcd or Zookeeper, it will immediately notify all our API gateways and with updated rules within seconds and all. So this way, something that we can really prefer poll based or push based. The challenges here is basically again more complexity, and we need to handle all of the fallback mechanism and also connection failures, like if how do we ensure like there is a partial failure, meaning only few API gateways receive updated rules and not others, and what do we do in those cases or something like that, is something that needs to be taken care of. And so this is not mostly preferred unless it is very sensitive, like dealing with security incidents or HFTs and high frequency trading scenarios that we have, is something that is ultimately preferred, or else mostly this poll based configuration is something it can be adopted mostly. Yeah, so at a high level, this is how we can think of when we are talking about designing a simple rate limiting system. Now let's discuss about Facebook news feed or Twitter timeline feed and all the stuff, wherever we have standard social media platforms of seeing the timelines of the posts or videos or whatever of the people that you're following or you are subscribed to. Let's just understand how can we design such systems for a longer scale. Okay, so going straight away into requirements, functional ones. So first thing is user should be able to create a post. That's first functional requirement, and then user should be able to follow specific people that they wanted to, and view the feed of the post from the people that they follow in the second step, maybe in chronological order. And yeah, and user should be able to page through their feed, pagination through their feed, whatever we have. And the additional points, it's good to have, they can either like or comment on specific post of the users that they're following, and also provide an option to make private posts or only visible to specific people that he or she allows. So maybe, yeah, these are like good to have points. We'll try to focus on discussing first 4 points. So those are like functional requirements. So when it comes to non-functional, the first thing is the posts, whatever the people that they're following, they should be visible in their timelines in less than 1 minute time window, meaning we are prioritizing availability over consistency. And it's okay if it takes 1 minute to update the respective timelines and all. So that's the first eventual consistency. And then posting and viewing post should be less than 500 milliseconds, meaning they should be able to see their post in less than 500 milliseconds. That's a latency criteria that we should meet. And our platform should handle massive scale of users, so assuming at least maybe 2 billion users on our platform. And then users should be able to follow unlimited number of users, and then should be followed by an unlimited number of users. So the simple follows and following and followers. Now that these are the now functional and non-functional requirements. So now we are clear on this. The core entities, I think it's a simple straight away. There it's going to be minimal core entities. We have, if you see straight away, there is going to be a post that he can create, and it's going to be, of course, user entity, the people itself, and then the follow, so whom they can follow and all that stuff. So here it is simple user in our system, and follow is simple unidirectional link between users in our system, and post is actually the one can contain the image or text or whatever they wanted to post it in the platform. So these are like core entities that are involved in this system design discussion. So now using this, the functional requirements that we have for every point, ideally will have one API exposed. So first thing is we should provide an option for user to create a post. So this will be a simple post endpoint. This is going to be a post. It can be post events. I think it should just be /post. Okay, and then it can they can provide some content, whatever it is. This is my first post or whatever, and it just gives 200 okay response status with the post ID that it was created. So this will have a simple endpoint to support the creating a post. Then the second is endpoint is they should be able to follow the users. So that is the that's the second point in our functional requirement. So this is going to be a simple endpoint, the put. So basically they will pass in the user ID that they want to follow, and accordingly we will just update the record in our table. So that's the second endpoint. And the third endpoint is going to be about viewing the feed. So here it's going to be simple get endpoint with the query params like page size, cursor, and accordingly whatever we have query params, we return list of the post items, and we pagination logic. If there is an X cursor, accordingly you can just use that to pull the subsequent results. So this is a simple cursor pagination endpoint. So I think these are the three endpoints that we can discuss about: creating a post, following a user, and then viewing a feed that they can see in the timelines. So now that we are clear about entities and high level endpoints, let's try to discuss at high level data flow or design of each of our functional point. So first thing is user should be able to create a post. So here it's basically create a post and have them accessible by their ID. So let's try to start a simple I think this is going to be standard flow. We know this is going to be for scaling, so we'll just put a horizontally scalable service behind this API gateway. So assuming this is a post service, a gateway or load balancer, which really handles routing, rate limiting, authentication, other stuff that we can. And so by having this API gateway or load balancer, we can just scale up our post service for more traffic by adding additional services of the same node. Since it is stateless, and anyhow we are writing to database here, the DynamoDB, it's easy to scale. So simple flow is user hits our API gateway with a new post request that gets passed to one of our post service endpoints, which creates an insertion row into our database. So this is a simple flow. Maybe the post table can be something like this: ID, content, created at, and updated at, created ID, and all those additional metadata fields that we wanted to. Okay, fine. So that's the simple the first requirement. And the second one is user should be able to follow people. So This is straightforward again. What happens, we will try to create a simple follow service, and in database I'll create a follow table. So maybe I'll try to use the entire relation, like user following, which is the partition key, and user followed, which is a sort key. So, and we can also create a global secondary index with the reverse relationship, that is your user followed here as the partition key and user following as the sort key. So what this really helps us is, basically it allows us to look up all the followers for a given user. So this really allows this way of having follow and then follow global secondary index of reverse relation thing. Querying is going to make us easy. Let's say that now if I want to check if user is following another user, we query with both the partition key and sort key. For example, here user following colon user followed. This is a simple lookup, and if we want to get all of the users a given user is following, we query the partition key, which is the user following. This is a range query. So if we want to get all the users who are following a given user, we query now the follow global secondary index with its partition key user followed thing, which is a better way for us to handle this query, and we are off to a good start, at least, of able to follow. So same way hits the follow user ID, the put endpoint that we have, and goes through follow service and accordingly updates our follow and follow GSI tables respectively. And this way a user can just achieve following thing. And the next requirement is user should be able to view feed of posts from people they follow. So the challenge can be broken down into multiple steps. First, what we do, we try to get what happens here. I try to get all of the users who a given user is following. Okay, so I'll try to get all of the users who a given user is following, and once we have all of the users list, we get all of the posts from those users using the creator ID. Finally, we sort all of the posts by their time and return them to the user. So this way I'll try to get posts of the users that he's following, so by introducing additional feed service. So this feed service is what the three queries, so the steps that I just mentioned, is what this feed service logic is going to be about. This is going to be very read heavy and have very different query patterns than the above two things, because this is read heavy and the other one was the post writing, and then this is a put updating and all. So separating it out is what really makes sense, and that's why we have here feed service. So finding all of the posts from given user is really tricky with the post table with now the three steps that I mentioned. While we have an index on our follow table here, to quickly look up all the users a user is following, we really don't have an index on our post table to quickly look up all the posts from a set of users. So again, same way how I did add a global secondary index to maintain reverse relationship, I will try to add a global secondary index on post table with the creator ID as a primary key and created at as the sort key. So this way allows us to quickly pull all the posts from a set of users in a chronological order. I think this is something if you're just you'll get time used to it if you get used to DynamoDB of partition keys, sort key, and what is global second index and all that stuff. So this seems to work for yeah. So basically for a given user, we first request all of the users they follow from the follow table. Then we request all the posts from that end users, whatever we got from this post table. Now we added this primary key, partition key and sort key. Using this GSI, we sort all of this post by timestamp and returns the results to the user, which is better way of querying and getting the results. Now the thing, if you really observe now, there might be a alarm ringing for you now, and several really potential bottlenecks or flags emerge here. So he's going to think like, now one user may be following a zillion of users, lots of users, and each of those users may have lots of posts. Okay, many users and many posts. The total set of posts may be very large because of many users and many posts. So we need to solve this. How can we handle this user having many user following many users, and that each user is having many posts? So this is something we need to keep thinking about, and how can we solve. We will discuss about this the many users and many posts in our deep dive, but that's one question immediately, something that we need to start thinking towards. And the other point in the functional requirement is user should be able to page through their feed. I think it's just simple, same as above. We will just first get all users who a given user is following. Next, I'll try to get all of the posts from those users that are older than the input timestamp that I have, the query that I endpoint which I just showcased, and then finally I'll just sort all these posts by time and return to the user. So it's just going to be same pattern, the architect of hitting the feed service and then trying to populate their timelines and all. So this is going to be a simple straightforward point, so I'm not going to talk much about it. So let's straight away dive deeper into our non-functional requirements, one point at a time. Handling users who are following a large number of users. So how are we going to handle this? I'm a user, so I'm following like it's a billion users on my platform, and how are we going to pull posts from all of the billion users and showcase in his timeline? So this is a standard funnel problem. So basically, if user is following very large number of users, the queries to the follow table will take definitely a while to return the details that I need. So once we get each of the people that they're following, again we'll be making huge number of queries to the post table to just build their feed of all the posts of that specific users. So this problem is something called fan out, which I've just, so a single request fans out to create a lot of queries. Here it is basically queries to pull the post of all the users that is following thing. So what is the straight away instinct is basically, can we compute or feed results on writing on or post creation, rather than trying to get this at the time that we really want to read and populate the feed. It's something that we can really think of. Then if we think in this direction, the instinct, whatever it was saying, then for users following really large number of users, we might maintain separate table called pre-computed feed. So instead of querying the follow and post tables, we'll be able to pull from this pre-computed table and then showcase on their time feed. And when a new post is created, we'll simply add it to the relevant feeds. So this itself, pre-computed feed, is going to be simple table of having user ID mapped to the list of the post IDs, keeping it compact, maybe 300 or so posts for each user feed. I think that should be it. It's not needed to store all of the posts of all the users that is following it, because nobody is going to keep scrolling all of the things. Even if you observe in the specific platforms, you will see after a while it gets dried up, because we don't really have it on the pre-computed feed. Again, if they even at the end of the last page of content, then we might trigger the standard querying of for users follow table, and then after we get the users, query post table, and then again append it to the current cursor that is in. Maybe that's something that we can just design in our system. So this way we can be compact, and then so once we introduce this pre-computed field, this is how it's going to look like. Here I have here now pre-computed field. Like I said, user ID is the partition key and created at is the sort key, and post ID is what I'll be trying to maintain. So let's now quickly check the size, storage size of this pre-computed table after introducing this pre-computed table, before we try to move on to the next point in our non-functional. So let's assume that each post ID is something like 10 bytes, and to store 200 posts per user or 300 posts, it might be like 2 KB per user if it's 200 posts. So if we have 2 billion users, so 2 billion users then what is it? It's going to be so 2 KB per user, 2 billion users, is going to be 2 TB of storage for all these feeds. So this is quite reasonable for whatever the system that we are trying to handle. So that's something. Pre-computed feed is something. Table is what is going to help us handling users who are following large number of users. Yeah, I think yes, this thing should be doing. Now let's the other point is, how do we handle users with a large number of followers, like celebrity or someone who is having large number of followers. So same fan out problem here as well. So when a user has large number of followers, we have similar fan out problem. When we create a post, we need to write it to millions of feeds, right? So we need to write it to their all of its followers timeline. So because we choose to trade off with some eventual consistency, we have a short window of time, maybe less than 1 minute, to perform all of this rights. So even in that less than 1 minute time window, how are we going to make sure that we update the followers timelines? So let's try to think of the multiple approaches here. So approaches is first the blaster request. So blasting is simply basically we try to update all of the users, all that millions of followers timelines at the time, which is in practical is not at all feasible, because this will definitely fail due to limitations in the number of connections that can be made from single post service host, as well as latency available. So this is something naive approach to just, but it's never going to work out. The other approach is asynchronous workers. So here what we do is we will try, if you see here, I'll try to add asynchronous workers behind a queue. So since our system tolerates some delay between when post is written and when post needs to be available in feeds, we can put up a queue which is like something like, say, post create queue, and I have fleet of feed workers to consume these requests from this post create queue. So any queue will work here as long as it supports at least one delivery of messages and is highly scalable. Maybe we can choose Amazon's simple queue service or any other queue that we have. So when a new post is created through this post service, we create an entry in this post create queue, which is SQS, with the post ID and the user who has created it, that is created user ID. Now each worker, the feed workers, will look up all the followers for that creator ID and prepend the post to the front of their feed entry. So if you see here, this worker, the pre-computed feed based on this ID that he got from this post create queue, and using that ID, it will try to get the all of the users that they are following and get it to the feed workers and use those IDs to populate those respective user IDs pre-computed feed table. That way there is eventual consistency of 1 minute, and we can try using this asynchronous workers of introducing queue layer and feed workers to do this job. So the throughput, so the challenge here is basically the throughput of this feed workers should need to be really enormous. For small accounts, there's no issue, meaning having few followers, there's no issue of updating their time things. But for mega accounts, let's say millions of followers of celebrities or the people well known among the crowd, writing to all of its followers, lot of work, really lot of work for these feed workers to really do it in that 1 minute time window. So that is really a challenge here. So what is the greatest solution for this approach is just trying to update all of its followers timeline is here asynchronous workers with hybrid feeds. So what is this basically is just extend this post create queue as really discussed in the previous approach. What we'll do, I'll create a asynchronous feed workers that are really working of a shared queue to write to our computed feeds. So what I really mean here is hybrid asynchronous hybrid feeds. So normal account posts, async worker pre-computes feeds for all followers. So like I said, a very less number of followers, that is a normal account, we just do pre-computing feeds for all followers, that's fine. But if mega account posts, async worker skips pre-computation, meaning it will not try to update the timelines of all of its followers. So follower X, let's say that now I'm following some celebrity or the tech guy who is popular. I'm following up that account. Assume that he opens an app and he tries to look at its timeline. So what we do, whatever we have any entries for that specific user ID already in the pre-computed feed, we'll be showcasing them in his timeline. And alongside with that, when he's trying to read, then we will try to pull latest post from mega account via query, which is a simple one because you might be following very less users, right? Then that's actually better way of letting the feed workers to do enormous job on post creation itself. And then I do the query and then I'll try to merge and sort them for display accordingly, both from the pre-computed feed along with the query that I'm doing on read time of that specific follower. So this is something we can really mitigate, that is this hybrid approach of following this async post create queue and the on read time reading from this querying directly from this post table and all. So the only thing complex here is doing the merge at read time is something more computationally expensive, but that I think that's a trade-off that we can really digest ourselves given the complexity that we need to handle for millions of followers. So this is the approach to how can we handle users who is having large number of followers when they have created a specific post. Okay, now the last point is how can we handle uneven reads of posts. So this is something really interesting point to talk about. Our feed service has been reading directly either from pre-computed feed or post table whenever request to the feed. So to discuss pragmatically, for vast majority of posts, they will be read for just first a few days and never read again. For some posts, especially those from accounts with lots of followers, the number of reads the post experience in the first few hours will be very massive. So these are the uneven loads of the traffic that I'm just trying to discuss about. So how are we going to deal with this hotkeys in post table, like viral content, other people who have posted for the first initial few hours or something? It's going to be high traffic or people will be trying to read it. So there are two approaches again. Post cache with large key space. What is this is basically, if you here I have here Redis post cache that I have introduced here. So we will try to insert this distributed cache between readers of the post table and the table itself. Since posts are very rarely edited, we can keep a long TTL value and cache it in our distributed this Redis one with LRU, least recently used. So as long as our cache is big enough to house maybe most recent post, the vast number of requests for the post table will whatever we are trying to hit will instead hit our queue, because we have cached it with a long TTL. And let's say if we have n host with m memory, our cache can fit as many posts as, let's say, n host and m memory, so n times n. So that many it can really fit in. And when posts are edited and not created, we can just invalidate the cache for that post ID. So this again, I'm just going to handle this post cache with the large key space of dealing hotkeys instead of reading from a post table, from directly reading from the Redis cache. And now the biggest challenge here is same hotkey problem that post table did have. For unlucky sharded partition that has multiple viral posts, the host that support it will be getting an unequal distribution of load again, which makes really cache also very hard to scale. So many of the hosts will be underutilized. What I'm trying to say is we have like multiple Redis host instances also, and if some instance has having multiple viral content hits, then again the traffic for that Redis cache is again going to be more than for other hosts. So it's like same scenario that we had for our post table. So that's one again the challenge thing. So even to mitigate this, here we just try to keep long TTL and post and evict those least recently used and n times n. And this same hotkey problem persists, like I said, uneven distribution across nodes. So assume this is a client and this is my Redis host and all those things, and just a simple this is getting more load than compared to this. Again, uneven distribution is still there with this post cache with the large key space. The to mitigate that is something redundant post cache. So like a distributed post cache that we just discussed here, I will try to insert a cache here again, this multiple between readers and this readers of this post table and this table itself, just preventing the hits to post. But what we do here, the only the additional thing that we do is we can choose to have multiple distinct caches using multiple instances serving the same post ID, meaning I will try to put the same post ID across multiple post cache, though now instead of one single database query, n queries can hit the database, which is very negligible when compared to millions of requests. What I mean here is, now since we are trying to store that post ID across multiple Redis cache instances, so though if that post ID is an hotkey, anyhow it is present across multiple Redis hosts, the load will be is kind of going to be not completely biased. Now we'll have only only small number of posts also across a cache, since we are trying to store duplicate post IDs and all. I think this way I can try to at least mitigate uneven distribution of load even onto Redis cache. And because since we are storing duplicate IDs, the cache misses can be high, and we do n queries into database. I think that's a trade-off that we are trying to make here. I think this is a simple timelines things when it system design discussion when it comes to I think the thing that we really need to learn from this kind of things is how can we really handle hot posts, and also how can we really update the timelines of all of the followers of the mega account, and a large number of followers. Another thing is handling users who are following really large number of users. Now, it's the opposite of the mega account. uh, like we just discussed, we'll try to have a pre-computed feed and maintain a post IDs big and compact, let's say 200 or something like that. So these are like three important points that we need to keep in mind when we really talk about this timeline feeds or news feeds and all those things. I think you learned something at least out of these 3 points. Maybe two or one point can at least might be clear. Yeah, this is what I want to talk about, this newsfeed or timelines newsfeed. Now let's discuss about how can we design a simple ad click aggregator service. Just a high level, what is ad aggregator? It's basically a system that helps us collect and aggregate the data on ad clicks that will be happening on websites like Google or other major platforms like Facebook, on whatever the platforms that we are. So it should be a service for advertisers to just track the performance of their ads and accordingly plan their next action, and try to optimize their campaigns and other things. So that's the simple ad aggregator click aggregator service. So now let's have a look at our requirements. So what should we meet? So first, a simple requirement is user can click on an the ad instance that will be displayed on specific website, and they should be able to be redirected to that advertiser's website. So that is the basic starting requirement. Then the second requirement is now advertisers can query that click metrics over time, maybe with 1 minute minute intervals or granularity. So these are like core critical points that we should try to design the system for. The other good to have points, and we're not going to discuss about this, but just I'm just mentioning it to you. We can have a system that can help solve ad targeting and ad serving, and track across devices, and integration with offline marketing channels and all that stuff. So these are like maybe good to have, and we are not going to discuss much on it. And let's look at the non-functional requirements. So here these are like important non-functional requirements that we should meet. Our system should be able to handle peak 10k clicks per second from our service, and the queries, the metrics that advertisers will be trying to pull, we should make sure that the latency for pulling those metrics is less than 1 second. So that's very important for them to see data in real time. And the other requirement is fault tolerance, and we should make sure that at any cost we don't lose any click data, because that's actually money for advertisers. So it should be fault tolerant and also not lose any click data. And like I said, as soon as user clicks on ad, whenever the analyst or from advertisers side, they try to pull the metrics on the dashboard, they should see the clicks on real time as possible. And that's one critical non-functional requirement. And other thing is idempotent click tracking. So meaning if the same user clicks on the same ad instance for twice or thrice and all, we should still count that as a one, not as like twice or thrice, because that's the duplicate count tracking and all. So how can we make sure that we do handle that idempotency? So these are like core critical non-functional requirements that we should meet. And others good to have is we can add a logic to detect the spams, and then demographic profiling of users from which region or something clicks that is we are getting, and what is the conversion of like tracking of the specific product or whatever it is that that advertisement is all about. Okay, so these are like core functional and non-functional requirements that we will be targeting to meet. Like we just discussed. So let's Now we are clear with the non-functional and functional requirements. Let's since this is not end user facing application, it's more of the data, more focused on data processing section, so there will not be any core entities or the APIs and all, but at high level we know the system interface. It's just let's just define system interface as something like input. What is the input that we'll be receiving? It is simple ad-click data from users, and output is we just need to give metrics of that ad for advertisers through any dashboard or whatever it is. So this is like simple input data and output data that it is expected out of our systems, and the data flow is going to be simple and straightforward. User clicks on ad a link, whatever that was displayed on a website, and then when user clicks on it, click is tracked and stored in our system, that is persisted in our store layer, and then once it is stored, user is redirected to that advertiser's website accordingly. And then once these three steps are done, advertisers can query the system for aggregated click metrics and all, see how many people have clicked it and all those metrics whatever they were looking for. So this is the simple data flow of this system. So yeah, at least yeah, we have like solid established simple data flow. Let's try to discuss one functional point at a time through our high level discussion. So here is the high level discussion. So first point is we can see that user can click on an ad and be redirected to the advertiser's website. So this is a simple requirement that we should meet. I think it's going to be very easy part, and it's going to be a very decent start that we have. So simple, what we do is we'll have a browser, so that is where we'll be trying to display the ad link or whatever on website. When user clicks an ad in the browser, we need to make sure that they are redirected to the advertiser's website. So what we'll do, we'll introduce one service called ad placement service, which will be mainly responsible for placing ads on a website that is in the browser and associating them with the correct redirect URL of the advertisers. So now when the user clicks on it, the URL that is placed by this ad placement service, we will send a request to this click processor. Something can be /click endpoint or whatever we can name it, which will track the click and then redirect the user to their the advertiser's website. So that's the simple thing. And the ad placement service can be simple advertisement table or something, which will have ad ID, the redirect URL, and other metadata if we have, and we need to maintain something like that. So this is going to be simple flow of this ad placement, placing the ad ID and link on the browser, and once we click will trigger this click, and then it will redirect accordingly to advertiser's website. So here redirecting again has two ways. Should we do client side redirect or server side redirect? So let's discuss about here. So like I said, handling redirects has two things. Client side redirect. Here if we follow this client side redirect, all we do is browser itself will automatically redirect them to target URL, and that will do browser parallelly, and parallelly we can post to our click endpoint so that we can track the link. So that is like two ways that we need to handle parallelly if we follow client side request. The downside is basically users could go to an advertiser's website without us knowing about it. So maybe the parallel post to /click endpoint might fail in between, and so we might lose the click data. So that is something that is not we need, because we need data accuracy, and we don't have to lose data. So this is something not preferred. So server side redirect is basically what happens is browser will not directly redirect, but on clicking it sends a request to our server, and there we will track the request, the click, and then respond with the redirect response code 302 to that specific advertiser's website. So this way it is always made sure that it goes through our server, and if you wanted to do additional metric calculation and all, it is will be taken care. And yeah, this is mostly preferred way to handle this redirects. And of course there is going to be additional load of handling this thing, and we need to make sure that the response for the users of redirecting to advertisers URL is way quicker, so they just don't feel that even fling. So this is how the handling redirect is there. So this is a simple thing. User can click an ad and be redirected to the advertiser's website. Okay, fine. So now the second point is advertisers can query the metrics over time with 1 minute granularity, like intervals and all. So they should be able to query every minute or so and get the data that we have. So ideally, let's just discuss what really happens when user clicks slash click endpoint or like when we receive a request from user to this slash click endpoint thing. So let's see. So first thing is maybe what we can do is we can directly store and query from the same database. What I mean here is when a click comes in from a user, we can simply store the click event in our database. So I'll just yeah. So when click comes in here, I'll just directly store it in my analytics database, which is the same as the ad db that we have. We have here ad click event. We will track event id, ad id, user id, and the timestamp that at which it has come. And so there will be an additional analytics service which will be something trying to pull query might look something like this. We try to count total clicks and distinct of user id from this ad click event table. Maybe let's say this is click events, and we try to match the ad id and timestamp should be whatever the stuff that they need, grouping by ad id. So they'll get the service and then that results will be showcased in the browser. So this can be one simple way of trying to utilize the same database and store it in the different table and query from the same thing. But the downside is because here, given the scale that we need to handle that we have, this solution will never work and the database will very quickly become a bottleneck here because if we scale up to 10,000 clicks per second, the group by query will be extremely slow and inefficient, and we will not be able to meet the low latency requirement that the advertisers really need. So it really breaks our non-functional requirements. So this is not the approach that we wanted to proceed with. So what is the other approach? So other approach is we can separate analytics database with batch processing. So this is something what happens, this is I think a better solution when compared to the previous one. So I'm looking at this design. Like I said, we will try to have a separate analytics database, something that can really help us with pre-aggregating data. So meaning when a click comes in, we will store the raw event in some database. So here raw events, it's something like Cassandra can help us with in the event database, and then there'll be some logic here. In our case, it's going to be Apache Spark with maybe cron scheduler which runs every minute, and it picks up the raw events. The Apache Spark picks up in batches, and then it will store it in our OLAP database. It can be Snowflake, Redshift, BigQuery, or Druid, or etc. whatever which is really optimized. The aggregating counts and all will be trying to store in this OLAP database, and analytics service will just query and then showcase it in the browser. So this way the schema of analytics database can be something like simple ad id and then minute timestamp and what was the unique clicks for that timestamp. So this is going to be simple, and here the Cassandra is something why we choose. Basically, it's a good choice here. It uses a storage structure that is called LSM, which is a log structured merge tree. So if you really want to understand what are the various kind of storage engines that are present, I would recommend you to have a look at how to design data intensive applications book. That is very informative, and it has a detailed section for the storage itself. So here what happens is it writes inserts and updates in a log like structure. Kind of it just keeps appending it to a file in memory, and it periodically what it does, it flushes this mem tables to disks in files called ss tables. So these ss tables they are optimized for reads for specific rows and all that stuff. So but they are not really optimized for pre-aggregating the metric count or range queries that we have. That is why we introduced here Apache Spark to pick up those things and do this aggregation logic and all that stuff in Spark job and store the aggregated count in OLAP database. That is why since it can is not good for handling the range queries and aggregations. We introduced this Apache Spark which can do that aggregation and store it in our OLAP database, which are good for retrieving this analytics thing. So yeah, now how will this data will be processing exactly? So let's say we have browser from users, we have 10k clicks per second, and we choose to run maybe, let's say we storing it in Cassandra, and do batch processing, let's say here cron scheduler of let's say every 5-minute window, and we'll be processing. So ideally 5 minutes is 300 seconds, so 10k clicks, so it roughly sums up to like 3 million events every batch. So here assume each event can be like 100 bytes of data, so we'll be processing around 3 million events, 100 bytes of data. It's around 300 MB of data every batch. So this is very well within Apache Spark that it can handle to do the aggregation logic and all stuff. So because this Apache Spark, what it does, it handles map reduce. So it will read the raw events from the Cassandra in raw chunks, parallel chunks, and aggregates them by add ID and minute timestamp, and then we'll write that whatever the results that he got into the analytics database. So yeah, this is a simple flow of achieving what separate analytics database with batch processing, and this way it really helps us to at least overcome the challenges that we saw in a previous approach. So here the flow is going to be simple like this. The data flow, add click is sent to the click process service here that we have, and the click processor service writes the event to event store, so which is here our Cassandra database with the schema that I just mentioned. So it will just write to it, and every 5 minutes the cron job kicks off the Spark job that read events from the event store and performs the logic to aggregate by add ID, timestamp, and wagera stuff, and it will have those metrics. And once that aggregated data is ready, it will be stored in our analytics database for querying for the analysts or advertisers. Then now advertisers can query the database to get metrics on their ads. So this is how it's going to be the flow with the current design that we proposed in the second approach. The challenges here is basically the batch processing introduces a significant delay in data pipeline. Since we are running the job like every 5 minutes and all, users still have to see always few minutes old data there, and we are not still providing for them to query the data in real time. So again, this is a downside, as real time data querying is something that we need to facilitate. So this doesn't meet that. So how can we address the challenge in the next approach is what this all going to be about. So the other approach we can think of is real-time analytics with stream processing. So what is this thing is to address the latency and the scalability issues that we just talked in the previous approach, we will introduce a stream for real-time processing. What happens is instead of we waiting for a batch to pick up and then put into our OLAP database, we process events as they come in, and rather than waiting for batch job to run. So what happens to achieve that real-time pickup is something we will use Kinesis or Kafka streams. So when a click comes in to our click processor, the service will immediately write the event to our stream, like either Kafka or Kinesis that just I mentioned. We then need something called stream processor. So stream processor here can be Flink or Spark streaming, which can process the streams from this Kinesis to read the events and aggregate them in real time. So this works by keeping a count of click totals in memory and updating them as new events come in from Kinesis. And when we reach end of maybe let's say time window or every couple of seconds that we wanted to flush to our OLAP database, and this will flush the aggregated data to OLAP database. So that way user can really query it in real time. So the flow is this way. The click processor writes this event to stream, here the Kinesis or Kafka streams, and stream processor like Flink or Apache Spark streaming reads the event from the stream and aggregates them whatever the logic that we have. and the aggregated data is flushed into OLAP database for querying, and advertisers can query to get metrics and all. So here, like if we have a time minute window of pushing the events to OLAP DB, you can question here the Spark job also. Why can't we reduce the cron job to 1 minute and then keep doing the same thing? So that adds additional data load. And also here there is a concept in a Flink called flush intervals. So what it really means is we can aggregate on a minute boundary, meaning the aggregation logic can really happen on minute per boundary, but flush the request every couple of seconds. So meaning aggregation will happen at here, but if you want to push those whatever at least we had a thing for every couple of seconds, we can just push it to OLAP database so that user can still query in real time. So that this flush intervals and is something that really helps us to achieve this real time the querying for the advertisers or analysts, whoever are trying to hit our services. So using this real-time analytics with stream processing, we will try to meet that latency challenge that we just discussed. So that was about our core functional requirements. So now let's try to go deeper into our non-functional requirements and see how can we achieve the non-functional requirement. So here the deep dives. First thing is we need to handle peak or 10,000 clicks per second. I think this should be pretty straightforward given the systems that we have discussed. So simple. So if you see the core components that we have here, the first is click process service. So we can easily scale this horizontally by adding more instances. Any modern cloud providers like AWS, Azure, GCP really provide managers services that can automatically scale services based on CPU or memory usage. All we need to do is just add a load balance. So this is why we just added load balancer or API gateway between the client and the service, so that this will take care of auto scaling based on that metrics that we configure. The other thing is stream. So this is again we are using Kinesis or Kafka streaming. Those are by default are built for distributed systems and can handle a large number of events per second if it is properly configured. So for example, here Kinesis has a limit of, let's say 1 MB per second that the data that it can pass through, or 1000 records per shard. So we need to add some sharding, maybe can be sharding by add ID, so that all of the events for given ID will be in the same shard, and it will be easy for us to query even for the advertisers. And the other thing is a stream processor. Here in our case is a Flink. This is also can be scaled horizontally by adding more tasks or jobs. So we can have separate Flink job reading from each shard from during the aggregation for the add IDs in that specific shard. And same thing applies to our OLAP database. It can be Snowflake, BigQuery and all, by adding more nodes. While here the sharding we might consider two ways: sharding by add ID or sharding by advertiser ID, so that all of the data for given advertiser will be on the same node, and it really helps us making queries for that advertisers ads very faster. So with assumption that advertisers querying for all their active ads in a single view. So that's something thing, and also we'll have additional monitoring layers and all that stuff. So just introducing load balancer, and then this is anyhow will be built for distributed systems, that will be taken care. So this I think this system the design what we had it here should be able to handle what we just talked about. The only problem here is how do we deal with hard shards. So hard shards is something that let's say some popular product has launched an ad with a popular celebrity and all, so this is getting a lot of clicks and on a website, and all of them are going to the same shard because we sharded here by add ID, and it's something uneven distribution is happening for that specific shard. So how do we handle situations like this is something that we need to think through. So now to solve this hard shard problem, one popular approach is now we can even add a IDs to appending a random number to the IDs, add ID like 0 to and 1 2 or whatever it is to the add ID, so that popular ads can be determined by this unique key of add ID with 0 or 1 and all, which will be distributed across multiple charts, and this way we can handle this popular clicks. Yeah, since we are adding additional partitions for that specific ad, this should help us achieve that. So this is one, at least a challenge that we need to take care using this the format that I just specified above. So this is a simple discussion of handling peak 10k clicks per second that we have. The other non-functional requirement is how can we make our system is fault tolerant and should not lose any click data. That's very very important. So so if we really notice here, we are already using a stream like Kinesis to store click data. So by default, these streams are distributed and fault tolerant and highly available. They replicate data across multiple nodes and data centers. So even if this node goes down, data is not lost because this allows us to enable persistent storage. Like we have here, if you see, we can enable this 7 days retention period on Kinesis. So even if this goes down, the data will be persisted and it will be picked up by the Kinesis whenever it's back up, and Flink can process this data accordingly. And also assume like our stream processor itself goes down, which is your Flink, and it will come back and can read if we have enable 7 days retention period on Kinesis from the stream again. And also this Flink, the stream processor, the scenario, if this Flink itself goes down, there is a concept called checkpointing. So checkpointing is something what it is ideally is, we periodically for every, let's say, a few minutes or hours can write its state to persistent storage like S3 whatever we have, especially if our aggregation windows are very long. It is like we are running daily ones or weekly ones. Since we don't want to redo those work again if we lose because of Flink is down, we can do checkpointing on Flink. So whenever now this comes back, the persistence is enabled we are to S3, so that can pick up from the latest checkpoint and continue from there, so that processed results are not lost and it will be continuing from there. So that's one thing we can think of on checkpointing on Flink. And still, after even relying on their 7 days retention period on Kinesis, enabling checkpointing on Flink, if we still not not confident of not losing any click data, we can do an hybrid approach here, making sure that click data is never lost and we always take care is I can introduce a combination of this real-time processing along with the Spark batch processing approach that we just discussed before. So here what we'll do, or parallelly there is a way from the Kinesis using through it's a file system interface and various connectors, so which really helps us to do both batch processing and real-time processing at the time. So raw what we'll do, batch processing, we will do raw click data pushing to S3, and then this gets picked up by Spark job depending upon the cron expression that we have, and do the all aggregation logic that we have, and that will be done by a reconciliation worker. So this basically, this is a layer that we added to double check if the counts that we have got through real-time processing is matching with the batch processing or not. So we will check accordingly. If there is any potential mismatch, then we'll try to identify root cause and try to fix it if something is going wrong in real-time processing. And this way it really ensures us us that we do guarantee the latency requirement using this real-time processing, and also the data accuracy with this batch processing, double verification of the click events that we have. So this way it's more flexible, the system that we are trying to design, and it takes care all of the requirements that we have. So this way we will try to meet this data is not lost at any cost. Now let's talk about the other non-functional requirement, which is idempotent click tracking. That, like we said, if user clicks multiple times, we should just consider that as a one-click event from that specific user. So what can we do to do that is we can add user ID to click event payload. So what but the only to get the user ID, we need to assume that user is always logged in, so that we can use its JW token or session cookie alongside with the click data that we are normally sending it to our click processor. So this that way we can add a user ID, and also the deduping, meaning the checking whether this has been hit before or not. Everything needs to be handled before sending it to streaming, because while we are doing aggregation over a lot of events, and if we delegate this deduping to that processing, it is going to take more time and additional work for it. So it's something that needs to be handled way before that sending it to streaming. So this is the downside, like I just specified. User should be logged in, and also, like, let's say user is trying to click on multiple instances of the same ID of ad that we have displayed. It's still considered as a one, which is not really what we really want. So this is something that it is not going to help us. Then another concept is called generating unique impression ID. So what this is all about is, we have an ad placement service, right? So now it generates a unique impression ID for each ad instance, and this will be sent to the browser along with the click data and redirect URL and all that stuff. And the flow is ideally it's going to look like this. The ad placement service generates a unique impression ID for each ad instance shown to the user. This impression ID is signed with a secret key. So why is signed with secret key? Let's say if a fake user tries to send with any unique impression ID, we still consider that as a unique one, and we might keep tracking that. So it's something that is defeating our idempotency, right? So we should always make sure that we are signing with secret key, so that when we try to verify in our click processor, we can make sure that the impression ID was something that we sent, that we got, not the new one from the fake user. Okay, so now when the user clicks on ad, the browser sends the impression ID along with click data. The click processor verifies using the signature of impression ID, and accordingly, if impression ID is present in a cache, if it does, then we will not process it, and if it is not, we will put that event in a stream and then cache that impression ID. So, and talking about the capacity of the cache, let's say we have 100 million clicks per day, and roughly around 16 bytes of message payload. So it is simply around 1.6 GB. So it's not much, very tiny when compared to the scale of the design that we have. So this way of generating unique impression ID is going to really help us solve this idempotent click tracking, so that only unique counts are calculated. So that's the thing. And the other discussion, so basically the last non-functional requirement is how can we make sure that a low latency analytics queries is less than 1 second. So we are already almost discussed on this in our streaming approach. So this streaming approach and batch processing approach it significantly helps solving this, because of pre-aggregating the data way before the querying by the advertisers or the analysts. So even if we still want to make it way faster for them, we can do separate table maintenance, like daily reports or weekly reports, kind of running nightly cron jobs and populating those tables, and then users can query those respective tables for high granularity details. If they want lower granularity details and every things, they can follow our standard table that we were maintaining and hit that table, and should be able to do that. So ultimately the final design is something it's going to look like this. So here, like I said, the cache to check for the impression ID, we introduced this, and here this ad placement service will help us in generating ad impression ID and sending it to the browser before we process the through a click browser when user clicks on it. And here we have the kinesis, which handles the stream of events from click processor, and then data reconciliation with the multiple approaches of batching, and then stream processing real time, so meeting latency and also the data accuracy. So this is what ultimate final design is going to look like, meeting the all the functional and non-functional requirements that we have discussed. Hope at least you learned something, maybe couple of new things, or whatever you can, at least the thought process that needs to be when we are put in a situation to solve the problems of this kind. Okay, now let's talk about a simple web crawler. How can we design such system? So as usual, let's try to go through requirements one point at a time. And first, before even going through requirements, web crawler, just a simple definition of that is, which really helps us to automatically traverse the web by downloading web pages and following the links from one page to another. So in real scenario, it's ideally used to index the web for search engines, or collect data for research, or to train models, LLM models, and monitor websites for changes and all that stuff. So that's the practical application of this web crawler system. So now let's discuss about requirements that we should meet while we are designing the system. The first requirement is we should be able to crawl the web starting from a given set of seed URLs. So seed URLs can be something like, URL of popular search engine, or popular news sites, or tech blogs, or social media platform link, just to get started with, depending upon the traffic that it is hitting the specific sites. We can just prepare a seed URLs and then start from that. So that is something we can crawl the web starting from those given set of seed URLs. And the second requirement is we should be able to extract text from that each page, the site, the URL that we are visiting, and store that text for later processing. It can be for anything, like I mentioned, for training the model, or indexing the content of the web page and all that stuff. So these are like minimal criteria that we should design system to meet. And others good to have is actual processing of text data once we store it in a database, like can be training a model or anything. And then good to have if our system can handle non-text data, can something like images, something like images, videos, or the content in the tables and all advanced stuff. If it is handling, then that's better. And handling dynamic content, maybe JavaScript rendered pages, like frameworks, React, or Angular, or Next.js, whatever they're using. How can we handle that dynamic rendered pages using maybe headless browser like Puppeteer and all that stuff? And also we should maybe good to have if our system can handle login required pages. So there will be some websites that needs exclusive credentials to access the content of their websites, and accordingly we can just crawl that and store the content of that page. So these 4 points are good to have, but we might not discuss in this, but these 2 points we'll try to discuss how can we achieve that. And coming down to non-functional, first the point that we should meet is we should keep our system as fault tolerance, and should be able to resume crawling without losing the progress of whatever the step that it failed at. Okay, so that's first point. And the second point is there will be a website with all websites will be with robots.txt file, and we should respect that whatever the rules are configured. And also we should not really overload website servers, frequently hitting them to crawl the content of that. So that is something we should respect. And coming down to scale, we should handle 10 billion pages, like a peak traffic. We should be able to support that handling of 10 billion pages. And our system, now the thing that we are trying to design, should be able to crawl this 10 pages, the scale that I'm talking, in 5 days. So how are we going to design a system such that it's going to help us retrieve 10 billion pages in content of the 10 billion pages in 5 days. And the other good to have is like security to protect from our malicious actors the services that we are designing. And if we can optimize such that cost of the instances and computation that we need can be adjusted within budget constraints, and adhering to compliances based on regional locations. If you are in EU region, there will be specific regulations that we should meet, and depending upon regulations, if we can consider, that's good to have. But again, this I'm just mentioning, and we will not be discussing in detail. So now that our functional and non-functional requirements are clear, let's since this is not a public user facing application, more of an systems infra, the services that we are trying to design, so we'll have a system interface. So let's first make ourselves very clear what is going to be the input and output of the application. So input is like I mentioned, it is going to be seed URLs to start crawling from, and the output is we should be able to extract the text present in those URLs and store it in our systems. So that is a simple system interface, input and output. And now let's just briefly understand the data flow of our application. So the data flow is first step is going to be take seed URL from maybe it can be frontier queue or whatever, we'll discuss more about that. And then once we have that URL, we need to request an IP address from that DNS, and once we get the IP, we will try to fetch the HTML content from that external server using that IP. And after that we have HTML, and we'll try to extract text data from that HTML and store the text whatever we extracted in previous step in our database, whatever the persistence layer that we're trying to add in this design. After that, once we store, we need to identify if there is any linked URLs from the text data that we tried extracting from HTML, and if so, I need to add them back to the list of the URLs to crawl. Basically, I should again append it to my queue, frontier queue, so that gets picked up. Yeah, so this thing is something that needs to be repeated until the URLs are empty or there are no more URLs to crawl from. Okay, so this is the rough data flow of our system, the take seed URL and these rough 5 to 6 steps. So I think this the data flow should be very clear of these steps that we just discussed. So since now we are clear exactly how the flow of our system is going to look like, let's try to discuss one point at a time from functional requirements as a high level discussion, and then take it from there. High level discussion. So like we just saw the flow in the above data flow, that is something I try to represent in the components here. Here the core components, like you see, we have the frontier queue and the crawler, the DNS, web page, and S3 text data. So if I talk about one at a time, frontier queue is basically this is where we'll try to put the queue of all URLs that we need to crawl. Maybe we'll start, like I said, with a set of seed URLs and add new URLs as we crawl the web. Here it can be any queue, it can be Kafka, Redis, or SQS, or whatever that we are comfortable with. And crawler, if you see, the main responsibility here we're trying to give it to it is fetch the web page, extract text, and extract URLs. And if there is any URLs, we'll just put extracted URLs back on the queue. And in this crawler, we'll try to receive domain receive IP addresses using the domain names by hitting this DNS, and that it's going to help us for DNS lookups and get that IP address, and using that IP address it crawls this web page content, and then executes this task, extracting text and extracting URLs, and accordingly it will store that whatever the text that was extracted in our S3 text section. And this is like the rough components, at least to begin with, the decent flow of achieving the requirements that we have drafted above. Yeah, so this whatever the things that are in our these are like in our control, and these are something like external that we are trying to rely on, DNS lookups, DNS providers, and web page that we are trying to crawl from. Okay, so let's go one point at a time, a deep discussion. The first thing is fault tolerance and resume crawling without losing progress. So here right now, if you see in the above picture, crawler is doing a lot of things. It is fetching, trying to fetch web page. I mean, first doing DNS lookup, and then fetch web page, extract text and extract URLs, and still if we had a logic of respecting robots.txt and all other stuff, it is trying to do a lot of things. So whenever we try to observe such things, the immediate thing that should come to our mind is we need to somehow break it down into smaller steps, so that we'll have a good point of checkpoint where exactly that we need to resume from. So after having observe that, we can split this one into two things. One is it can just do URL fetcher, and another is the URL and text extraction. So if we try to split it, this is how it's going to look like. So now the design is something in this way. We have separated into two things, the fetch and store web page. So this what this does ideally, whatever the raw HTML that we have, it will try to store in the S3 bucket, and once we have that S3 URL, it will put that S3 URL in our parsing queue. So that URLs, whatever we are appending into our queue, will be picked up by our parsing worker. So here, this is where actual text extraction and URLs extractions will happen, and accordingly here, once we pass in these S3 links, it will try to download the content of this S3 from this S3 bucket. So that is this first step, downloading HTML from that S3 link. After downloading, we do some processing of the logic, whatever we have to extract text and all. Once we have extracted text, again I'll save the S3 link for parsed text back to first to bucket, and then update our URL metadata for keeping track of even the text S3 link URL. And if we found any the link to another URL, I'll put back this onto our frontier queue. So now that this, if you see, it just does the job of looking DNS lookups and fetching that web page, and just saving the raw HTML, and parsing and all is something delegated to this workers, and this queue will make sure that these are decoupled and will be able to scale it independently. So this is something we can make this work to delegate or split the tasks and all. And even if something fails, this queue is something is going to help us handle that. Let's discuss like what if, like, first in the failure scenario that can be when we are trying to look up the content of the specific URL of a website, that might fail. So what happens if we fail to fetch a URL? So it can be mainly due to that website can be no longer there on the internet, or it might have moved, it might be down, or it might be slow or experiencing some downtime and all. So to confirm, we'll want to retry, of course, on failures, right? So how can we do that retrying on failures? So here are the couple of approaches that we can think of. What if we fail to fetch URL? One straightforward approaches can be in-memory timer, so that I'll try to wait for a few seconds and then again try to retry to hitting the same URL and see if I can still be able to access that URL and get the content of it. Ideally, this approach is something not going to work in just few more seconds. Again, it really succeed. And also, what if the crawler itself goes down? That's again the problem in this approach, in memory timer. So that is something that we cannot stick to it, or we cannot consider in this scenario. And another thing is Kafka with the manual exponential backoff. So now we'll try to maintain for whatever we are failing here, we will try to maintain separate topic just for failed URLs, and a separate service that reads from this maybe can be a failed topic or whatever the name that we can keep. And this way we could store the URLs in that queue, and it gets picked up by crawler. Again, we'll try to hit it again, the kind of retry. So we could store how can we do this is basically we could store the time that the next fetch should occur in the message itself. The one which I'm trying to put on the queue. So when consumer, meaning our caller, tries to read some message, it really waits until that time to retry. So this way we can make sure that we are retrying after a specific time, not immediately. And then a good way to think of to achieve this retry logic. And this is something, the downside is we should implement all this logic manually, whatever the retrying that we just talked about, of storing the time with the message itself, and then waiting till that time is reached, and then try to process it and all. So the straightforward approach is basically using SQS queue. I'm AWS simple queue service with exponential backoff. So by default it comes up with all of this retry logic and everything. So we'll have a configurable exponential backoff strategy out of the box. For example, there is a concept of visibility timeout in SQS. Let's say if one worker has picked up for that 15 seconds, that will not be visible in the queue, so that others crawlers or workers cannot pick it up. And after that it will try again for 2 minutes or 5 minutes and up to 15 minutes, and meaning it will put back after 15 seconds back in the queue, and some other crawler will try to pick it up and all that stuff. Even after it failed after 15 minutes, it will push it to dead letter queue. So again, this is good strategy to try up to like in n times, maybe 3 to 4 times, and then put it to DLQ. We don't want to retry infinitely, right? So I think this out of the box strategy is something that really helps us to achieve in the scenario. What if we try to fail fetching the URL? So that's how we can try to address conditions. And the next question can be like, what if the crawler itself goes down? The crawler, whatever that it was trying to handle DNS lookups and fetching the web page and then extracting raw HTML. This trade, the thought that really strikes is how we can just spin up a new one, and URL will still be in the queue. So basically here, why URL will stay in the queue is basically until our crawler worker confirms it will not be erased from the queue, whatever that we are using, since it is failed and we have not acknowledged it. So it will still be there in the queue, and it gets picked up by the new instances that we'll be trying to spin up. So here we can use either Kafka or SQS depending upon our comfort of the choice. So here if we say the Kafka scenario, it retains messages in a log and does not really remove unless a consumer or the worker really confirms that it was successful. If not, the new crawler or the worker will pick it up the latest offset thing, and then it will be retry that as usual. And in SQS, like we just discussed, visibility timeout is the concept that will really help us to help other workers to pick it up. So this is how it's going to look like after considering the above points heading. So here now frontier queue we are considering the SQS because we don't want to add our own manual retry logic and other stuff, and just want to use out of the box features that we get. And then there is a dead letter queue after retrying on failure with exponential backoff. Even after the 2 minutes, 5 minutes, the window that I was just specifying, we'll just put it into our dead letter queue. Maybe later some developer or we can just inspect what might be the reason, or maybe we need to have periodic purging logic which can remove from the DLQ so that storage will not be piled up. So yeah, this is a simple way of handling the problem that we just discussed above. And the second point that we need to address is respect robots.txt and not overload website servers. So just let's try to understand what is robots.txt. So basically that's a file where that websites really use to communicate with web crawlers. So it really helps or tells crawlers which pages they are allowed to crawl from that website and which they are not, and also it tells crawlers how frequently they can crawl this site. It might look something like this, user agent. So basically it allows all agents, and disallow, they are specifying that whatever the pages are present under slash private, it's something that you are not allowed to crawl from. And crawl delay is like 10 seconds that should wait between the consecutive requests that it's trying to make to that website. So yeah, what we need to do here, the flow ultimately is something, it should be in this way. Fetch the robots.txt file for that specific domain, the web page that we are trying to hit, and will try to parse that robots.txt file, so and store in our metadata db. So here we are trying to create a new table called domain. So for that domain and last crawl time and along with that robots.txt file that we have extracted, we'll try to store in this metadata database. So once we store that, and when something's when we try to pull URL off the queue, we'll first check the rules stored in that domains table for that domain. So if the URL is in disallowed list, so we will just acknowledge the message and move on to the next URL from the queue and all. If URL is allowed, we will check the crawl delay directive and see if it is something that we are meeting. Then if it's not passed, we'll put it back on the queue using the delay seconds concepts in SQS, so that it will be trying out after that specific time thing. If passed, we'll try to crawl the page and update the last crawl time for that specific domain. So this is how the simple flow it's going to be like, respecting the lookups of by the crawler in the metadata database using the domain and all, and the rest it's going to be the same. And the rate limiting, so is like, we'll really want to limit like one request per second for that specific website. So how are we going to do is, we'll try to add a simple maybe let's say here Redis to just help us store the count like maybe per domain. So we'll try to use Redis sliding window algo to check request counts per domain per second, and accordingly see if it does not reach the limit, and if it's not, we'll try to just hit it, or else we'll restrict for the time being. So, and the issues here, it might be of if several crawlers, meaning our workers, are waiting to make requests and simultaneously retry when the rate limit window resets. Okay, so they all try and one will succeed and the process will repeat. It's something like everyone is trying to do it at the same time. So how can we address that? Is something, there is a simple thing to address that synchronized behavior called jitter. So jitter is nothing but, we'll just try to introduce a random delay to each crawler's request, so that we'll make sure that they will not try to crawl the web at the same time. So that is something we can handle using this rate limit. Fine. So this way, maybe I might not have explained detailedly, but high level idea is the intuition is what I'm trying to give for this rate limiter and all, and to make sure that we try to do respect the industry limit of one request per second for a particular website and all. Okay, fine. So that's the thing. And the next point is, how can we scale to handle 10 billion pages and efficient to crawl 10 billion pages in 5 days? So this is very important discussion in this system now. So let's try to just discuss practical numbers. So assume average size of the page is 2 MB. Okay, so 2 MB. So typically AWS clouds, let's say most optimized network instance can handle about 400 gigabits per second. So converting it to bytes by 8 is something like 50 gigabytes per second. That's the throughput that we can send per second. So here we have 2 MB pages. So for this 50 GB per second, how many pages can we send is something 50,000 megabytes per second by 2 MB is something 25,000 pages per second is what one instance can process. And here we need to handle 10 billion pages, and this is like ultimate capacity of specific instance. We will never consider 100% capacity of a specific instance. So assume there might be network delays, response times and all that stuff. So we hardly consider 30 to 40% of that specific utilization of that instance. So considering here 30% of that, so 30% of this is so 25,000 is 7,500 pages per second. So now we know one instance can handle 7,500 pages per second. So 1 second 7,500 pages. So for handling 10 billion pages, how much time? So how much time is something roughly around 15.4 days. So if we use one instance and to process 10 billion pages, it takes 15.4 days for one mission. So but the requirement is we should achieve it in 5 days. So to achieve it in 5 days, how many missions is something that we need? 15.4 by 4, maybe I'm considering here 4 missions. So it gives us like roughly so we might need 4 missions, and if we have 4 missions we can achieve this 3.85 days. So we need 4 missions to reach a target of less than 5 days. Fine. So that's the number of missions that we need. And the common question here that's going to come is how are we going to scale parser workloads, like which is actually doing the job of extracting the text and identifying URLs, and that it's putting back in the queue. So here we can straight away leverage auto scaling containers like ECS based upon the pages that are further left in the processing queue, and you just auto scale using that ECS task. I think this way we can just scale our parser workers, and since we need to handle this much of a scale, the DNS also, I think it's important for every request with domain. We not always try to look for that in our DNS provider, because that will also have an hard cap limit of hitting request per time based. So instead of trying to hit every time, maybe we might cache that lookups in our Redis, and also not just relying on one single provider. We can try to use multiple DNS providers so that we can smartly avoid this rate limit cap that we'll have on specific DNS provider, and use round robin of hitting that specific provider and get the lookup IP address accordingly and all. So that way in the scaling, when we are trying to handle this much of a traffic, is something that we can think when it comes to DNS and all. So efficiency wise, first thing, we should make sure that we don't really crawl pages that have been crawled already. So how can we do this one? Maybe simple metadata lookup. Before trying to crawl, we'll just have a look in our metadata, see if we have crawled that before. If yes, we will not crawl it again. If no, we will proceed with the whatever the logic that we have. But the magic of the internet is this: what if different URLs point to the same page? For example, example.com, www.example.com, so it might point to the same page. And also it's really possible different domains to have the exactly same content. So here we cannot now just compare URLs to see if that has been crawled. So now we need to compare it even at the content level. So if that has been already passed and there is a content or something of that stuff in our DB and all. So here how can we do now? Make sure we do compare the content also. The simple and straightforward approach, ideally, which is mostly preferred, is this: we'll try to hash the content of the that specific web page and all, and store it in our metadata DB with index. So that now when we try to get pass new thing, pass it to parsing workers, we try to again hash that and see if there is a lookup match, and accordingly to proceed or not. Is that's something I'll just add a global secondary index in our metadata DB and add index column for that table. Other approach is something we can rely is using Bloom filter. So Bloom filter is basically, that's a simple probabilistic data structure that really allows us to test whether an element is part of a particular set. So then it's something we can straight away use the Bloom filter data structure in Redis and try to maintain this in the Redis and check if it is member part of that set which we already have in our Redis and all accordingly. But ideally this is an overkill, and mostly the preferred approach is this hash and storing metadata DB with index. And also one more thing really that we should be very cautious is, what if the website has a link to itself? So it's something that really there's a chance that it might put us in an infinite loop. So it is something that needs to be addressed also. So to avoid situations of this kind, we can add a concept called maybe depth field or something like that in our metadata DB. So if let's say I configure depth as like 3 or 4, so after meeting this number we will not try that URL anymore and then take on the next URL. So something that is how we can avoid this trap. So after discussing above points, so this is how it can be about the DNS cache we'll try to add to achieve this efficiency whatever we just discussed, and the additional fields here for comparing the content, we'll try to maintain a hash and also the depth to avoid the scroll trap. So that now I can just have a look up on the hash to just see if the content is already present in our sources. Fine. So that's the simple way of trying to meet this scaling to 10B pages and achieving in 5 days and all whatever we just discussed. So this is a simple design and not maybe might not be that intuitive, but it really gives us a good insight to at least to think in the direction of. And other things that we might really consider is, like I said, handling dynamic content and to to handle the React or Angular pages and all. We can do this using headless browser like Puppeteer to render the page and extract the content. And we might need to monitor health of our systems or of all our services. We can use something like Datadog or New Relic to monitor the performance of crawlers or parser workers and everything, and alert us if anything goes wrong. And there might be scenarios where web pages will have large files, and maybe that's a good sign to look for content type content length header to determine if the size of the file before downloading. If it's too large we'll just skip and not proceed with that web page. And and one more important point here, now we're considering it's just a one-time crawl, but what if you want to enable continual updates to our data source? Maybe we might plan to retrain the model every month, or our crawler is something we wanted to do, maybe index the search engine that needs to be updated regularly. So how can we at least think of is the rough idea. We can have a new component here somewhere, whatever we can name it as something called URL scheduler, that is responsible for scheduling URLs to be crawled. Okay, so rather than putting the URLs directly on our parser workers that we are trying to do now, we will try to put that URLs in our metadb first, and once we put in our metadata DB, the URL scheduler, the new component whatever we are trying to add, is something will be responsible for scheduling URLs by picking it from our metadata database by using some logic base based on crawl last scroll time, popularity, or something on those lines. So that's how at least we can think of or discuss on. So to sum it up, this is a simple web crawler, and we did try to think in the direction of at least addressing one or two important points in either functional or non-functional sections. Yeah. And all right, now let's discuss about Tinder or Bumble, a simple dating app that normally people use, so which everybody I think are familiar with it. What is the core functionality of it is basically it allows users to swipe right or left to like or dislike profiles, and mainly it depends on users location data and user specified filters preferences to show potential matches for them. So that's what the Tinder is about. So let's try to see how can we break down into requirements, functional, non-functional, and eventually take it from there and evolve into high-level system design of this systems. So requirements, functional, straightforward. User can create a profile with the preferences and the maximum the distance that he wants to find the matches nearby in. So yeah, so here, yeah, user can create profile with preferences and specify the maximum distance that we should consider when generating his feed or the stack, or that he can look over the profiles for. And the second functional requirement is the recommendation that we show normally in their feed should be purely based off their filters, whatever the preferences they have set, and also the location kind of which is in nearby, and respect the maximum distance that they have suggested above. And the other functional is requirement is they can either swipe left or right to go through each of the profiles. Swipe right is kind of liking the profile, and swipe left is kind of a no, disliking such thing. And here let's say now there are two persons, person A, person B. Person A has liked person B, and person B also liked the person A. Then there's a mutual liking between them. Once if there is a match between both of them, then we should notify those respective people. So how is it that we are going to do this? So this is these are like core functional requirements that we should meet while we are trying to design the system. Coming down to non-functional, we should strongly respect the consistency for swipes, meaning if a user swipes S on a particular user who already swiped S on that user, then they should really get a notification, something like consistency, that we don't miss even if particular user has liked specific user. So that is one standard thing. And coming down to scale wise, we should have a system such that it'll be good to handle 20 million daily active users, and on an average maybe 100 or 200 swipes per user per day on average. So we should support that these numbers. So that's how a system should be designed. So that's the second non-functional requirements. And of course to give best user experience, always we should focus on giving high throughput and low latency. So latency for the feed stack to be generated should be very less than 300 milliseconds. Kind of it should be in milliseconds, and it should give better user experience for them. And the other non-functional requirement that we should respect is we should avoid showing repetitive profiles for them, so that they don't get frustrated. Why is it we are showing the same profile which they would have already liked it or disliked it, right? So that these are like main functional and non-functional requirements that we should respect while we are designing system. So now that we are clear on this the functional and non-functional thing, so I think the identifying entities is simple and straightforward. So that is the second step, identifying entities. So usually just try to avoid specifying users, since now here it just represents both the user using the app and the profile that might be shown to user. That's why I just added. So that's the core entity of user. And another is a swipe, which is kind of like the expression that we should maintain, kind of, is it yes or no on a specific user profile. Like it can be a swiping user on a target user, and then match, is it like yes or no, something we should maintain of that kind. And the match, it's a connect between two users as a result of them both swiping yes on each other. So these are the like core entities. Maybe there might be more, but to achieve our above requirements above, this should do it, and it should be a good decent start for us. So now that the entities are clear, let's I think now we should focus on this is a end user facing application. So for each functional requirements, ideally we will have one API endpoint. So let's have a look at that API endpoint. So first point was about able to create a profile and then give their own preferences and all that stuff. So there's simple post endpoint, something called /profile, and here we can take their preferences like age minimum 20, max 30, distance should be in the radius of 10, and interested in, is they're interested in female, male, or both, and other stuff. We can collect a lot of the stuff that we normally want to have it stored in our system, so that we can give better recommendation or suggestions for them. So once this is created, you can go ahead and create a profile and all. So that's the first endpoint. The second endpoint is we providing a feed for the user. So of course this is going to be simple get endpoint feed, and we take in query params like latitude, longitude, and the distance that we want. There might be additional query params of user preferences which we might have already you used it in the server side, because that's something that it's going to be constant for a while, kind of app settings and all. So that's why I have not added inside in a query param. So if they provide this latitude, longitude, distance, and then we all have to do is return a object list of user objects, and then we will try to populate their feed. That's the endpoint. And the next endpoint is swiping. So for that specific user ID, the user, whoever is trying to swipe towards left or right, we should record that. So there we will get the user ID to which he has swiped for, and we should identify the direction, was it a right or left, and based on that we should update the decision to yes or no. So like these are the like core endpoints that we need for this system for time being to meet our requirements. So the endpoints are also clear. Now let's try to go into high level discussion of talking more on a one point of a functional requirement at a time. So going to this high level design, the first thing is user can create a profile with the preferences and specify max distance. So this is going to be a simple and straightforward. So maybe I'll just have a simple flow here that I have drafted. So here if I just show you, it's going to be simple few components. The client, the user interacts with the system through their mobile app or whatever application, and there is an API gateway, normal standard thing which routes incoming request of appropriate services. In this case it is our profile service, and this is simple service kind of we expose / profile endpoint. This handles incoming traffic from the API gateway by updating the user's preferences and all that stuff in our profile DB. So it can be, the schema can be something like name, art description, age preference, gender preference, maximum distance, and other metadata that we wanted to specify. We can just keep it here. The flow is simple, which I just specified. He just sends a post request to our API gateway, and that routes to profile service respectively, and this updates the user profile in our DB whatever we have, and the results are then returned to the client via API gateway. So that's the simple way of providing an option for user to create a profile and all. Now let's look at the second point. The user's recommendations is based on purely their filters and locations. So they should, whenever they enter an application, they should see the stack of profiles to swipe on, right? So serving up this feed efficiently is something, a key challenge that we need to try to address in this system. But let's start off with a simple simple approach, and later we'll see in a deep dives maybe how can we optimize this. So first, the intention should always to be build at least a minimal functioning system. Okay, so the easiest thing that what we can do is we can straight away query these profiles DB, that whatever we have, through the other endpoint, something called /feed or feed or something like that. The query might look simple, as simple as this. I try to select all the rows from this profile table from that DB, where the age is something, whatever the preferences, and interested in female, and latitude I'll just calculate with the distance that he has specified, and longitude. So whatever the results that we get using this query, we try to populate for that client, the user, in their feed section. So this is going to be a simple and the flow is as usual the straightforward whatever we normally see. Of course this is not optimal, and it's not even searching by location without even basic indexing or geospatial indexing, it's not even a very efficient, but it's at least a working this is working prototype or working system that we have at least in our hand. We will discuss about how can we address all bottlenecks and meet the criteria requirements that we have. The next point is users can swipe left or right. So this, once the users have this stack of profiles from the feed in the previous point that we just discussed, they're ready to now perform the swipes, either right or left. And now it's our duty to record the heat swipe and tell the user whether they have a match if they swipe right on previously matched users or not. Okay, so now we need to process the swipes. How can we do this? Is maybe it's easy to split the service, and so that we can independently scale. We know that according to this app's design, there is going to be a lot of rights to swipe services, and something that most of the all like users are going to spend most time on. So now that we know this couple of points, then it's obviously very the important to have a separate service so that we can independently scale it. So that's why we'll introduce two new components here, the swipe service and swipe db here. So this swipe service, what it does, basically we expose /swipe endpoint, and it process swipes and checks for matches using this swipe db. Maybe we can use for something like Cassandra. So given that the swipe interaction now is divided, and it's going to handle a lot of writes to the db, and there is going to be, let's say assume like we have 20 billion daily active users doing like 200 swipes a day on average. That gives us approximately like 4 billion swipes a day. So then this that many swipes to handle in a single db, it's something that is not manageable and maintainable. So we need to somehow partition the data across multiple partitions of the Cassandra. So how can we do that? Is something that we need to identify. So the key thing that whenever the volume of this kind is something that we need to handle, look for the key that we can partition by. So here the easiest looking the thing that we can do is partitioning by the swipe user id. So whatever the swipe user id, this means whenever we try to access, meaning let's say if user A is swiped on user B, then the access pattern will be very faster, because we can very confidently query a single partition for the data, since we are trying to partition by swiping user id, and we know which partition to look for, and then query just that partition and showcase the results to the meaning for say that was it a match or not. So the flow is something like this. The client sends a post request to this API gateway for this /swipe endpoint with profile id and swipe direction, either it is a right or left, other params whatever we need as params, and this API gateway routes to this swipe service. That's whatever the code logic that we have here, it routes to this swipe service. This swipe service updates the swipe data swipe db, which in our case is Cassandra, the right partition. Now this swipe service, whatever it is, the logic that we have, checks if there is an inverse swipe, like user A liked user B, and now it will try to look for the inverse check, if is there an entry for user B liking user A, and it will check in our the same partition of the Cassandra. If it is so, it will return a match to that specific user immediately. If not, it will not return anything. So that's the simple way of handling swiping left or right, and adding this new two components, swipe service and swipe db. It can be anything, since we are supposed to handle huge thing, so that's why we are choosing the Cassandra and all. And the next thing, that is, if they mutually swiped S, then we should send a notification. So how we said that we can send a notification to them. So here the only the challenging part is, let's say that there are two persons, person 1 and person 2. So let's say that the first person who liked the other person is person 1, and the second person, let's say person 2. So person 2 liked it, and we know we are doing inverse lookup, and then immediately we can notify him, yes, there was a match of that for you before. Now we are saying that there's a match. Now you can either chat or go, or whatever the next steps can be, something can be done. How can we now notify the first person immediately? That is something is the challenge for you here. Because they might have swapped on that person 2 weeks ago or months ago, or don't exactly or the days. So we need to send them a push notification informing that they have a new connection waiting for them. So to do this, what we'll do, we'll try to rely on external notifications, something like APNS, which is Apple push notification service, or FCM's Firebase cloud messaging thing. And accordingly, we will try to ping that notification, and then that sends a push notification to that respective client. In this case, it is person 1. So just recapping, the flow is something, it's going to be simple as this. Sometime in the past, the person A swiped right on person B, and we persisted this in our swipe DB. Now person B swipes right on person A. The server checks for inverse swipe and finds that it does exist. We display match to that person B immediately. And to notify person A also immediately, we need to rely on sending push notifications via this FCM or APNS. And this is how we are going to achieve that, sending a notification mutually if there is a match. And this system will try to handle the fourth requirement that we have. Now that we are clear at least on basic functional requirements of having simple separate components to handle each of the requirements, and we meet basic needs. Now let's try to focus on the non-functional things, kind of which really helps us to evolve our design to handle scales and the latency and other numbers that we normally have drafted while starting this design. So going to this deep dives, first thing is consistency for swipes. The current problem here is clearly stated here. So assuming both persons swipe at the same time, let's say like they try to swipe at the exactly same time, person A swipe hits the server, our server, and we check for inverse swipe, there's nothing. And person B also hits the server at the same time, and we check for inverse swipe, there's nothing. So we say person A swipe on person B, and we say person B swipe on person E, and they both will never know that they have liked each other. So that is something that we need to address, this consistency. So how can we address the problem of this kind if in our system? So let's just simply discuss the approaches. First is database polling for matches. So what we do here is, like, maybe let's say we try to poll the DB every few minutes or few seconds and see if there is a match, and then we accordingly notify them using our push notification. But the downside of this here is it is not immediate, and it's going to frustrate the user because we are not giving best user experience, and a lot of latency issue, and they will the engagement on our platform is of course is going to go down. So that is why this approach is something it's not preferable. The other approach, when it really comes to consistency, the thing that we really need to think about or should strike us is transactions. So here we are using Cassandra. There is a concept of lightweight transactions in Cassandra, which uses Paxos census protocol to provide us decent consistency for specific operations. Within the only downside is it can only provide consistency within a single partition, but not across the partitions. So with the given scale that we have, single partition cannot really hold our traffic, and this is something we cannot rely on, and so this is also not preferable. The other approach, maybe we can think of at least a great solution or something that can address is sharded Cassandra with single partition transactions. So what we do, like we saw in the previous point, there is a single partition transaction automaticity in a Cassandra. So now how can we leverage that and see if we can leverage that advantage? So what we do, we'll try to first create a table with compounded primary key. Here primary key can be user pair from user to user. So I'll try to create this table with user pair from user to user, and the direction and the created and all stuff. This is going to be partition key and this clustering key, and the key is going to be something like smaller ID and larger ID. So when a user swipes, we create the user pay key by what we do by sorting the IDs to ensure consistency. So here we sort IDs, let's say A to B and B to B are in same partition. We sort this ID and we return this the user pay that we have, and I'll try to find that pair and then handle swipe. So we do operations automatically in the same batch. I'll try to insert into swipes values, whatever the direction from size and all everything that we have. So this approach is quite effective because Cassandra single partition transactions provide really atomistic guarantees, and that is what we are looking for. But the challenge here is over time the partition size can grow significantly, and which can affect performance, meaning here high active users could create hard partitions that receive can receive uneven or disproportionate amount of traffic. So to address these issues, again we need to have some strategies to do robust cleanup, so that we archive or delete old swipe data, and preventing partitions from growing unbounded, and making the partition even across the old sharding. Okay, so I think that is this approach is about. And the ultimate approach that we can always rely on is using Redis for atomic operations. So Redis here, it's actually a better fit for consistency requirements that our swipe matching logic requires. So for durability we can still have the Cassandra, but for the real-time match detection we can use Redis. So what we'll do here, the same as before what we just discussed. Now we need swipes between the same users to land on the same shard. So we can achieve this one by creating a key of this, something like this, like swipes 1 2 3 4 5 6, here 1 2 3 swipe and 4 5 6 swipe. And I will try to again get the same key in the same format and handle this swipe. And here we'll try to use the script. Here I'll try to set first thing whatever the thing that we have, and the second thing redis.call function, and we'll try to execute this finding at the other swipe using a Lua script, like which one to look for and all. And now after we get this other swipe, we'll just check if the direction is right, whatever the input that we received for this handle swipe is right, and the other swipe is also right, then that is a match. And then we'll create a match and maybe notify or something like this. So this can be a better approach to prefer. And after considering this Redis for atomic operations, the updated system design is something it's going to look like this. This swipe service now talks to this Redis, which is a swipe cashier, whatever we can call it. So, and to see if there is a match or not, and the everything lookup logic goes here, and the problem that we stated here initially will be addressed by this Redis, because we're trying to handle this automatically. So this is how we can try to address this point of consistency for swipes, no matter what the scale of our application is. So in here it's about the 20 million daily active users. And now how can we achieve the low latency feed stack of less than 300 milliseconds, or in some milliseconds? So let's try to achieve or discuss, brainstorm few approaches. First is the using of index databases for real-time querying. So index databases can be something like an OpenSearch or Elasticsearch, which are really optimized to handle this querying of data. Or else we can implement geospatial index on Postgres, or if you don't want to use Cassandra and do something on that scale. So if we have this the Elasticsearch introduced, so here now whenever we wanted to show a feed, we will try to fetch that feed stack from this Elasticsearch and then showcase it to the users. And since anyhow these systems are optimized for read heavy thing, and it can handle the scale and all, the only downside, the problem, the challenge in this approach can be something like that: the consistency that we are supposed to maintain between our profile database and Elasticsearch. So we need to implement something like change data capture technique, and then so that they will be synced, and we have the data, not the stale data, every time the user is trying to check out his feed. And Elasticsearch is something really optimized for read heavy, not write heavy, meaning here we are trying to flush or sync between this profile and Elasticsearch frequently, meaning there is a lot of writes are happening onto Elasticsearch. So that is something that we need to even be cautious about. Maybe we can try to batch or request or flush every on time windows and all. Again, that's a trade-off that we need to make depending upon which criteria or requirement is way high priority than the other one. So this can be a simple approach that we can take to achieve the minimal latency. The other approach is in the pre-computing the results and caching them, so that we can heavy lift that all calculating things, wait in advance, and then showcase the user whenever he's trying to hit his feed or so. So here what we do is we have here the cache. What I'll do, will somehow introduce some cron job where it will try to do some logic of fetching the entries from profile db, and then maintain a cache for that user's feed in our thing. And now this profile service will try to query from this cache and then showcase it to users. So this, by serving this cache feeds, users experience will be quite good and immediate access to potential matches, and it really enhances their satisfaction. It can be maybe when can we schedule this cron job to populate our cache. Can be during night times or peak off peak hours times and all those things. That way we can address this. So again, the challenge in this case is highly active users, who are swiping very aggressively, and they are very active, and they're spending a lot of time on our application. Then their cache will exhaust very quickly, because we calculate only few things for specific user. So if again the cache is exhausted for specific user, we'll have to again do expensive querying to this profile db, and then fetch all of that related user details and showcase it to the user. So this is something again we need to handle for such very highly active users if we choose this approach. So the ultimate approach is going to be a hybrid approach, meaning the combination of this pre-computation and index database. So whatever I discussed in 1 and 2, we'll try to combine here. So meaning we'll have this Elasticsearch also along with the stack cache that we have. So only thing is when to choose which approach for whom. The parameters that is going to decide to choose Elasticsearch as stack cache are this. So basically what should be TTL for cached profiles, and what should be the actual profiles that we are going to cache, and who are the set of users who we are caching feeds for. So these are all the params that we need to keep into consideration, and see which one is the best one to suit for, and then accordingly route them to either Elasticsearch for pulling their feeds and all that stuff. Is something we can do this. The problem here is always going to be, how can we avoid stale feeds? The challenge can be easier. A user suggested in a feed might have changed some locations, or he might have moved to different neighborhood or city, and is no longer close enough to fit the feed filter if we are trying to show it from the cache. So that now that user suggested in that feed might also that the first point whatever I just mentioned can be one scenario. The other scenario can be the user might have changed their profile preferences, meaning they have changed interest now, and there no longer fits the feed whatever we already calculated for him in the feed. So that is something, how can we avoid this stale data and all. So this is all going to depend on this, like what should be TTL. So ultimately we should try to have a TTL less than 1 hour or so, and see now which profiles needs to be cached and all those things. And also there might be few user actions that might really lead to stale profiles in the feed, like user being served the feed changes, whatever the feed that we are serving either from Elasticsearch or stack cache, you might change their filter criteria, resulting in profiles whatever we cached in stack cache or Elasticsearch getting outdated, and still we are showing that. So that becomes really stale for him. And yeah, again if he changes the location instantaneously very frequently, then the whatever the things that we have is again going to become outdated. So those are the edge cases and the situations that we need to really consider when we are designing a system of this kind. And now okay, so at least this helps us achieve the latency of whatever maybe some few hundreds milliseconds thing. The next the point is, how can we avoid showing repetitive profiles so that they never get frustrated of either whatever the profiles they liked it or disliked it, and not showing in their feed again and again. So the approaches again here can be simple db query and content check lookup. So here what I'll do is simply we can hit the same feed builder service, querying the swipe database, and just check if that user has been swiped before or not, and accordingly I'll just do a content check and then try to populate the feed for him. But the problem here is over time the contents lookup might really get expensive, maybe because there might be a lot of users IDs written, and then we'll have to do a lookup against all of that. So this is something it's not feasible given our requirements. The other thing is caching and debugging query and like contents check logic that we have. So here what we do, the yeah yeah here what I will do is managing, we'll try to rely on assuming that user is using single device only, maybe this particular app or not. Okay, so then I will try to leverage the storage system on their application, kind of like client side storage, so that this can really help us to filter from the server whatever that we are trying to show him based upon already the things that he has swiped or not, and then accordingly filter and show it to him. So here what we are trying to leverage is client as part of our system. We can with the assumption that user is only using this app on one device, so therefore we are trying to leverage this client itself as a place to manage and store data. It can be something like this. There is an initial stack of profiles. Imagine like users swiping through, let's say, 100 or 200 prefetched profiles. When a user gets to profile 150 or 160, 170, the client can what it does now, it can ping our API gateway at the backend to generate a new feed for that user and request that feed once the backend is done generating the feed. And now we'll try to filter out profiles that a user eventually swipes on, so whatever that we stored in the client. So something, this might be trickier, but we can leverage mobiles memory storage and all that stuff and try to achieve this. Or the other approach can be, this is kind of overkill, but we can also have some bloom filter along with the Redis. There is a bloom filter data structure readily available in Redis. We can leverage that and do a quick lookup of like that user is part of that set or not. What we'll do, like ideally this is applicable for users with large swipe histories of storing them in a bloom filter. So if user exceeds the swipe history of certain size, meaning the size that would make storage in cache very uneven, and then we can build and cache a bloom filter for that user, and then we might use that bloom filter while we are trying to filter, while we're trying to populate the feed database. So this is something that we can consider on, and then keep syncing up our profile service link up, and also between this when we do the calculation, the cron job for this putting it into bloom filter also. Something it might look like this, but this is something overkill. I think the better approach can be some the one that we have, simple cache db query lookup should do it, but ultimately the final design is going to look like this, something like this. So these are the requirements, a couple of them that I wanted to discuss for this use case. Maybe not that clear, but should really give you some insight on how to approach problems of this kind. Okay, now let's discuss about Leetcode. We all know what Leetcode is, a simple platform which helps us to prepare for coding interviews, and it provides a vast collection of coding problems ranging from level easy to hard, and also we can participate in coding competitions and all that stuff. So that's the what at high level Leetcode offers. So let's try to maybe break down into 4 functional and 4 non-functional requirements, and then try to see how can we build a system that can meet those requirements. So first requirement is simple and straightforward. User should be able to view list of the problems on the platform. So that's the first requirement. And then after having provided them with a list of the problems, they should be able to view specific problem details and all those details. So here that is the second requirement, view given problem and code solution in multiple languages and all. So that's the second requirement. And the other that he should be able to perform is he should be able to submit solution and get instant feedback or the response or result that he wants. And whenever there is a coding competition, we should provide a live leaderboard for that competition, so that they can see who is leading and all, with what score and how many problems has they solved and all that stuff. So these are the basic functional requirements that we will try to target to fit into this design that we'll be discussing. When it comes to non-functional, we should give high priority to the availability over consistency. And the second point is we should support isolation and security when running users code, whatever they have submitted, and see how can we isolate them apart from our code services, whatever we are building, and ensure that it is not affecting our code bases and all. So how can we make sure that is going to happen, is that the second the requirement. So the third one is, of course, whenever we are designing any system, we should provide responses in very less time. So that is the low latency whenever they return the submit their code. So the response should be within the less than 5 seconds, whether all test cases passed, which failed, and which succeeded and all that stuff. And coming down to scale, we should be able to handle a decent 100k users for competitions and all. So yeah, that is the simple non-functional requirements points and all. And so we have this functional and non-functional points now clear. So once that we are clear with the requirements, as usual, we know the core entities here by simple and straightforward. We can apply understand here itself. The problems is going to be one core entity, and the submission, whatever the he's trying to submit, that is going to be one thing. And then the leaderboard that we need to store for competitions and all. So those are like 3 core entities. So problem, which standard storing problem statement, test cases, and expected output, and all those details, whatever it needs, it's going to store that. Submission, this will store user's code, whatever he has written or submitted, and result of the running the code against the test cases, whatever we had for that problem. And the leaderboard is just straightforward. Is going to store the leaderboard stats for that specific competition. So these are like roughly the core entities that we'll be dealing in this system. And now that we are clear with the core entities, we need to since this is user facing application, so each functional requirement point is going to be something like an endpoint that we need to expose for our users. So endpoint, first is requirement was should be able to see list of the problems. So it is going to be simple get endpoint, something like /problems, maybe paginations at page 1 limit 100, and we'll give some partial subset of problem entity, and that is going to be list of problems, so that they can see in the home page or whatever dashboard that they are viewing. The second is they should be able to view the details of that specific problem. So this given the problem ID for this endpoint, again it's going to be get endpoint, and which language they wanted to view, and we will just showcase the problem details and all examples, and then the code in that specific language. The other endpoint is to submit a solutions. So once he has solved the problem and whatever the code he has written, we should provide a way for him to submit that code, so that it can be evaluated against our test cases. So this is going to be post endpoint because we need its code and the language in which he has written. So post here for that problem ID and submit. We will have accept the body, the code, whatever is written, and the language in which he has written. And the output of this is going to be submission entity. And this is going to be something simple and straightforward. Yeah. And the other one, whenever there is a competition, to view live leaderboard and to see who is leading and all the stuff. So this can be a simple endpoint as such, leaderboard and competition ID and pagination details and leaderboard entities what will be trying to showcase to them, and they can see the results and all. So maybe this can be very high level and it might not be in detail, but this just gives the list of the endpoints that the system needs at least. Okay, so now we are clear on endpoints and good. Now let's try to discuss one point at a time in our high level discussion, focusing how can we have simple design flow, how it's going to be. First point is he should be able to view list of the problems. So here it's a simple see, given the scale of the applications, ideally this is not that big of a system that we'll be designing because it's hardly thousands or a few hundred thousands of users, and simple client server architecture should do it. And it's something that we go with microservices, but that's for a bigger scale of a platform, but this should be able to handle it. So here we have a simple flow. Here we'll have a client and he will try to hit the problems endpoint through our API server, and this will talk to our database. Maybe it can be DynamoDB, PostgreSDB, whatever the thing that we are comfortable with. And we have here entity ID, description, code stubs, test cases, many data, metadata, or the other fields that we wanted to, and it might be something of this kind. Okay, the structure or something, it can be a schema of the problem, can be something like this. So core components here is simple. The server, API server will simply handle incoming requests from this client and return the appropriate data from database to this client, and so that he can showcase accordingly. Yeah, so this is like simple flow which provides a way for a user to view list of the problems. And now coming down to the second point, view given problem and code solution in multiple languages. This also, it's going to be straightforward. Here same flow. All he is going to do is hit with the problem ID, because we'll be when he clicks on that specific problem, we'll get the ID, and accordingly we'll get the more details of that problem schema and provide it to the client, and it will showcase in that specific page and all that stuff. So this is also going to be very simple and straightforward. And the second point, whatever we have. And now the third point is submit a solution and get instant feedback. So this is something, the place that we need to spend some time and discuss on it. So when user submits a solution, where and how are we going to run this code is something that we need to question ourselves and discuss a couple of approaches and brainstorm, and then narrow down to one final approach that we wanted to choose. So if let's go with the naive approach, directly run code in the server. So whatever he's submitting, we'll try to run it our own API server, and then see we can run against all test cases, and accordingly we return whether it has passed or not. This is never recommended. Why? Because running code is very CPU intensive and it can really crash our server. So we don't want to run it our own server. And also running code in the same process as our API server, we are not isolating it, and it's something that we have it in our non-functional requirement, and we should expect it. And it is also kind of providing or exposing to client that they can write a code which can delete all of our stuff and all in our API server. So this is something, it's not recommended, and this approach is not a choice for us. The other approach is running code in virtual machine. So this, how does it look? So basically when he tries to submit, so we'll have a VM to run the code whatever he has submitted, and then see here yeah, so this is isolated environment which really runs on top of our own server, and can be easily reset if something goes wrong. So I think this is decent approach. Even if the user's code crashes that VM, it's not going to affect our any server. But the challenge here is it's resource intensive and can be slow to start up and all that stuff, and because it will have complete OS stack, which we really doesn't need it. Only we need libraries components that needs the specific code to run. So this is something good to have but cannot go ahead with. But the ultimate the solution that we might prefer is running code in containers, that is a Docker. So here what we'll do, we'll try to run the user code in the containers. Okay, so here we'll have maybe a language specific container like Python runtime service, whatever the dependencies that Python needs, we'll have it on one service. Same language specific, we'll try to spin up like this TypeScript is C++ and all that containers that we need, and like this way we will try to isolate and execute whatever the user is submitting in those containers. So the difference between VMs and containers, like I said, VM, it really includes full copy of an operating system, like application necessary binaries, libraries, making them larger in size and slower to start. But whereas compared to containers, they basically share host system's kernel and really isolate the application processes from our host and the like from each other. So it will have its own dependencies, libraries and binaries, but not full OS, and that's what really makes the Dockers as lightweight, and that's the only like major difference between them. And here, yeah, this is something, yeah, the flow is going to look like something like this. If we don't want even Docker container, there are other approach you can go is using serverless functions. Maybe we can spin up our own the Lambda functions for specific languages and then try to execute that. But since we want like maybe more control, and also there might be a scenario that we want to avoid cold start, because Lambda functions really have a cold start issues, so it might take some time to spin them up and run the code. And also if you wanted to run bit longer jobs, container is something that is preferable, so it's up to you. And the ideal flow here is going to look like this. The API server will receive the user's code submission, the problem ID, and it will send it to appropriate container for language whatever the he has specified. Then the isolated container runs the user code. Let's say if it's a Python code, and it will run in this Python runtime service and returns the result to this API server. And then this API server will store the submission results in database and return the results to the client. So this is going to be a simple flow running code in containers, Docker. So that's how we decide like way to run our code, and then that we try to though it's still not instant, but we'll discuss on that as we go deep diver. But that's one place to run our code. So let's discuss next point. The next point is live leaderboard for competitions. So here now what he should be like, maybe we can have some assumptions. Maybe the competition can be like 90 minutes long, like 3 problems, up to 100k users. So scoring can be like number of problems solved in that 90 minutes, and we'll rank by like if there's a tie, who solved it first and all that stuff. Maybe that can be something like that. So the easiest way can be something like we directly have here what can we do is basically we'll try to just query, maybe have this endpoint something like this, a leaderboard and a competition ID, and we'll just query the submissions table, whatever we have ID against this competition ID, and for all rows, and then group by user ID and ordering by number of successful submissions, and then we'll try to show. That's the new, at least direct SQL querying normally that we do, and showcase it to the users. So in order to make sure it's fresh, the client needs to request the leaderboard again every 5 seconds, meaning every 5 seconds it should hit our DB with that the SQL query to pull from the submissions table and showcase it to the result. So tying it all together, it's a simple. So user requests the leaderboard via this endpoint, and API server initiates a query to the submissions table, whatever we have, and depending on the ranking by the score, and then it will return the leaderboard result to the client, and client again will repeat this process every 5 seconds to ensure it's up to date. So that's the thing. I know this is adding a significant load on the database because every 5 seconds we're trying to hit it. We'll discuss how can we mitigate this. At least now we have a decent working functioning design for our requirements. So let's try to go deeper for each of the non-functional requirements. So first of all, how do we guarantee isolation and security when running users code? So here it's a simple and straightforward. It's not that highly needed to go very deeper into it. All we will try to specify is anyhow we are trying to run separating the running in the Docker, so that's something that we are already isolating it. And to make it more secure, we will allow only read only file system, meaning we'll prevent users from writing to the file system. So we can mount the code directory as read only and write any output only to the temporary directory, which will be eventually deleted after a short time. And also we'll add strict bounds on CPU and memory usages, so that we prevent users from consuming excessive resources. And the other thing is we'll have standard limit for executing their code, like maybe 5-minute timeout or anything, so that we avoid like infinite executing and then starving the resources for the user, something like that. So that way we can ensure. And if you really wanted to even give limit to network access and all, we can let's say if you are using AWS, we can use virtual private cloud for network controls and also do not allow system calls. Maybe this at high level, if we know at least what needs to be done, maybe a couple of few points and all, then we should be good. And this is a standard way of isolating and providing security whenever we are trying to run user code. And that's the one point that we are going to address, this isolation and security. And now let's discuss about how can we make that fetching leaderboard. Now we were kind of like pulling a db every 5 seconds or something like that to pull the stats from submissions table. So it's something that's not really efficient, because it is putting a lot of load on database. So here this polling with database queries, that's the approach that we have currently, which is a naive and we really don't want to go ahead with. So what can be the other approaches? Basically the caching with periodic updates. So what we do is now we'll try to introduce a Redis cache in between the database and API server, and now the cache will be updated let's say every 30 seconds by querying the database. So whenever clients wants to see the results, now it will not hit the database, but through API it will hit the Redis through API server and will show. So here it's a significant improvement over the load onto the database, it's a something still it's not real time. So basically users need to still see some stale data and wait for a few seconds to get the data. So to see real, maybe kind of feel real-time data, we can go with Redis sorted set with the periodic polling. So what it's going to be basically when a submission is processed, basically when submission is submitted and processed, both the database and Redis sorted set are updated. So client will try to now poll the server every 5 seconds for leaderboard updates, and the server returns the top n users from the Redis sorted set, which is really fast and requires no expensive database queries. So to give an high idea what is Redis sorted set, it's simply a in-memory data structure that really allows us to store and retrieve data based on specific score. Here score can be the number of problems or the timestamp that we have. So something the key can be, we'll try to maintain in this way in our Redis thing: computation, leaderboard and computation ID. And we'll have something like endpoint computations, computation ID, leaderboard and query like top 100. And whenever we're trying to put into a Redis query, we'll try to add it in this way: computation, leaderboard, computation ID, the score and the user ID of that score. And when we are trying to retrieve pull from Redis, we'll try to again query 0 to n-1 with score. So this way it will be by default maintaining in a sorted order of the highest to lowest score. So we don't have to do additional processing and all, we'll get instantaneously the thing. So the additional Redis sorted set that we really provided, it's going to give us significant advantage of like kind of it will be a real time showcasing results to the users. So ideally Leetcode does this. This is how it's going to update leaderboards. So the 5-second delay of hitting this radius is generally acceptable for most users, because maybe we might have a strategy like, at the beginning of the competition, maybe we might do like every 10 seconds we might update a leaderboard, but to the finishing of, like, let's say 10 minutes is left in the competition, then we might do the polling kind of like 2 seconds, so that we do a frequent updates and all. So something of that kind of strategy can be added, because we know the competition is of like 90 minutes and all that stuff. So this way we can really go ahead with this approach, and then address the real-time leaderboard updating, and like client will be polling based upon like whatever we just discussed. So with this we'll be addressing this leaderboard more efficiently. And now the other thing is, how can we handle the scale that this needs, the 100k users for competitions and all. I think this should be very straightforward, because whenever we talk about system designs, first thing is we can go with the vertical scaling. So let's talk about vertical scaling, why it's a very, very bad approach here. So assume, like, the rough number, like we have 10k submissions at a time, and for each submission problem, let's say we have 100 test cases, and each test case may take around, let's say, 100 milliseconds to run. So each submission is 100 test cases and 100 milliseconds to run, so takes around 10 seconds to run. So we have 10k submissions at a time, and that is basically how many test cases? 1 million test cases, and it takes around 100,000 seconds, which is roughly 27 hours, and it needs this many CPU cores to run. So in reality, the powerful AWS instance itself has only 128 cores. So this is something that is not at all preferable given the scale that we need to handle. The other thing is, we can simply go ahead with the dynamic horizontal scaling, the standard things which in any cloud, it really these days they provide us, like scaling our containers using ECS or ECS auto scaling, and then scale up accordingly the language containers, whatever we have using AWS Fargate or whatever the stuff that we have. Or else we can introduce a queue, horizontal scaling with a queue. Maybe here the approach is something like this. So if I narrow it down and showcase the thing, and now whenever a user submits a code, we will try to put it in our AWS SQS queue, and that will be picked up by the worker, and accordingly it will delegate it to respective based on the language the containers that we have. And once that is done, it will update back in the API server, and this will update our primary database and gives to this. So here it is not instantaneous, and it can be asynchronous, and so they can do simple polling, because this is going to be significantly faster. And given that whenever they know the problem ID, so they will just try to poll like maybe few milliseconds, and then polling like 3 times, 5 times, and then they should be able to get the results. And using this check/id and polling to this API server, they should be able to go get the results of the code that they have submitted. So this way we try to make it is asynchronous, and even try to handle even if something code submission has failed, and we give them assurance that we do retry by putting it back, or maybe exponential strategy and all visibility timeouts that normally SQS provides. And we ensure that we do handle scale, and also make sure the submissions, whatever they have done, is taken care. So this way we might prefer this design. So, and next is handling running test cases. So how do we actually run test cases? So the test cases, it's something that we don't want to write test cases for each of the language. So it should be some standard JSON file or string format that we'll be writing, and then that should be used to execute all of the test cases in whatever the language the user is preferring. Maybe we need to standardize serializing inputs and serializing outputs, so that way we one test case passing to respective language runtime should be able to pick it up and process that. So maybe typical test case flow can look like this. So we'll define test cases, one universal set per problem can be JSON format, and then we'll try to serialize that input output data, like standardized input and output can be arrays, trees, or whatever it is. And then we'll try to select language specific code handles like whatever the input and output that we have, and compare. After that, we'll just set up container and load user code, and then help profiles, whatever it needs to execute. And once we have everything that we need for the specific language. Whatever the input that we have, we'll try to deserialize now. So meaning we'll try to convert that JSON, the string that we have, into specific objects. It can be tree node and other things that we have, and then we'll try to run the user code and do that stuff, and everything, if whatever the logic that we have, we'll execute it. And after everything is done, whatever the output that we got, we'll again try to serialize it to standard way, result back to JSON and array format, and then we'll try to compare results against whatever the first JSON that we are maintaining, and then accordingly we'll see how many passed or failed to the user. So this is how it's going to be typical flow of testing the test cases for a specific problem. And ultimately this is going to be our final design, and which we talked about, and this is a simple a Leetcode system design that really meets the functional and non-functional requirements that we have laid out. I guess this might have given decent idea. And yeah.
All right, let's discuss now about how can we design a simple online auction system. So we just know what is online auction. So basically, that lets users to list items for sale, allowing other users to compete by placing increasingly higher demands until maybe the auction ends. At the end, the highest bidder takes the item home. That is the one who is going to win the item. That's the simple online auction system. Okay, now that we clear at least high level broader definition for online auction, let's try to break them down into functional and non-functional requirements as usual. So listing down the requirements here, the functional things. First, there are 3 points that we need to take care of. So user should be able to post an item for the auction. So basically the item that they want to sell for, and the other configuration can be what is the starting price they wanted to start the bid for, and also the end date that the item is being auctioned for. So that's the first requirement when we are trying to design a system, is going to meet this a simple the first requirements that we will be trying to hit. The other requirement is they should be able to bid on a specific item. So let's say user has listed an auction, and then so the other users now who want to buy it, we should provide an option for them to bid on that item, and also have a strong validation logic of like bids are accepted only if that value is greater than current max highest bid that we are holding in our system. So that's the the second requirement that we should meet. The other thing is the user should be able to view auction details completely, and including, so basically what is the current highest bid and all, so that it will be properly notified to the users of what is the highest bid, and then they can see real time data being updated. So those are the three functional requirements that we should try to meet. So okay, fine. So now we are clear at least on the functional requirements, and what should be the other non-functional. So maybe we can add other points, like they should be able to search for items, maybe filter items by category, sort items by price, and then maybe view the auction history of that specific item and all. But they were good to have, we can just stand and discuss on that, but right now I'll just focus on these 3 points. Coming down to non-functional things, the first priority is basically we should give a strong consistency for bids, so that basically whenever multiple users are trying to compete for that item, they see the same highest bid, and there's no stale highest price that we are trying to show for specific users also. So that's something very important. And the other thing is fault tolerant and durable, meaning that we really can't afford to lose or drop a bit, and and that really makes the users lose the trust on our platform. So if a person has placed highest bid, and then or the answer to his question if is something like we um, drop that bid, it's something that lose complete trust on a platform. So something it should be very fault tolerant and durable. That's the second non-functional requirement that we should try to take care. And then the third one is basically real-time display of current highest bid. Of course, they should know what is the highest price currently the item is being bid for, so they can choose the higher amount that thing. So it's, if multiple users trying to bid for the specific item, it's something it's our duty to keep updating in real time the max bid value. And then talking about the scale, it should be able to handle 10 million concurrent auctions at the same time. So that's the system that we should try to build in like. Okay, fine. So clear on functional or non-functional, the things that we have something on these lines. And yeah, now we are clear. We can go to the second step, which is something just trying to identify the core entities that we have based on this functional and non-functional requirements. So the core entities is basically straightforward. The auction, which represents an auction for an item, it could include information something like starting price, and then auction in date, an item being auction, and all that stuff. Other metadata fields that we wanted to maintain, this is the place that we can add in. Then the item, so this is just the represents an item being auctioned. Again, it could have information like name, description, image, links, and all other stuff that we have. And the other entity is bid, which actually represents a bid on an auction. So kind of can be, it holds amount of bid, the user placing that bid, and the auction that's being this bid is upon, and all those things we will try to maintain in this entity. And user is basically straightforward, who just represents the user of the system, who either starts an action or bids on an action. So these are the core entities for time being: auction, item, and bid, and user. And if we need it, we'll try to add as we go deeper into our high level discussions. So field level discussion also we'll try to add when we are trying to discuss one functional requirement at a time. Right. Okay, fine. The core entities are logged in, and we are good. Let's now identify the system interface or APIs that we need to expose it to the user. So I think it should be very straightforward once we identify the options and then the functional and non-functional requirements. The first thing is we should provide an endpoint for a user to create an auction. It can be simple as such, post endpoint slash auctions, and maybe it might return auction object and item object. It can be something like this. The item they want to create for that auction, and then start date, and then end date, and what is the starting price, or something like this. So this is something that we might expose it to the users to create an auction. Then the other endpoint is basically, once the auction is created, they should be able to bid on that specific item in that auction. So it can be something like auctions, auction ID, and bids. And then we just get in the bid ID, and then return again, and just give uh, bid the object and all that stuff. uh, it can be bid ID, bid object, and also I'm just specifying now bid object, and then whatever we want, we can just add it as we need new fields. So this is simple endpoint, post endpoint to create a bid. Let's the other thing is, once the auction is created and able to create a bid, they should be able to view auction details, meaning what is the current max highest bid, and what is the item and other details they wanted to look for before they try to bid for it. So it can be simple get endpoint auctions, and then give us the auction ID, and then I give them auction and item and all that stuff. So maybe broadly to talk here, ideally each functional requirements will try to deal with one endpoint. So that's what we are trying to do here as well. So creating an auction, creating a bid, and view an auction. I think for time being this should be it. And these are like standard system interface for the users. Okay, so now let's try to discuss one functional requirement point at a time. The first point is basically they should be able to post an item for an auction with starting price, ending date, and all that other details that they, if they wanted to. So I think this is simple and straightforward. So as usual, when we start to discuss about a new designing a system, the core components we normally try to lay out as the client, can be web or other application, whatever it's they're using, and API gateway, which usually handles routing or logging, middleware, and all that stuff. And here we have a simple auction service. Maybe the endpoint is something, it's going to be same post endpoint slash auctions, and then for this step, it's going to be just a thin wrapper around the database tables that we wanted to query these auction table and item table. So the ID and then item ID, so link to this item, then start time, end time, creator ID, and starting price, and other details if you wanted to maintain. We can maintain in this way. So this way, so the simple flow, they should be able to post an item for an auction, starting price and end date. So the components, so we have client and API gateway, auction service, and the database. I think this should be simple, self-explanatory. The flow looks something like this. So client sends a post request to auctions through the API gateway with auction details and all, and this API gateway routes to specific service. So here in our case, it's the auction service, and this what maybe it does, try to validate the request and store the action and item data whatever it gets inside in our database section. So and then the database stores the auction and data item data in tables. So this can be a simple raw flow with this given design that we have currently. Fine. So the second point is they should be able to bid on item. So bids are accepted only if it's greater than the current highest bid and all that stuff, right? So this can be something like this. So what we do, we try to introduce a new service additionally called bid service. So why choosing separate service than not handling inside the auction service is basically we wanted to scale this independently, because bidding traffic is typically is something very high when compared to auction service. So we people hardly create auctions, and then there might be 100 times more bids than auction. So that's why it's something, it's important to have it separated, and so that we can independently scale it. And also very good to have isolation of concerns, and there might be a strong business logic around validation, grace conditions, and real-time updates. So keeping it separate really gives us that flexible hand to add in the layer that we only need it. And then performance optimization stuff, even for high throughput write operations. So basically bit write is something very write heavy, while the auction service can be maybe more optimized for read heavy workloads. So that's why we try to have a separate bit service. What this does basically, it validates incoming bits. So example, in this case maybe simple example, checking the bid amount is higher than the current max or not, and then accordingly we try to update the auction table with the the highest bid ID, and store the bid history in the database, and maybe notify relevant parties of big updates and all that stuff. So this is a simple a flow which really helps us. Here we have the bid ID and the link to our auction ID, and then the price, the user ID created at, and what is its status, accepted or rejected. So again, the flow, he sends a post request to this auction ID bits, maybe something like this. And API gateway, this what it does now, it routes to a specific service, which in our case it's a bid service, a bidding service. And then this bidding service, it queries the database layer for highest current bid on these actions, and then it stores that bid in the database with the status of either accepted if the bid is higher than the current max one, or rejected if not. So that's how we try to update this bids table. And this is the flow of should be able to create a bid is something it's going to look like. And the third requirement is basically should be able to view auction including current highest bid. So they might be able to want to see an auction for two reasons. One, they want to learn about the item in case they decide they're interested in buying it, and they want to place a bid, so they need to know basically what is the current max highest bid that they need to beat. So that's why it's important they should be able to view auction details and all that stuff. They're quite similar, but the first is basically read only operation, and second to place a bid, and it's something we need consistency. So the discussion is simple here. When a user first goes maybe to view an auction, they'll likely make a get request to something like auctions and passing the auction ID. which will return the relevant auction and item details by querying the database through auction service to the client something. So here there are a lot of issues here, and we will try to discuss when we try to go into deep dives discussions. But this is something how the simple flow is going to look like to meet our core functional requirements. Now let's try to discuss on deep dives. So here deep dives is something, the first point in our list that we mentioned is strong consistency for bids, so users see the same highest bid. So this is very tricky. So what do I mean by this is basically, let's say current bid is at the $10 and user A decides to place a bid of like $100, and user B also tries to place a bid of like $20. So both user A and user B tries to do at the same time. So maybe I can so user A reads the amount highest bid as $10. User C, what he'll do, he'll try to update a max bid price to $100. Users B, since it was also doing alongside parallelly with user A, what happens now is basically user B reads the current highest bid again as the $10, and it will set the that value to $20. And because there is no consistency, due to which we face these problems, and as a result, what we are trying to do, we are accepting both bids, and the auction now has two users who think they have the highest bid. So that's something we need to take care. So how to handle this inconsistency between multiple users is something now we'll try to discuss. So approaches is something we can think through in these directions. The first approach is row locking with the bids query. So something it might look like this. We'll try to begin a transaction, and then we'll try to lock all bid rows for that auction using the select for update statement. So with current max, I'll try to query from bids table, and by locking all rows so that others will not be able to access till I release. And then after that, I try to query for the max bid and from the bids table, and then set it to max bid. After that, what we do, we try to check the incoming we try to check incoming bid amount and see if it's higher than the current max bid, and we try to accordingly update it. So here we try to update that accordingly. What is the after comparing, we try to write new bid if accepted into bids table and commit the transaction. So this is how it's going to look like. I think it should be simple, straightforward query that we have here, and I just see if it's accepted or not, and then since we are trying to do it in transactions, so it's going to be an atomic in nature. But the challenges here are quite few. First is performance and scalability issues. So here we are trying to lock all bid rows for an auction, and basically it's the one which is going to create a lot of bottleneck. As number of concurrent auctions and bids increase, the contention for the locks intensifies, and leading to increased latency and poor user experience. So the database even can go to an extent of table level logs under heavy load and blocking all operations on that bids table and all that stuff. So those are the like primary reasons: poor user experience, and then the scalability issues and performance issues that we just discussed. So this has to be a big no approach for us, and we should something that we should not try to prefer an approach of this kind. So let's look at the other approach, is basically caching max bid externally. So whenever we think of externally, it's something that we can think through the Redis introduction into our system. So what happens is basically here, we will try to cache the max bid value in memory. Here in our case it can be Redis. Now the data flow when a bid comes in looks really different. So what we do is we try to read the max bid for a given auction from Redis instead of the database, and if the new bid value is higher than whatever we have in Redis, should update our cache and then write the bid to that database with the status of accepted or rejected accordingly. So this is something it's going to look like. We just introduce a cache layer into the bid service, and then we try to look for that inside this accordingly, and then do the updates in database and all. The challenges here is this. uh, we solve one problem, meaning and created a new one. So we the problem was consistency problem within the database to within the database, and now we solve that, but introduce again new thing. How do we achieve consistency between the database and the cache? So the two layers that we have, the cache and the database. So and for this to be achieved, there are two things that we need to take care. One is cache read and cache write atomically. So here it's something that we can really use Lua scripts in Redis, and it can look something like this. So current max bid I try to get using Redis dot call get by passing an option key, and then the proposed bid amount we'll just receive this, and I will check if the proposed bid amount is greater than the current max bid that we have. Then I am going to update the cache accordingly, and so this is something read and write is happening automatically, and this is going to take care read modify write sequence as one operation. And also for strong consistency between database and cache, it's a bigger challenge here. So there are multiple approaches to achieve that. So one is 2PC, that is a two-phase commit distributed in, which is normally followed in distributed transactions for atomicity across the Redis and the database that we have. So what we should do is try to follow this, but when ever possible, we should try to avoid this kind of operations, because they are very hard to implement and hard to maintain. So it's a lot of overhead for us. So it's something that we should try to revisit our design and see if we can find other alternative ways to make it way easier for us to maintain and expand as we go on. And then the other can be, we simply try to accept Redis as a single source of truth during the auction, and we try to write to database asynchronously. Again, there is again trade-off of consistency for performance. So this is something we don't want to compromise on. And also we can check to see if we can implement optimistic concurrency with retry logic, kind of like we try to update the cache automatically first, and then write to the database. If database write fails, we try to roll back the cache update and all that stuff. So this is a good solution to think of and see if try to implement this. But the best solution in our case here is going to be basically we try to cache max bid in database itself. So this is very smart solution. Whatever we have here, what we can do, I will try to now focus on locking single row instead of locking all rows of a bids table. So here single row in a auction table, not in a bids table. So the flow is something, it's going to look like this. Basically I try to lock that specific auction row, and then read the max bid price additional property that I'm trying to maintain from that auction table, and then we try to write the bid to the status of accepted or rejected into this table, and then we try to update max bid in the auction table if that new bid is higher than whatever we had before, and we try to commit the transaction. So this is going to be a simple one. So it's a single row and for short duration and all that stuff. So this is how the optimistic concurrency control, the pattern that we just discussed, is going to look like. We try to read the auction row, get the current max bid, and validate that new bid is higher than current max bid, and then we try to update auction row. So this maximum bid, we try to set this accordingly, and if the update succeeds, I try to write the bid record, and if it fails, we'll again try to retry from the step one here. So this is going to how solve us the problem of the consistency for bids, so that users will always see the same highest bid that we just discuss. So yeah, okay, fine. And let's go and talk about the second point, which is fault tolerant and durable, meaning we really can't afford to drop bits. So how do we make sure of durability and fault tolerance? So whenever they discuss about durability and fault tolerance, immediate thing is basically we can go ahead and discuss about durable message queues and all. So because message queues are the ones which really offer straight away these things, durable storage, meaning whenever now bit comes in, we directly doesn't send it to bit service, but I would rather put it into message queue. So even if entire bit service, whatever that it is picking, all the core logic, it goes down. The bit is safely stayed in the saved in queues, and then it won't be lost, and it's like basically again it can be picked up by bit service whenever it is up. And also it's a very standard way to handle load spikes during maybe popular auctions and other times where sudden surge might happen. So this is something it takes care of. Message queue is going to take care of that problem. And also we need guaranteed ordering. So message queues like Kafka really gives us by default that as a for free of the ordering of the messages. So if the user places the bid for the same price, so whoever has tried to create that bid first has to be processed first. So something that ordering is very important in here, and that message queue really helps us to achieve that. So if we consider this message queue and all, so maybe now the it's going to look like this. So a user submits a bid through API gateway, and API gateway routes to producer now. So here the producer which immediately writes the bid to our queue. So it can be in here Kafka for our example, and then it Kafka acknowledges the right, and then we can tell the user their bid was received. So now after we appending it to queue, the bid service will try to pick it up at its own pace and all. And if bid is valid, it is returned to the database. If bid service fails at any point, the bid remains in Kafka, and then we can maybe apply exponential retry logic and all that stuff. And if not, again we try to push it to DLQ and all that stuff. So this is how we try to handle this fault tolerance and durability, and we make sure that we don't lose the bits. And the next point is, how do you make sure we give a real-time display of current highest bid? So yeah, so this is uh, very important because uh, we have concurrent auctions being executed across multiple auctions. Then if the people are not given the latest highest maximum bid amount, then they will of course always have bid they'll of course always bid it for the lower or the stale bid amount. So how can we achieve that is, let's think about right now. We were when we started discussing, we just discuss maybe simple polling for a few seconds, and then see and then we provide updated maximum bid value to the users or the clients. Or to extend that as an extension, we can think of long polling for that maximum bid. So it can be something simple as this. The function that I just tried creating. So it is just an improvement over the regular polling which we discussed here. Without trying to reconnect every time, it tries to maintain open connection to the server until new data is available or until the specific timeout. So when a client wants to monitor the auction's current bid, they establish a connection that remains open maybe 30 seconds or either max bid changed. The server, what it does basically, it holds open this request open instead of responding immediately, and whenever new bid is accepted, the server responds to all requests clients, so that they can immediately see the updated current max thing. But the problem in this approach is basically it server needs to maintain open connections for all clients without needing for some time, because max bid might not change and all that stuff. So if again many clients are watching the same auction, we might face a problem that they try to attempt reconnect simultaneously after receiving an update. So that is something called thundering herd problem. So that's one thing that we need to take care of. And also this timeout mechanism introduces a small delay as well. So these are a couple of issues that we need to take care, and this is something that we don't want to compromise upon. So the best way here is basically think always for the server-sent events, which really helps establish a unidirectional channel from server to client, allowing the server to push updates whenever the changes occur without the client polling or maintaining multiple connections. So on the client side, it might look something simple as this. They create a new event source object, API auctions and auction ID by bitstream and all some endpoint whatever we have, and then that will be listening to that event. If there is anything, it will get the max bid and then update UI whatever the bid ID that we have. Server side can be simple as this. We have something like auction event manager, and here we try to maintain mapping of list of the connections that we need to update to, and then the simple helper functions to add a new connection and then broadcast that new bid whatever we have. So here I just try to get the based on auction ID connections list of connections using this map whatever we have, and if we have, we just create an event, and then I loop through all the connections and try to write that response. So this way it's going to really meet the real-time updating of values to that specific auction and all that stuff. So the design is something it's going to look like this. It's just the same, but now bid service we have between client and bid service, we have server sent events connection for just the updates like we just discussed. Fine, so that's the point. And then the last point is how do we handle the scale. So basically handle 10 million concurrent auctions. So talking about these few numbers in here, we let's assume each auction as 100 bids, and we have 10 million concurrent auctions, then it's going to be 1 billion bits per day. Okay, so then 1 billion bits per day. So how about for seconds? So maybe I'm just rounding off this seconds 86,000 something 400 to 100,000. Roughly it's a 10k bits per second is something that we need to support. So and coming to data size, if each auction may be 1 KB and each bid may be 500 bytes, so 10 million multiplied by 52 is 520 million auctions per year, so weeks. So that's something. Now calculating total size, 520 mil auctions multiplied by 1 KB of each auction size, and we have 100 bits and each bit size is around 500 bytes. It's 0.5 KB, and it sums up to 25 TB of storage per here. So and these are the things, the numbers that we should think of when we try to build a system of handling this much scale. So here the components here, if you talk with the 10,000 bits per second, this message queue can easily handle that. So there's no issue with the recent hardware if we have. And the bit service, since they are stateless, so easily we can configure auto scaling based upon the CPU utilization or memory usage and all that stuff, and so that whenever it's needed it will auto scale since they are stateless and all. The database is something now it's we need to take think through as well. In the message queue, so I'll come to database. In the message queue we can partition with the auction ID so that ordering and then parallel processing of everything is taken care. And yeah, that's a good way always to follow through. Now let's come to the database. So database here we are talking about 10k writes per second. So that's a huge throughput for a single database, and it's it's going to overwhelm a single database instance and all. So to distribute it, so it's the ideal way is to shard by the auction ID, so that all auction related data sits on the specific shard, and it will become easier for us to query. So when we try to do this sharding by auction ID, and since we need to handle 10k bits per second, it can easily handle if we follow that sharding. So this is how it's going to look like when we talk about the scale for database sharding by the auction ID, and the message queue partitioning by the auction ID. And lastly is basically server sent events. Okay, so there was a problem. So let's say if I try to scale this bit service horizontally, and since we are implementing real-time updates through SSE, if user is connected to server A, and user B is connected to server B, and whenever user A updates, only the people who are listening to that specific server 1 or A, whatever I just described, they will receive updates, but not the people who are connected to the other server. So how do we make sure that the updates happen across multiple server instances of a bit service? So that's where something we can leverage, something called PubSub. The Either we can use Redis PubSub, Kafka, or even custom solution. So then using this, we need to broadcast the new bit to all relevant servers so that they can push update to their connected clients. This is simple. The flow is something it's going to be simple. Let's say what happens when a server A receives new bit. Maybe here server A can be bit service, so whatever we have on our the diagram, it publishes that bit to PubSub system, so here at the bottom. And this what essentially we are trying to put that in our Redis pub sub queue, and all other instances of that bit service, so can be service B, service C, service D, and all that stuff, are subscribed to this PubSub channel, and they receive the message whenever we try to put some content on this PubSub. So that way, if they have subscribed, or the other instances subscribe to this PubSub, they get the updated values as well, and then they can push it to their clients accordingly, and everybody is taken care to show the latest updated price in real time stream. So at final stage, this is how this discussion is going to look like: the client API gateway, and then auction service, and then producer message queue. Bit service is something we need to take care, horizontally scaling, and then PubSub to distribute the price across multiple instances of bit service, and then the database sharding by the auction ID. So this is how it's going to look like, and to meet the simple three requirements that we were trying to discuss on, and few non-functional requirements, we can go deep diver as well, maybe dynamic auction in time. So how can we update dynamic auction in time dynamically? Let's say if the last bid was placed an hour ago, and then we should just update the auction in time as accordingly. So this is something maybe what we can do. We can simply update auction in time on auction table with each new bid. So, and then cron job can then periodically look for the auctions that have ended, and something we can do on those lines. And also purchasing, whenever whenever a bid is won, then we need to send an email at the end of auctions asking them to pay for an item. And if they fail, maybe in 1 hour, 2 hours, 3 hours, or 1 day, or whatever the time that we have, then we need to trigger a mail to the next highest bidder, and then on so on. So that's something we can also add it in our system, in our current system that we have, and maybe also show a user to see all the bid history for specific auction and all that stuff. Yeah, I think just those are like rough ideas that we can add on to this design that we have, and enhance this. So this way we learn more and more about integrating components into system, and able to expand as we keep developing it. I guess, yeah, learn something from this online auction, and then we'll catch up.
All right, now let's discuss on price tracking service, a simple service that we can try to build. Maybe let's take an example or use case here. We want a service that kind of monitors Amazon products prices over time and alerts users whenever price drops below certain threshold, and then something which our service will notify them, and so they can go ahead and buy the product or whatever it is. So at a high level, this is the kind of a system that we'll be trying to discuss and see how we can at least come up with a simple design to meet certain requirements. Okay, so now the definition is clear. Let's see the requirements that we should meet: functional, non-functional. So the functional, we have here, the first point is basically users should be able to view a price history for Amazon products. So over a period of time for a specific product, we should provide an option for them to see what was the price graph for that specific product and all. So that should be the first criteria that we should meet while we are designing the system. The other requirement is the user should be able to subscribe to specific product, so that and we should provide an option for them to enter some threshold value, and whenever the price meets that specific threshold range, then we need to notify them with even maybe can be some email notification or something like that. So these are the simple requirements that we should meet. So they should be view price history for Amazon products, and they should be able to subscribe to those specific products. Coming down to the non-functional thing, here we should prioritize the availability over consistency. So eventual consistency from actual price changed in the source of truth websites like Amazon is acceptable. So that's the first criteria. Here functional, we can just think of more features that to add, maybe provide an option for users to search and discover the products on our platform, and then price comparison across multiple retailers. Then maybe product reviews and ratings also can be added, but those are good to have. But right now we'll just restrict it to two functional requirements, and then we'll discuss on it. And the second non-functional requirement is basically our system should handle maybe rough figure, ballpark figure of, let's say there are 500 million products on Amazon's platform. So we should be able to handle such massive number of products in our platform as well. So yeah, that's the second criteria. And then whenever user tries to see let's say a price history for specific product or a 2-year time frame or window, then the query for that price history should be very fast, meaning the latency to retrieve the record should be less than 500 milliseconds. So that should be the criteria whenever we are designing this service. And the price drop notification should be delivered to users within 1 hour of price change. Okay, so these are like core or non-functional things that we should try to address while we are designing the system. So given now the functional and non-functional are at least pretty much clear, and we know what should be the objective that our system should meet. So after having identified these requirements, then the second is core entities. Straightforward. So looking at the requirements, the things that we normally see core entities here is the product. So that's the symbol represents the product we are tracking. It can include it something like its current price, metadata related to that product, and all those details. And then the user, so basically that's straightforward user using our service. It can contain contact information and preferences for their notifications and all that stuff. This entity will try to handle. And then the subscription, so it basically links users to products that they want to monitor, specifying certain threshold which is the one that triggers notification to that specific user. And the price table, it's something kind of like time series data which we try to keep track, which changes over a period of a time for specific product, so that it makes it easier for us to pull
metrics using specific query for that product. So these are the core entities at a high level. As we go or deeper into our discussion, we'll expand on specific fields and how they interact with each other. All right. So and generally after this, it's the system interface or APIs that we should discuss upon, and they mostly adhere to one point of a functional requirement connected to one endpoint and something like that. Okay, so here API is first thing is retrieving historical price data. So it can be as simple as get endpoint. So your product's endpoint, and we pass in dynamic product ID, and then the price endpoint, maybe here period maybe 30 days, and granularity it's daily, and then I just provide some object, let's name it as a price history list of such objects, so that can be easily used to render it on a charts or whatever. So this is a simple endpoint which helps us to retrieve the specific product's historical price data. Then the second endpoint is providing an option for users to subscribe to that specific product price drop notifications. So it can be as simple as like / subscriptions, and the body we try to take in the product ID they wanted to subscribe to, and the price threshold that they're looking for, and then the notification type. So here maybe mail or whatever we wanted to, we can just provide an options for them, and then it's going to be a simple 200 response that we provide. So these are like two rough endpoints that we will have in our system given the functional requirements, or just two that we will be discussing. All right, so now we are clear, at least functional, non-functional entities, and then APIs and all. So let's try to understand overall data flow in our system, how it's going to look like. So the simple data flow is going to look something like this. So web crawlers or Chrome extension, we will try to collect current prices from Amazon product pages, and after we collect those related info, this price data is validated and stored in our price database, which is specific to our service, and then the price changes trigger events for notification processing. After that, users receive email notification if the price meets that threshold and all those things. So this is going to be rough data flow at a high level, at least how the journey of data is going to look like in our system. All right, that is clear. So now let's go deeper into high level discussion. So ideally one functional point discussion at a time. So first thing is user should be able to view a price history for specific Amazon products. So here how let's try to keep it simple, and overall we'll try to have a simple components talking to each other, and then we try to expand deeper as we go into further points discussion. So at a high level, I just have the simple flow. So here the client basically I have here client component. It can be website or extension, and the standard API gateway, price history service, and talks to price DB. We have here price table, something product ID, timestamp, and price, and here web crawler. So let's not talk about now more onto it. That's all in all separate discussion. So we do have this also in our list. You can just go back and check out that. But assuming this is something black box, so this web crawler will try to scrape that Amazon.com website, and then the primary database, whatever we are trying to maintain, will capture all the info related to that specific product. So it can be ID, and then Amazon ID, and then last scrape, timestamp, and other details and all. So this is rough the flow, how it's going to look like if user should be able to view price history for Amazon products. So like I said, so the core components is, it can be website or extension. That's how the users views price history graphs and all. And API gateway, we all know, standard which handles authentication, rate limiting, routing requests to the specific services and all that stuff. And here we have price history service. It basically just is a thin wrapper around our price DB, which manages price data retrieval and coordinates with this database, whatever we are trying to populate using our web crawler. And price database, it stores current price, product information, and then historical price data. And here maybe let's say here primary database, I'll try to keep all users info, products info, subscription info.
The reason here we are trying to separate a price history service from main web crawler services because they really have a different scaling characteristics. Meaning here the history service need to handle very high read request from the user. So basically this is more read heavy, and this write crawler is something operates with consistent write patterns. So that's why it's important to separate them as independent services, so that it really helps just for us to handle scale as we go deeper to handle higher traffics. So the flow is simple. Users makes a request, maybe the endpoint which we just discussed, products, product ID and price, period, 30 days and other query parameters that we get. And API gateway tries to authenticate the request and routes the request to this price history service. Then price history service queries this price database, like filtered by the product ID and the time range and other query parameters that it receives. And then this historical data is returned as a JSON to this price history service, ready for some recharts or whatever chart rendering. Then Chrome extensions or website which will get those details will try to display the price chart to the user. So that's a simple flow for time being for user to see the price history for specific product. Okay, so let's discuss the second point. They should be able to subscribe to price drop notification with the specific thresholds that they give for that particular product. So what is it here is now we need to focus on how can we manage new components. What I'll do is to notify or check, we can start with simple polling approach that really gets the job done, though it's not the most optimized method. But let's see how, after introducing that into our above design, how it's going to look like. So here we have the new services, which is a subscription service, and the notification cron job. So what the subscription service does is basically it tries to manage users subscription and then price threshold settings. So this is the one, maybe it receives product ID and then the price threshold and other things that the user wants to subscribe to. And here we have the subscriptions. So ID, user ID, product ID and price threshold. So this passes in that, and we try to save into that subscriptions table accordingly through this subscription service. And this notification cron job, so now what it does is basically, let's say periodically every couple of hours or so, it checks for price changes in our price DB and sends email notifications if that has met the subscriptions. So I'm just trying to abstract it at a high level. We'll discuss more on as we go deeper. So this now we have separate for price history and then subscription service as they serve different purposes and all. So here the cron job, so like I said, it tries to check every couple of hours and it queries this price table here for any price changes in the last 2 hours. And for each price change, whatever we get, it queries this subscriptions table from this primary database to find users with that thresholds greater than or equals to that new price, and then collect those users list and then send the emails to that specific user. So then we try to mark somehow like notification as sent, so to make sure that we don't send duplicate notifications to the user. Yeah, and whenever user subscribes to price alerts, this it just sends a post request to this subscription service, and then we save it to our subscriptions table. So to add a new subscriptions entry through this service is something will be taken care. So this is how it's going to simple flow look like. Submit subscription via this our client, whatever it's going to be, and then API gateway routes a post request to this subscription service, and then it creates a record in this subscriptions table, and then it returns confirmation that a subscription has been created for that specific product. Okay, so this is a simple way for providing an option for users to subscribe to a particular product. All right, fine. So at least now we have a decent flow of actually meeting our basic functional requirements. Now it's time to discuss deeper and see how we can meet non-functional requirements, which are those are very important when it comes to scale, and that those are the points to be discussed. So deep dive. So first thing is, now how can we handle meaning in here, in this case it's how can you discover first that's such a huge platform of 500 million products and track products at scale. So this is like um, mm, very challenging discussion. So because we need to find all 500 million existing products and be able to discover at a high level, let's say like every day 3k plus or products are being added onto that platform daily. So how are we going to discover those new ones and also monitor all of the 500 million products prices, and how will we know which one to prioritize to check most frequently and which one not to? So it's something 500 million and such things, we cannot monitor all those things, so those are the questions that now we need to address, and let's discuss the several approaches and see what is the best approach to deal with a situation of this kind. So approaches, so first thing is we just do native web crawling approach. So here what we do is basically it's a simple straightforward. We try to deploy traditional web crawlers that systematically browse Amazon's website, maybe with some seed URLs like main homepage and some product categories, and as a seed URL to our web crawler service, that all in all it's a separate system design discussions. So for time being we assume that this is a simple design. What we do is we try to implement a simple frontier queue. What this does, it basically offloads
to the crawler service, and whatever the scheduler we just get the URLs, we'll try to append it to our frontier queue, and that gets picked up by crawler service, and if it again identifies any other URLs, it appends back to this queue, and then that gets repeated, and we save those price related details into our price DB and primary DB accordingly. So it's a simple um, flow. Basically the scheduler picks up and then puts into frontier queue. Crawler picks up that specific URL, tries to crawl that, and then update prices if we have any price related metadata and product related info into our primary database. So this is something which is offloaded to separate services. All in all, I will not go deeper into discussions because we have other things to discuss, but if you want, you can just check back how to design a web crawler service that we have. That's fine. So this is how it's going to the look like the native web crawling approach, and then we do. But the challenges here is this thing. So with one single server for 500 million products, assuming so it's something like services like that, they will have strict rate limiting things, and they hardly encourage to crawl things like that. So they restrict maybe one request per second per IP address. So if we have assumed one crawler service, one instance, so it needs over 15 plus years to crawl just 500 million products. So that's just our rough imagination and the ballpark figure that we have. But assume that we expanded our infrastructure and added, deployed 1k plus servers, and even after adding 1k plus servers, we need at least 5 plus days for complete catalog refresh. And again, this is going to lead to a lot of discovery lag problem, and every time for a full catalog refresh we need at least 5 plus days for complete refreshing of our products list. So this is something, given our functional requirements and non-functional requirements, this is not going to help us meet them. So it's something now we need to look for other direction, and what is that is going to be. So we can think of other approaches, basically prioritize crawling based on user interest. So here the key realization here is this graph. So if you see here, so basically a very small percentage of products get vast majority of user attention. So here this is what, and there are long tail of products that people rarely care about. And so instead of treating all 500 million products equally, then we need to maybe think of, can we tire our products crawling approach based on users interest. So basically here we will have certain high priority products and certain products in the middle tier, and then other in the low tier. So it's just this simple graph interested users and products over a period of a time. So what we can do, we can implement a priority scoring systems. Basically which products gets higher scores depends on active user engagement. So maybe mm, let's say there are many number of people have subscribed to a particular product, can be iPhone or any electronic gadget. So we know that the people that they have subscribed to that product is high in number, so obviously we need to give high priority number to that product. So that can be one way to give high priority for product. And then maybe users who search I mean the products which are searched most frequently, for that product also we can assign priority score. And yeah, that's one way to give high priority score. Maybe we can introduce priority queues based on that queue and it gets picked up. And yeah, so those are two ways that we can think of. And there can be something like that when we send an email notification to the users, and if based on the users clicks on those links also, we can maybe assign priority score. Like if the link is most clicked, then we know that people are looking to see price drop for that product, and then we improve based on that users activity and feedback as well. It's something that we can cover. So maybe after considering this, it can look something like this. It's uh, in this frontier queue we just try to add in this priority queue. Based on that it gets picked up, high score gets picked up by the crawler accordingly. So here we can, yeah, high score for product based on an active user engagement, more subscriptions, and more such products and product links and so on. So this can be few criteria that we can decide the score on, but we can still discuss and elaborate on other points as well. So this is how it's going to look like adding this priority layer. So now we try to prioritize only the products that needs to be taken care of. Okay, fine. But the problem here is if there are new or trending products are being added, we still doesn't have our system built up the users interest for those products, so we miss them, and this can be very significant problem for the user. So something that it's not taken care of. So we always rely on here users activity, and based on that itself we try to prioritize that specific product. So which is something people doesn't cope up with. So this is something again doesn't really help us in solving the major problem that we have. So talking about the next approach, it's going to be something like, Chrome extension plus the selective crawling. So here remember we assume like we have already some established Chrome extension for this system. So it's more of like, why can't we use that Chrome extension and then collect this data. So this basically significantly helps us deal with rate limiting that those services will try to have. And to be honest, they don't really expose services of that kind, which really helps other services to scrape and all that stuff. So here what we do, when users tries to browse the specific Amazon website and all with our extension installed, so we try to capture those product IDs, current prices, page metadata, and then this that information is sent to our backend services. This approach basically transforms users browsing behavior into something like primary data collection mechanism for us. So here there can be something like this price update service, which can be input from an extension, and then we try to update our price database and accordingly based on whatever the user that has been viewing. So this basically helps us to handle products that haven't been viewed by extension users, or uh, recently as well, because they are viewing that current page, and we get this data to our service, and we mitigate that problem. And the problem here is basically, again, it's not much of a problem. It's just we are trying to rely on user adaptation and browsing patterns, and also people who are not trying to browse the products with the low user interest might not receive frequent updates, and it can really widen the coverage gaps for such products. And one more thing that we need to really care about here is data manipulation. So there could be a lot of ways that user can manipulate and give us incorrect price drops, and it will create huge chaos if we send like, let's say iPhone has dropped to $1, and we try to send notifications to other people who are subscribed to the products. It's going to create a lot of chaos. So how are we going to handle that malicious content being provided, and we just blindly insert yours into our systems, and then we do check and then send notifications? So those are the additional checks and validations that we need to really keep thinking, and then implement such mechanisms are taken care in our system. So I think this way, Chrome extension plus selective crawling really helps us to solve this, helping us to discover this many products at scale, and without having to rely on exclusive rate limiting caps of that specific service. Okay, fine. Let's discuss the second point, which is the malicious price updates, which I was just talking about, the extension users. So this has to be taken care. It can be simple approach as well. So there are a couple of approaches that we can think of here. Let's say the consensus based validation. So this is a simple uh, consensus validation. So what we do, we try to maintain separate consensus table that tracks like how many unique users have reported the price drop for specific product. Let's say if two or more users, or like specific end users have reported same price drop, then we are very confident that it's not the wrong number, it's the ideal number, and we can then send a notifications to the user. So that also can be changed. For example, more the validation for popular products. Let's say I need 5 unique users confirmation if they have reported the same price or around the same price, and only then notify the people who are subscribed to the popular products. But if it's less popular, we doesn't really care, because it's less number of users, maybe one or two or confirmations, and if that's met, we just send notifications for this thing. But still here, there are some few challenges, which is basically there can be delay for legitimate price changes, because we are waiting for consensus to be met and then send. So if there is something flash sale or something which is time sensitive, users might experience bad uh, notification. So that's something we need to take care. And then there is a still chance they can beat our consensus systems and still send the same wrong price, couple of people, or three or five people, and then still fall back to the same problem that we had. So this is something really doesn't solve our the problem, core high priority problem. But to solve that, maybe we can combine this hybrid approach. Basically this trust but verify with priority verification. So basically what we do trust extension data whatever we're getting with some consensus that we just discussed. But what we do, we additionally we do exclusive verification with our crawlers, traditional crawlers that we have introduced in our system. So only for certain criteria. Let's say they have notified us of huge price drop, so that's something that we definitely need to verify before maybe creating confusion among users, or the price product with a high number of subscriptions, that also we need to double verify. And if there is that notification is received from the user who has been wrong before, then again that's the indication for me to re-verify. So these are the things that we can think of, and we can send immediate notifications, but again after double verification, if it's something not bad, we can send a correction email. That's not going to give them a bad user experience. It's something that if we don't send the notification after having corrected, it's something that is not good user experience. So this way we can just try to mitigate that malicious users of entering corrupt data into a system. All right, so the other discussion point is, how can we notify the price drop to the user within 1 hour of a price change? Right now, if you remember, there is just a cron job running over every couple of hours, and then if there's a change, we try to notify. So this is the huge problem. So the fundamental the question itself here, we have been asking like what changed in last 2 hours through our cron job, and then filter and then collect that and then try to notify. But that's not the question to be asked. The actual question to be asked is, who really cares about this change, that price change? So that's the question that we should change our dimension to, and then that throws us a new approach of how this can be converted into something like event driven notifications system. So the first option that we can straightforward think is CDC, that is a change data capture. So what is this is, we have your primary database, let's say it's a Postgres or whatever it is. We configure our database to automatically publish the events whenever the price data change happens. So here I do through change data capture to this price change stream, and that gets picked up by this price change worker, and it tries to notify over email. So here whenever they insert new records, the crawlers or any updates or anything into our price db, we this database triggers and sends events to our the maybe something here can be a Kafka or other streams, kinesis or something containing the product id, old price and new price, and then this gets picked up by the price change worker, and this notifies us over email, and accordingly just queries the subscriptions table to find those users and notify the users. So this can be one way to replace completely our polling approach of cron job with this the CDC technique. So this is clean because the price changes automatically trigger notifications without any application level coordination, and we don't really need to remember to publish events in our application's code, because database really handles it for us. And this data flow also becomes the automatic. And there can be other approach as well, dual writes, meaning we can prefer dual writes. I can try to write simultaneously to my primary database and to Kafka, and that gets picked up by the worker and all those things. So that is also one approach that we can really prefer, because there we can filter out many price fluctuations that wouldn't really interest users, or we can batch multiple rapid changes before publishing events, which really helps us avoid database overhead of triggering triggers and every price update. So regardless of which one to choose, I think both one suits, so whichever is convenient or better to implement, so we can choose that. I think CDC should be a simple solution in this case, and we should stick with that. So yeah, I think that's this way we can mostly address this problem of notifying within 1 hour of price change, and instead of polling, we have just replaced with CDC or dual writes using a Kafka stream or whatever, and worker will try to do that logic whatever we just discussed, and notify the client if it has met that condition. All right, so now the next point is, how can we make sure the history queries are meeting less than 500 milliseconds latency? So currently everything what we are doing is just storing in our Postgres with an index on some, let's say product ID timestamp and all. So even on this indexing, so it doesn't really meet less than 500 milliseconds for a product at that such scale. So it's something now we need to think through, how can we improve this. So there are a couple of approaches for this as well. We can do a pre aggregations for that specific product over a period of time with cron jobs. So it can be something like every night we try to run a job that calculates daily granularity, can be daily, weekly and monthly price summaries for all products, and then we try to maintain in our separate table called price calculated or price aggregated with the specific columns that we wanted to showcase it to the users. So that can be something like this. So here we have here this cron aggregate, so which runs maybe every night or every whatever we configure the cron expression to, and we have here additional table price aggregation, the product ID, price, and granularity here, daily, monthly, weekly, or whatever it is, and window, which the duration of the period. So something we try to maintain here pre-calculated things, and then whenever user tries to query that, we try just straight away pull this from the price aggregation table. So the problem here is there is a data freshness problem, meaning data is always 24 hours old, because we are running cron job every 24 hours or 12 hours or whatever the expression it is. And now we have introduced additional storage requirements, so we have new table, and then every time we need to maintain that storage. And these are the like two challenges we have additionally introduced to solve the problem of the latency requirement. So the clean approach to mitigate these challenges as well as meet this latency requirement is simple. Introducing timescale DB extension into our Postgres database, which are really built for real-time price analytics itself. So what we can do, we can use a timescale DB, which is a time series extension for PostgreSQL. So something that query, if you want to pull for 6 months or 1 year, it can look something like that. Select time bucket, 1 day, or the timestamp, average price from prices, where product ID, into buy one and all. So this one, now introducing this timescale DB, we try to keep everything, our core tables, so primary DB, which was product, user, subscription, other things. Along with that, prices also are in the single ecosystem, so which is very important when it comes to developers perspective to manage all this operational overhead and all that things. It really becomes easier for one to maintain as well. So this way, this time series DB helps us to meet that the query requirements in less than 500 milliseconds, because even if we try to query million products, it gives us a response in milliseconds. That's what this was designed to be. All right, so yeah, that can be one way, and we can even use ClickHouse, which is really OLAP database, extensively used at a bigger organization like Netflix and other things to do some analytics and all. But if you're okay to add additional operational overhead and okay to deal with that, it's also a good option that we can stick to. It's again the trade-off. If you want to have in a single ecosystem, use timescale DB extension, or also go with the ClickHouse. So at a high level, this is how our the end system design is going to look like. The critical parts are here, and I think though this is not that such extensive thing, but at least gives us a decent idea of how we can think through and see how we can approach. And then later, as we start really implementing each component, then we can go into nuanced details whenever you are implementing and all such things. Hope you learned something from this simple price tracking service. And then
Okay, all right. Now let's discuss about how can we design a simple fitness tracking service. At a high level, this allows users to record and share their physical activities. Primarily, maybe let's take running, cycling within their network. Okay, so it should help users provide detailed analytics and performance routes, and allow social interactions with their friends and all that stuff. Okay, this is a broader definition of the service that we'll be discussing. Having understood the high level definition of it, let's go to the requirements, breaking down into functional and non-functional. So the functional, like we just discussed, so they should be able to start, pause, stop, or save their runs or rides of their bicycles and all. So that's the first functionality that we should provide to the end users. And the second functional requirement is, while they're running or they're cycling, they should be able to view activity data, like what's the route they are taking, and then the distance and the time and all that stuff. It's something that we need to provide it to them. And the third requirement is, they should be able to view details about themselves, all the tracking of their activities, and also their friends. So these are the core three functional requirements that we should target to meet while designing this system. All right, so that's the functional requirements. So going to the non-functional, here we should prioritize availability over consistency. It's okay if we maybe delay data sync up for a few seconds or thing, but it should be up for them to keep using it. So that's the first non-functional requirement that we should meet. And the second is we should provide offline first approach to them, so that even in the remote network areas they should be able to use our application. Maybe can be in this case mobile app or whatever it is. It should be functional even in those scenarios. So that's the second point, that we should try to take care of it. And then the updating their local activity stats onto their dashboard or something, it should be very quick, meaning that should be very low latency of real-time updating is something that users expect, and we should meet them. So that's one of the again critical non-functional requirement. And we should build a system in such a way that it should handle decent amount of traffic, meaning concurrent activities, like let's say at a high level ballpark figure can be 10 million concurrent activities we should support. So these are the core functional and non-functional we should try to keep in mind while we are trying to design this system and delve deeper into discussions. Okay, fine. Now that we are clear, so second, the core entities is I think should be straightforward, tying up to our functional non-functional requirements. So core entities here, it's going to be the user, just the person who is going to use the app, contains basic information, settings and all those things of that specific entity. And then the activity, so it represents like the individual or the person running or the cycling activity. It might include a type, can be it's a run, ride, for since we are trying to address only those two activities, so those can be the type. And then start time, end time, then the route data like GPS coordinates from some on device coordinates or external services, and then the distance and duration. So those fields something we can try to keep on this entity. We'll discuss on attribute level as we go deeper. And then other is the route. So here again we'll try to maintain a separate collection of GPS coordinates recorded during their activity. So or else we can either keep one of the fields inside this activity as well, but it's again up to us to normalize the tables or not. And then the friend, just the relations between the users, so that we maintain the vice versa relationship between those, so that it becomes easier for us to query. So these are the like core entities we have to deal with to meet the above functional and non-functional requirements. Okay, fine. So let's talk about now the API or system interface. So here like there are a couple of endpoints that we need to talk about. Mostly it will be like one-to-one mapping to functional requirements, more or less plus or minus depending upon the use case that we are discussing. So the first endpoint, it's going to be a simple creating a new activity, which is a straightforward post endpoint. Maybe it might look something like v1/activities, and then it gives just the activity object. And here he can other just the type can be here a runner, right, and other metadata will be collecting as usual. So this is one endpoint with which user can start. Maybe it might look simple as he comes to an app and then clicks on start activity, and we hit this API, and then this gets created into our database and all. So that is this endpoint. And then the second endpoint is updating the activity. So once he has so basically this is an endpoint to keep updating the status of that activity in our database, maybe periodically or whatever. We'll discuss how we are going to do that. So here just given the activity ID, and we should just update the status of it, like started a past. So it's this patch endpoint, because we are not updating all the fields, just the specific fields in that entity in the activity thing. So that's what the patch should do in this case. That's to update activity. Okay, fine. And then updating coordinates of the activity that he has taken. So basically here we need to frequently periodically we need to update the coordinates of its the activity GPS coordinates. And then it's also something can be specific separate route for routes, and we send in the location coordinates post endpoint, and we try to update this as well in our database. So this can be one more endpoint that we can talk about. And then as soon as he opens our application, he should be able to see all the activities he has taken so far in our application and all, just to get endpoint to list activities for specific user. So it is going to be activities and mode, was it for him or for friends, just to see his activities or his friends activities, and pagination, page size and standard thing, and we just give partial of this activities array, so only the things that we need to showcase in our dashboard or the main page of that user. So this endpoint is going to retrieve that, and we're going to showcase in the application app as the design is implemented. And the other thing is the other endpoint is giving extensive details of that specific activity. Just passing in the activity, we give the activity so that they can see the map, the route that they get taken. Maybe we can use Google Maps API or others providers, whatever it is, and then showcase other details, maybe some graphs and the details which they need. So these are like 5 endpoints we need ideally to meet our functional and non-functional requirements. I think these are pretty simple endpoints, and then we will discuss how they are going to interact with each other, how we are going to fit into our design between multiple components. All right, so we are clear with these endpoints and then the entities and then functional non-functional requirements. Let's take one point at a time from functional requirements and see how we can start evolving our design from simple client-server architecture. So the high-level discussion, the first point that we should meet is we should be able to start, pause, stop and save their runs and writes, right? So here I'm just starting with a simple client-server architecture. So this is straightforward. So user interact with the system through this. In this case, let's take a mobile application, and they interact with this activity service. So basically this activity server, it just handles incoming requests for creating or updating activities, and the database here, we just try to store information about activities including route, distance and time. So it can be something like ID, the type, start time, the status, and then status updates event. So it can be here something like this, when he started and timestamp of it, and then when he stopped, the timestamp of it, and when he resumed and then stopped. So that this really status of updates events, it really helps us to calculate what was the active time that he involved in that activity rather than the total time. So we can calculate the elapsed time very effectively. So that's why it's important to maintain status update events, and something it might look in this way. So this is a simple flow. He just makes a post request here to /activities to create a new activities through this activity server, and specifying whether it's a run or write, and then this activity server will create an entry in our database and then return the activity object through this activity server to the client. And then if users opts to pause or resume and all, he will use the patch endpoint which we just discussed, and same flow is going to happen and updating the status update events accordingly. And and then finally, whenever he tries to save activity, then we try to trigger a patch request with the status as complete, and then update the final status of this to complete. So this is the rough ideal flow of having a minimal client server architecture to meet the basic functionality. Let's see, there are a lot of bottlenecks and all given the requirements that we have, but we will try to discuss on this as we evolve into further discussion. And that's how we try to meet this simple start, pause, stop and save their runs and writes. The second point is, while running or cycling, we should be able to view activity data. Can be something the route that he's taking, the distance he has covered so far, and the time and all that stuff he has been active in that activity or so. So how is it that we are going to do here is simple. Here we assume, like by default these days all mobiles come with basic GPS integrations. So that's something we can leverage on. So let's say tracking this coordinates of a user is something important here, so we might track it at a constant interval. So So what we can do, we can now use this GPS coordinates that we are getting to calculate the distance, maybe using Havasin formula or whatever, which makes really ideal to use it, and calculate the total distance E has covered so far. And then there is the new table, so activity ID and the link to this route mapping. So activity ID and the coordinates that we'll be receiving from our GPS, coordinates, latitude, longitude, and the timestamp we'll try to maintain in this routes table. So this is how it could work ideally. What happens is basically the client app here in this case will record users GPS coordinates, let's say at every couple of seconds or 5 seconds, for a run or bike ride, depends upon the activity type. And we will try to use inbuilt location services. For example, for iOS there is a core location framework, this location manager class, and then we can leverage start updating location function, and then implement this location manager to give us the periodic update locations coordinates, and then try to store it in our routes table that we are trying to maintain. So if it's an Android, we can use Google's location services API, and then we'll try to use something like Fuse location provider client and call request location updates, and then update routes table accordingly. So it depends on the OS that we have. So then the client app, what happens, this sends this coordinates to our activity ID endpoint, and then the activities, the server will try to update our routes the table in the database with the new coordinates, timestamp, whatever we get. And then we need to calculate this distance, the value as well, maybe by distance between the new coordinates that we'll be receiving to this routes table with the previous one, using Havasin formula and all that stuff. So this way we try to make sure that store the coordinates of the users, and then calculate distance and the timestamp and everything is taken care using the GPS on device GPS usage and all. Fine. So that's how we'll try to meet this simple functional requirement. And let's now jump on to the next discussion. Then the next is, you should be able to view details about self and friends. Okay. So here it can be simple as a query when we try to look for some specific details about self or friends. Let's say if our user is trying to look, as simple as query, we can do something like this. We'll try to query our activities table and check just the state is complete, and use filtering by user ID and then pagination logic that we'll try to apply. So this can be simple query to get the details for that specific user. For his friends, it can be something like this, and user ID in select friend ID from friends table, where we try to maintain this friends table will try to maintain user 1 and user 2 entry in our table, and same as vice versa, so that we get all the friends of user 1 user 2 simultaneously. So this way we'll try to maintain just the relationship table between users, and so that I can make use of it while trying to query for that friends. And that simple pagination here, so we can get friends details as simple as this. Yep. So the flow is something like this. User might navigate to something, the activities page that is present on that app, and then he makes a get request to activities mode user or friends page and pagination side to get the list of activities, which we discussed in the endpoints section. And then the list of activities is rendered through the server to the UI to view things. And then to view more details of that activity, he again makes a get request to that specific activity ID and views those details. So this is how it's going to look like, just to view details of the app itself and friends, and then simple query. We are just trying to first have a simple working functional system design, and then we'll then discuss heavily on regarding non-functional requirements to meet the actual numbers and the scale that we are talking about in our discussion. All right. Fine. So this is the simple functional requirements, and now it's time to discuss on non-functional things. It's a deep dive discussions. So deep dives, so first is how do we make our offline working functionality as the best as possible to the users, meaning even when they're offline, we should just let them use our application as is. So here it's something very important given the use case that we're trying to deal in. To at least see what problems this solves, if we achieve this, assume, so we now don't have to worry about network reliability on the client side, and also even the load, I mean the network bandwidth to our server is significantly reduced, because now we don't ping for location updates very frequently. Instead we try to send only on run completion or pass, whatever it is, and then showing accurate up-to-date activity also happens synchronously, since it's all on device. So that's something that if we achieve this, it helps us to achieve those problems. So how it might work, so this is how we are going to make this one work. So this is just the simple design that we had before. We had something, we'll try to leverage in-memory activity buffer and something persistent storage. Okay, let's see here what we do. We'll try to use on-device location services to record users coordinates at a constant interval. So we record this event data locally and store it in our in-memory buffer. So it can be simple as like array of GPS coordinates and timestamp paths and whatever we just had in our route schema that we have. So and yeah, there are like situations that the data might get lost during maybe device shutdown, or their battery is degrading very fastly. So to even persist that, what we can leverage local storage concepts on device. So for example, in iOS there is a core data, or we can use even a SQLite database for larger data sets, or just if it's a smaller amounts of data, we can use user defaults to store that. If it's an Android, there is a room database for larger data storage, or even SQLite again or also can be preferred here. And if it's a minor, again we can go for shared preferences, storing those details. So once we have this, then when the app is reopened after crashed or anything, we first check this local storage here, whatever we were talking about, if there is any saved data left and all. And then if it is so, we will try to load the saved data back into our in-memory buffer before continuing to record new data into that in-memory buffer. So this way we'll be taking care of even the device shutdown or device crash or battery shutdown on those stuffs. So after that we'll try to maybe accumulate data to our server in a single request, maybe on completion of activity, or we can send it in chunks if the data is very heavy, or implement background sync mechanism. Maybe periodically we'll try to sync between our this device and our remote server. That can also be something that can be implemented. And then upon confirmation from remote database that activity is saved and completed, then we'll try to clear our device local storage of room database or core data or whatever SQLite that we are trying to maintain. So this way it's something we make sure that it even works without heavily relying on our remote services or remote database and all, completely leveraging here the client. And we are very much emphasizing that client is very critical part in our core system design of our this fitness tracking service that we have. So this is how we provide the offline local functionality for the application that user is going to use. So the exact implementation and all specific to the OS and then the framework that's being used, it's going to change, but it's more of a discussion when we are trying to go into nuances of a mobile system design, and then trying to start getting hands-on and all those things. That's again all in all different discussion. But at high level, this gives us a rough idea of how we can think through, and then and what is the direction to go ahead in. So this approach helps us meet this one. So now let's go to the second point, which is how do we handle this 10 million concurrent activities. That's the ballpark number that we have to support the scale that we have. So assuming, let's say we have 100 million daily active users, and so if that is the case, and let's say one user is trying to create one activity per day at least, so then 100 million users one activity, so it's going to leave us to 100 million new activities per day. So that's something per year, it's going to be 365 yeah, 36,500 million activities. That's something roughly 36.5 billion activities. So those are the activities per year that we are expecting to be created into our system. So storage wise, for that number of activities, let's say each activity is something 100 bytes, can be very simple because we have simple the status, user id, start and date, and other pretty cheap. So we'll just assume 100 bytes per activity. So the route, the coordinates, assume if like activities average duration is 30 minutes, and the route, that's the coordinates that we need to store for that activity, is 30 minutes. So, and since we, let's say for GPS coordinates, we are trying to periodically query every 3 seconds. So at a high level, how many points per activity that we'll be getting? So 30 minutes is 1800 seconds, by 3 it's going to give us 600 points. So ideally we need to store 600 points per activity in a route table. So here we'll be storing latitude, longitude, and the timestamp of that. So this, like assuming 8 bytes per each, so this 24 multiplied by 600, it's roughly around 15 KB per each activities route. And then so that is the activities, and total activities that we have is, I'm just ignoring this negligible 100 bytes. So for each activity we have 15 KB, and then we have 36.5 billion activities. So it's sums up to like around 550 TB of data each year. So that's the data that we are supposed to support and store it in our system. So this is something heavy data, and now we need to think of how can we think in terms of scaling this. So one thing is, we can cleverly shard by this completion time of that activity, so that whenever we're trying to query for charts or whatever we want to store, showcase historical data, it becomes easier, and they will be part of the same shard, and then really helps us to query efficiently. Other approach is, basically we can introduce multiple data tiers. Let's say that like there is a very recent data, that's something that we can call it as hot data, and we might store it in our Redis cache or in the database itself for recent one, so that it will be very fast for retrieval and all. Ideally people will try to look for only recent activity data, and then that's how we support good user experience with fast retrieval. And let's say there are like couple of months old, and then less than a year old and something, we can try to keep it in Postgres, something like we call it as warm data, so that even if they're looking for, we can just query from our primary database and showcase. But let's say if it's something legacy, less than 1 year, 2 years old, and we ideally don't expect users to query for those details until unless they desperately need it. So those, we know that they are less frequently accessed, so we can move to much cheaper storage, so that it doesn't pile up our costs for the finance team. So what we can do, that we can try to store inside our S3 buckets and all, which is a cheaper option to store the data which is not frequently accessed. So this way we can think in this multiple directions to handle the scale of this, at the same time mitigate the overall the cost, and also not to compromise on our performance of the system as well. So introducing these layers really helps us to handle this concurrent activities of introducing the sharding by this completion time and different data types, and here we might have the Redis layer to cache the recent activities and all that stuff. And the others design is going to look just pretty much the same whatever we discussed in our previous points. So this way we make sure that we support this scaling problem and all those things. And let's discuss about the next point. How do we support real-time sharing of activities with friends? So this is important. Let's say like now the friend want to actively see the activity of the other user, so that he also gets motivated and he tries to push for the run or cycling, whatever he's doing, and so that he wants to compete and win. But, so how do we make sure that real-time coordinates we broadcast it to those friends, clients who are looking for active updates? Immediately, whenever we think of the real-time sharing, we think of straightforward as WebSockets or server-sent events, and then maybe using the pub/sub model, we try to broadcast the updates of the specific user to its friends and all those things, so that they get to see the real-time coordinates and give decent live user experience for them of coordinates. But to be honest, here it's overkill if we try to use WebSockets or SSE. We can implement, but again it's a significant operational overhead. The reason why it's a significant overkill is basically here they are better. So whenever we think of like live commenting or WhatsApp live, WhatsApp and all, we prefer using this approach. But here, if you observe here very keenly, this simple polling is going to do the job for us, because we know that updates are predictable. So we know that likely every 2 to 5 seconds it's something that we need to update the friends who are trying to monitor the real-time coordinates of a particular user. And then here user are not very keen on real-time precision, so they're okay if there is a delay of like 5-10 seconds of the user's coordinates, because it's a human tendency that they normally don't try to see every second location update of a user. So that is why the simple polling we know, so every 2 to 5 seconds we can update the coordinates of the user, and then the other friends whoever are trying to look for will get that. So this is a simple thing. So what we do is simple polling, where friend clients periodically request updates at the same interval that the athletes, basically the user's device, is sending updates to the server. So here again we can try to offset by few seconds to account for latency. What do I mean here is basically we'll try to implement smart buffering system. It is an intentional lag displaying maybe lag by two intervals, maybe 5 to 10 seconds. So this what really helps us is eliminates the jarring effect on, like, if there is a sudden position change that can really occur with real-time updates. And so this showcases a constant motion to the friends whoever is monitoring, creating a like more engaging live stream like experience. So though this might sacrifice real-time accuracy, it really provides significantly improved visual experience that actually matches user expectations of like how live tracking features should really look and feel. So that's this way we can make sure that the system design is simple, and also we are meeting the requirements that has been specified to us. So this is how we can deal with real-time sharing of activities with friends and all. And the last point that we want to discuss is how can we expose a leadership of like top athletes or top users across many activities, regions, or the time range and all that stuff. So let's discuss of this. Even here we have multiple approaches starting from naive to optimal, and let's see how it's going to. So naive approach, what I do is straight away write a simple query by hitting this activities table that we have in our table, and then do a join on our users table by matching the user ID and other filtering state complete, type run, and then grouping by user ID, group order by total distance. So this one, so whatever the top 10 or whatever I wanted to show, I'll try to query this the table, that primary database that we have, and get the results and showcase it to the user. But here the significant challenge here is simple. So the query performance of this is going to degrade exponentially as number of activities grows higher, leading to higher the latency and then bad user experience, and then people try to look for the other alternatives one. So this is something not acceptable in this scenario. And the other things is standard way periodic aggregation. So what we do, we might introduce some background job or cron job. What it does is basically periodically try to like every night or few hours once. It tries to pre-calculate the user's distance, the activity, location, and the completion things, and we maintain separately in our leaderboard table. And it's going to be simple, straightforward query, and there is not going to be lots of aggregations across millions of rows, since we have already have aggregated results stored in this table. It's a simple query to that leaderboard table, and we showcase it to the user. But here the challenge here is it reduces eventual consistency, meaning users have to wait for that cron job to be complete to get the latest data, and it might create a confusion among the users. Is my activities getting updated in the leaderboard, and why is it not getting updated, and all those things. And also it's going to strain our system resources, because every couple of hours or a few hours we're trying to run a cron job and hit our database to query and then perform these aggregations over millions of records. So there's a chance that it might strain our system resource, and again affecting real user experience, though it's not the actual client talking to it. So that's something, these are like downsides to go with this approach. The ultimate approach, the need real time, whenever we try to discuss, it's going to be ready sorted sets. So we try to use ready sorted sets to provide a real time leaderboard for the users. So here it can be simple as that. We try to use user ID as members and total distance as score, so that it will always be sorted by this total score, and we just try to retrieve top and whatever we want to show in our leaderboard. So there are other additional filters as well we need to support. So in this case, how can we provide filter by country? So we can maintain along with the geographical global sorted set, we can maintain even regional specific sorted set, something like leaderboard run and the country name. It can be any country that we wanted to showcase filter by. So that's how it can be. So this is how I can try to add it to leaderboard. First is to global leaderboard. I can try to update here the distance and the user ID, and also here increment for that specific country the distance of that specific user. So this way we try to maintain the leaderboard for global as well as the region specific, and to query the leaderboard by total distance, I can just now try to get this with the scores and query how many I want, and this is going to give me the top n or so, whatever the at least that we want to showcase. And the other thing is filter by timestamp. So how are we going to achieve this? So this is again going to be straightforward. So we'll try to use a combination of Redis solid sets and hashes to store both timestamp and distance information. This can be as simple as this. So assume that whenever you're trying to log new activity, I just assume there is some random function that we have to generate a activity ID. So here first we try to create an sorted set again with the key activities and timestamps, and it can be activity ID and timestamp. And then I also create a hash set with that activity and activity ID, and here the mapping is going to be user ID and the distance. So now whenever user is trying to query the leaderboard for, let's say, last 24 hours, 48 hours, then we day ago is something we have. And first what we do, we try to get all the activities IDs within that time range. So here day ago now is the time range that we should try to get. So here we just do the range by score, and this is the key activities timestamp as a member, and then the time range that we need to get. So this is going to give us all the list of activity IDs. Now that we have list of activities IDs, now we need to query this hash sets to actually find out the users who are leading. So I can do now, given this list of activity IDs, and then I'll try to get all of this hash of for this specific activity. And then here when we were trying to store, we were having this user ID and then distance. So I'll try to get the user ID and then the distance of that thing, and then we try to maintain a simple here dictionary. So here user distance of that user ID, I try to increment that distance whatever I'm calculating. Once we have this dictionary of user ID to the distance that he has covered, we'll just try to sort users by the total the distance, and then showcase the highest to lowest depending upon the number of users that we wanted to show. So this is how ultimate the real-time querying with low latency we can provide with multiple conditions of time range, country range, global, and everything. So final design is something it's going to look like, and this is something we already have. and now we have this recent activity cache and the database sharding and then data tiers and then ready sorted sets for leaderboard, and this is all the tables and the schemas that we have and few important points that we can how the flow is going to look like. So this is how the system is going to look like to meet the simple functional and non-functional requirements that we started with. Hope you learned something from this discussion, simple discussions, at least going to give you an insight of the direction towards what is the direction that we should think in terms of, and then proceed with an implementation. All right, now let's discuss on live comments design discussion. So just we all know basically what is live comments. Whenever there is a live streaming either from Twitch, YouTube or other platforms, this enables viewers to post comments on live video feed so that viewers can see continuous stream of comments in near real time. So that's what this use case is all about. Now that we are clear what is live comments and all, let's see how we can break down these things into functional and non-functional requirements. A core couple of points or maybe 3 or so, and then we'll break down that and discuss as we go into deeper discussions. So looking at the functional requirements here, first thing is user can post comments. So yeah, the user can post comments on the live video feed. So that's the core functional requirement. So basically providing an option for viewers to post comments on particular video ID. And then the second requirement is user can see all comments whatever is being posted by other users in near real time. So that's the second requirement that we should meet. The other the last requirement is basically user can see all comments posted before even they join the live stream. So basically we should provide a way to query the history of the comments so that they can go through or scroll through the comments that were posted before they join. So these are the core 3 requirements that we should try to meet. So can post comments, can see comments in real time, and can see history comments even before they join the stream. Now that we are clear on this functional, let's see non-functional things. Here we can even add more the deeper functional requirements, like viewers can reply to comments or can react to comments and all that stuff, but it's I just want to keep it to these 3 points. Talking about non-functional things, so our system should be designed in such a way that it should scale to millions of viewers per video. So basically higher number of concurrent connections is something at a humongous scale is something that we need to support. And here the availability is given high priority, then consistency. It's okay if we delay for a while to showcase the comments of the user, but it should be taken care such a way that comments are not lost. So eventual consistency is accepted. So that's why we give high preference to the availability. And then the low latency comments broadcast. So basically broadcasting the comment of a specific user to all other viewers should be very fast, meaning it should be in less than 200 milliseconds range. So these are like core non-functional that we should try to meet, and then functional which we just discussed. So yeah, at least now we are clear on the points that we need to achieve. And as we identified the points non-functional and functional, so it's pretty clear the core entities what are they are going to be. The core entities, if you see, it's going to be straightforward. The user, so basically it's the standard thing, the viewer or the broadcaster of a video or a commenter. And then live video, it's basically the video that is the thing that is being broadcasted by user. So this might be owned by the other people and all, but that's the core entity that will be dealing with as well. And then of course it's a comment entity, the message that is posted by the user on that live video. So these are the critical and core entities that we'll be dealing with while we are trying to design this system. All right, now we are clear on this, and then now we need to have an API or system interface, basically a way for users to interact with. So here they align one-to-one with functional requirements more or less. The first thing is the first endpoint is creating a comment. So it can be as simple as this: post endpoint, the comments, and the for which video ID they are trying to comment, so live video ID, and assuming this address the users are authenticated with the specific platform and all, and we get in JW token or session token, whatever it is. And then the body, so I'm just keeping it simple. Message can be something like, he tries to post something for that specific video. So this can be a simple endpoint to create a comment. And now we are clear of how can provide a way for user to create, and then the other endpoint is to get the comments. So here getting comments can be same as get endpoint, live video ID, and the query param would be like cursor here can be here last comment ID, and the page size might be 10 or sorting order and all, just a few additional query params to give them the list of the comments and all. So this can be as simple as this endpoints to, so that users can go ahead and fetch past comments for given live video and all, and then see. We'll see if additional query params are something that we can add it as we discuss further. And yeah, those are like the I think endpoints are needed for time being and to meet our all of our functional requirements. Now let's take one point at a time from functional requirements, and then discuss at high level how can we at least design a simple system meeting those requirements, and then we'll think about how can we address the non-functional requirements, and then scale our design accordingly to meet all of the numbers and the latency that we are given. So first thing is the first point is users can post comments on a live video feed. So this is the simple thing. So let's try to make a simple way to allow users to comment on a live video feed. So this can be as simple as this. So here users will try to, so I have here three components. One is the commenter client, and then the comment management service, and then there is a comments DB. It can be anything, PostgreSQL, DynamoDB, or whatever it is. And then comment schema can look something like this: comment ID, video ID, and then the content, author, and created at. So this can be simple of this. So the flow of this is going to look as simple as this. The commenter client can be a simple web or any mobile application that basically allows users to post comments, and it's basically responsible for authenticating user and sending the comment to our comment management service. So this comment management service is what it does is responsible for creating and querying comments, the DB wrapper, and it just receives comments from this commenter client and stores them in the comments database, and this is what will help communicate the clients to our DB. And then this comments DB as usual, which I explained. So basically the flow is simple. User drafts a comment from their device and sends a comment to this comment management service via post request, which we just discussed in the above endpoint, and then this service receives the request and stores the comment in this comments database. So this it's a simple way. Just we try to have a working prototype initially, working system, and then we will discuss about how all the bottlenecks. Of course, this is not going to help us achieve what we have in the requirements, but this is a good start. All right, so that's the first point. And the second thing is users can see all comments in near real time. So basically it's whatever the comments are being posted by the users, they should be able to watch in real time. So how this is going to be achieved is, let's start with simple polling, meaning, so basically let's say I have here simple sequence diagram. So here we have viewer, server, and database. So what we do here is basically have a client's poll for new comments every few seconds. So maybe the endpoint that we had, get comments live video ID since the last comment ID end up, we can add even since parameter to the request that points to the last comment ID that client has seen. So then the server will return all the comments that were posted after the sense, and then client would append them to list of comments that were displayed on their specific screen. So this can be as simple as this. So here there is a viewer, and then he tries to poll every few seconds, and this is the loop that will be happening in the polling for. So user will try to request for this get comments for that specific live ID, and then since the last comment that he has seen,
polling, and then this server will query for the new comments from this database, and this database will try to return the comments, and then that server will try to list provide the list of new comments, and then that gets appended in the user's view, and then will be showcased accordingly. So here there is a this is going to be simple polling mechanism, and then it's going to at least achieve this real time and all, but there is of course there's a huge bottleneck. So it can the load on the database can go higher way faster with more viewers trying to hit the database, because the frequency of polling can also increase rapidly. So this is a good start, but it really doesn't scale, because as number of comments and viewers grows, the polling frequency will obviously need to keep up to meet the demand, and then it will obviously put a lot of strain on this database, which might really put our old system down and all those things. So we'll come back to this and we'll elaborate more on this, how can we mitigate this one. So for providing comments in near real time, polling is one simple approach. All right, now let's discuss on the other point, which is something you can see all comments posted before they join. So here let's discuss couple of approaches. Here basically there are two ways. The things that our get endpoint is trying to give, two pagination, so offset pagination and cursor pagination. I think it should be simple, given that if you have designed lot of services before, so there's a pattern like infinite scrolling in the UI pattern that we need to support through this. So here can be this comments live video ID and offset 0 and page size 10. So it's simple as this. Basically we first offset is basically go through the first the end rows and give me limit. So start from this offset, like let's say the nth row, that is the offset, and then give me like this 10 rows after that, something like that. So here it's very inefficient because it has to scan through all of the rows to reach that specific row and then get me those limited things, and this is also going to give the stale or repeated comment to the user if there is a new addition or deletion of comments being appended to our database. So something this is inefficient in our case, and we don't want to go ahead with this offset pagination. And the cursor pagination is something ideal for us in our case. So here we'll try to maybe we have some cursor. So basically the point that we wanted to query using by, it can be indexed, and here in our case can be comment ID and page size. So basically what we'll do, we'll just try to hit the comments after that last comment ID and only get the comments which user has not seen and pull those from DB and then try to give it to the user. So it can be as simple as this. If in our DynamoDB the expression, so table name is comments and then key condition expression is live video is matching to that, and comment ID is less than this cursor, whatever we have the cursor that we are trying to use, and then this live ID attribute values is something that we will try to match and then index things. So here this basically really helps us for users to, like, if they scroll up to view hold comments, we just use this comment ID that viewer is sending to us, and then we hit this server, get those things, and then populate in that infinite scroll view so that users always feel they are getting the hold comments and all those things. So it's a simple pagination approach that we should stick to make sure that users can see all the comments before they join. So that's the simple way to achieve this point. All right, now that we have at least discussed all three basic functional points, and we have a simple working functioning system, so let's try to go into deep dive discussions and pick one non-functional requirement at a time and see how can we scale our design or system so that we try to meet those requirements. So the deep dive. So first thing is in our first deep dive, how can we ensure the comments are broadcasted to viewers in real time? So this is very important discussions. So now right now we have a simple polling solution, which was a good start, but it's not going to meet the requirement. So here what we now we need to switch. Basically, instead of having the client guess like when new comments are ready and requesting them, we need to change something from pull based to push based model. So this way the server can push new comments whenever they are created by others people. So there are two ways to think about whenever they talk about push based models or real time, server sent events and then WebSockets. So let's see which one suits better in this approach. So here first one, let's talk about WebSockets. So here WebSockets, I think we should be clear on what WebSockets are. So they establish two-way communication between a client and server, and here the client opens a connection to the server, keeps it open, and server keeps a connection open and sends new data to client without requiring additional request and all. So simple, whenever a new comment arrives, the comment management server, it distributes the comments to all of the clients who have established a connection with. So this eliminates a simple polling and all. So it's simple as this. So again, a sequence diagram we try to establish WebSocket connection between this client and server, and this establish WebSocket connection, and then we acknowledge the same, and now the connection is kept open. So let's see the loop. So when a new comments are posted to this server, then we know this viewer is connected to this server, then we just push that new comment data to that viewer, and then this client processes new data immediately. So here we don't need for polling, and server pushes the updates as they happen. But the downside here is this: if you try to prefer this WebSocket, so basically WebSocket is preferred ideally for balanced read write ratio, something like a chat based application, something like this. So here we were very clear, it is very few comment creations. It's something more on reading or view all comments that we need to broadcast. So since there is an imbalanced read write ratio, this is not ideal way to go ahead with. So let's discuss the ideal one, which is a server sent events. So here what we do is basically it's something, we want to establish a persistent connection over a simple HTTP, and it's way simpler to implement than WebSockets. So what we do is basically the server will try to establish something for a longer time with the client, so that it can push data to the client whenever we receive any new comment from other server. So this it's as simple as this. So we'll try to establish the server sent event for comment broadcasting. So we establish connection between client and server for a particular long duration, and whenever new comment is created, then we try to persist in DB, and then we try to send over SSE to the other clients whoever has connected. So this is the ideal way to be considered for our use case. So yeah, maybe the flow is simple as this: we creates and persist it to database as explained, and then in order for all viewers to see the comment, now this comment management server will send the comment over this SSE that I have for comment broadcasting, all connected clients that are subscribed to that specific video ID. Then commenter client will receive the comment and will add it to the comment feed of them, and so that they can see it accordingly. I know this doesn't scale. We will discuss more on this, how given the numbers that we have, but just this discussion is over a WebSocket and server sent events, and why server sent events is needed. It's basically more of a server needs to send, not a client needs to send. That's why we don't want WebSockets, and we try to go with the server sent events. All right, we'll discuss again how we can even scale this to support higher numbers. And now let's discuss the other point. So here, how can we scale to millions of viewers per video? So of course, now we landed on server-sent events being like right technology to use. Now we need to figure out how to scale it. So with SSE, we need to maintain open connection for each client, meaning for each viewer. So here modern servers or OS can handle max in the range of 100k plus concurrent connections. With this number, we are very clear that the single instance doesn't really do or meet our requirements. So we need to scale it horizontally. If we scale it horizontally, the question is basically that's going to haunt us is how do we distribute a load across servers and ensure that each server knows which comments to send to which viewers. So this is very important. So basically, if we scale it horizontally, we need to let the server know which comments to send to which viewers. So let's discuss one scenario here. Let's say user A is watching video 1 on server 1. Okay, and so assume we scaled it, and he is trying to watch on this server 1, and user B is also trying to watch on video 1, watch video 1 on server 2, something like this. Now let's say that a new comment is posted by some other user, and assume it hits a server 1. So now we need to broadcast this comment to all other users who have been watching that specific video 1. So since user is connected to that server 1, we will obviously broadcast it to user E, and he will see the new comments. But how will user B get, meaning how will server 2 get the new comments that are being sent to server 1, and he also gets the new comment. So here this is the same challenge that we need to solve. So how, given we try to horizontally scale it, make sure that all other users irrespective of the server they're connected to receive the comments. So let's discuss here the approaches. So this is like something now we need to focus a lot of time on. So let's see the approaches and what the final approach that we can narrow down to. First thing is we have here, of course, horizontal scaling with load balancer and pub/sub. So what we do here in this case, we will try to separate out read and write traffic, like by trying to create real-time messaging servers which will be just responsible for sending the comments to the clients or the viewers. So we try to separate out because here the write traffic we know is much less or lower than compared to read traffic by the users. So we need to be able to scale the read traffic independently. That's why we try to separate out read and write traffic. Okay, and now we have separated, and to make sure that we distribute traffic evenly across multiple services, we can use something load balancing algorithm, something like round robin. So yeah, and the real-time message servers which I was talking about, it can maintain simple mapping in local memory, something like this live video or ID1. This has connected to this SSE connection 1, 2, 3, and then live video 2 and all these servers. So here basically what does this mean? This is a pointer to SSE connection for that viewer. So now anytime a new comment is created, this server, whatever real-time messaging server we have, it will try to loop through over all these mappings, and then for that live video, and send then comment to each one of this client. So yeah, the question now is, how does like each real-time messaging server know when that a new comment was created? So to know that, it's something that we need to introduce this pub/sub. So what pub/sub is, basically we know it's a simple messaging system. Publishers send messages to a channel or topic, and subscribers receive messages from that specific channel or topic. So in our case, let's see here in our case here, this comment management service would publish a message to a channel. So here let's say we are talking about Redis pub/sub or Kafka, whatever it is. I'm not going to discuss those intricacy details. It's let's publish this message to this channel, and here whenever new comment is created, the real-time message service would subscribe to this channel and receive the message, and then this would send the comment to the viewers watching this live video over this SSE. So this is how it's going to look like. So basically, whenever new comment is posted, we try to persist and then broadcast via this pops up or to this real time messaging service, and then this sends the comment over SSE to clients. So the downside of this is basically it's not efficient, because each real-time messaging service need to process every new comment, even if it's not broadcasting the live video. So this basically going to strain our servers, and then it's going to lead to significantly slow performance, and it's going to be inefficient. So that's why it's not preferred here. The horizontal scaling with load balancer and pops up. Let's see how can we mitigate and see how what is the other approach that can really help us with. So it's just the expansion on top of the previous approach. Here we'll try to partition the whatever the pops up that we have into channels per live video. So basically, whenever we try to partition the comment stream into different channels based on live video, the things that the real-time server that it needs to listen to or specific channels, it's going to come down, and then the load on that servers also is going to go down. And here, to keep a cap on like upper bound and number of channels, it's not ideal if you try to create the channel for each live video. So there can be millions of videos that being live streamed. So if we try to create a new channel or a topic for each of the live video, it's something we cannot handle given the constraints of the compute. So we can use something like hashing of live video, and using, let's say we have n servers, I mean the n channels, then we can distribute the load accordingly to that specific channel. And then we will, of course, now we have a limit on upper bound on the number of channels that we can have as well. So it's simple as that. We just broadcast by partition by live video ID, so topic per video. So what this real-time message server now will only subscribe only to topics with comments from live videos that clients are watching. So instead of listening to every thing, it will just listen or subscribe to only the one that live video is. So here, let's say here video 3 or video 2 and all, and accordingly will broadcast to that specific client. So this is simple thing. It's a better improvement over a previous one, but it again could end up with the same problem that we had seen in the previous approach. Basically, its server could end up with viewers subscribed to many different streams, replicating the issue from the previous approach. Yeah, so if user has subscribed to let's say all of these videos, then again this real-time message servers needs to subscribe to all these channels, and again this leads back to the same problem that we had before. So that's why this again doesn't really help with. So let's see what is the optimal or ideal solution is going to be. So here we have the pops up partitioning, but we'll now go with a layer 7 load balancer. So what the goal now, the problem to solve is try to always go in the direction like we need to have now each server primarily handle viewers of same live video instead of multiple live videos, so that it doesn't have to subscribe to multiple channels. Okay, so that's the primary goal. So to achieve this, there are two ways. So first option is intelligent routing via scripts or configuration. So layer 7, the load balancer API gateway, we can leverage the consistent hashing on that live video ID. So basically here we will get that video ID maybe in the header or path parameter. We expect that query to have that video ID. Then the load balancer can apply hashing function that always routes that viewers to the of the same video to same server. Maybe tools like the Nginx can be scripted with Lua to achieve this content based routing, and then make sure that we route to the same server of that video ID for those viewers. And the other thing is we can have dynamic lookup using coordination service like Zookeeper or etcd. So here what we do, we'll try to store that live video to server mapping in Zookeeper or etcd. So the load balancer or custom proxy, we will try to query every time the Zookeeper to determine the correct server and get that mapping value, and then accordingly route that request to the specific server. So this way we try to limit the viewers of same live video go to same server, so that the server, real-time messaging server, whatever we have, it will only have to listen to that specific channel and all those things. So this can be as simple as this. Now we only end up the viewers of same video end up on this same server, meaning real-time messaging service, on then it leads to that only specific topics to subscribe of this for the specific channel, and accordingly it will broadcast those comments to the clients. So this can be one thing. So if we don't want a pub/sub model, all in all, there is another approach. We can introduce something called a dispatcher instead of pub/sub. So it can be like this. So that is, pub/sub is ideally preferred given the edge cases are minimal in that situation. But if we don't want that, there's another approach as well we can think through, though in reality this is very hard to implement and something, but we can have a discussion on. So we can introduce scalable dispatcher instead of pub/sub. So what now it does is, the idea is simple. So service creating comments, instead of coming through pub/sub to real-time messaging server, we directly try to route each new comment to appropriate real-time messaging server. So this that dispatcher service is someone who should help us to determine the exact server responsible for the viewers of that given live video and send the comment there. So this can be something as this dispatcher responsible for sending to correct messaging servers. And now we don't use pub/sub, it's just through HTTPS. This real-time messaging server will receive and then will broadcast the same to this clients. So how does it knows which server to send to? Something like this, it needs to maintain few things here. Maybe at high level we can have, so it needs to maintain dynamic mappings. So kind of like, it needs to store in memory and same video to server mapping, or it can periodically refresh from consistent store, something like Zookeeper etcd, which we discussed maybe through heartbeats or registration protocols as servers join or leave. And then the other thing is registration and discovery. So when this real-time messaging server comes online, it registers with this dispatcher service that we have, or the coordination server, in this case Zookeeper etcd. Then the dispatcher updates it in its internal local memory mapping to reflect now which server is serving particular live videos and all. So likewise the same, if it scales down, again it needs to remove that mapping in that local memory and accordingly sync up with the Zookeeper and all those things. And this direct routing, so upon receiving a new comment, the comment management service just calls this dispatcher service. Now that we have local mapping, so it just forwards the comment to that specific server value, whatever it had in this mapping. And the scalability and redundancy, basically here again, even if you wanted to handle, there can be, now we need to introduce multiple dispatcher instances to run in parallel behind a load balancer. Again, they all try to consult the same coordination service or something like Zookeeper or etcd. But this replication really adds more redundancy and makes system more resilient to failures and all. But the challenge is, like I said, in reality it's really hard because we need to ensure the dispatcher service it's always accurate and up to date. So there might be rapid changes in viewers distributions, meaning viral stream can cause sudden influx of viewers. So that requires dispatcher's view of the system to be
refreshed frequently, meaning syncing up with the zookeeper or etcd. So this really involves heavy coordination with zookeeper, and we need to propagate the changes to all dispatcher instances properly and all those things. So this is something challenge to implement. And also the consistency, like I said, across multiple dispatcher instances. So that's the problem. But ideally pops up whatever we discussed here. This is preferred, but that is also one approach that we can have in mind, or an approach. And let's not worry about implementation. It's all about like at least aligning onto one thing, and then that's all in all separate problem to think about. But to sum it up, this is how given our requirements for live commenting, functional, non-functional, we can at least narrow down to this design and meet at least those basic requirements that we have listed down. Hope you learned at least something and gave you decent idea, and then maybe think from here and see if we are put in a situation of this kind, what is the way that we need to think through. Yep. All right, now let's discuss on simple system design using of WhatsApp use case. We all know what is WhatsApp. So basically, which really allows us to send or receive encrypted messages or make a calls from phones, laptops, or computers. So at a high level, that's what it really helps us to achieve those basic functionalities. Now that we are clear on what is WhatsApp, let's see the basic functional and non-functional requirements, and see if we can achieve at least couple of them or few of the points whatever we try to discuss here. So first, the requirements, the functional requirements, straightforward. The things that we need to be able to achieve is the first is user should be able to start a group chats with multiple participants. Let's say maybe couple of users, or let's say max cap can be 100 or 200, whatever. Good to always have a cap on number of participants that can be part of that group chat. So that's the first requirement, should be able to start group chats. And the second is should be able to send or receive messages, which is a basic functionality that we should try to meet in our design discussion. And then users should be able to receive messages even when they are not offline. So basically we should somehow provide persist even when they're offline. So it should be durably persisted, so that when they are back online we should send them all those messages. So that's this third requirement, should able to receive messages sent while they're not online. So that's the third requirement. The fourth one is should be able to send attachments or media in their messages, normally files or video or audio, whatever the media that we normally see. So these are like core functional requirements: group chats, send or receive messages, offline support, and then the media support in their messages. Okay, fine. So now let's see the non-functional things. Non-functional is we should make sure that the messages that are getting delivered to users having very less latency, kind of, let's say 500 less than 500 milliseconds or so, or plus or minus, and it should be within that range, so that they don't feel lag in the messages being sent or received. And then we should guarantee the messages are being delivered and they're not getting lost, and that's the other things. And our system should be designed such a way that it should handle like billions plus users with very high throughput. And then finally it should be very fault tolerant, so meaning it should be resilient. And then we should be able to handle not just one single device per user, but user can have multiple devices, can mobile, laptop, or tablet, and other stuffs, whatever he has. So how are we going to handle that multiple devices situation, also something that we need to discuss. So these are like core non-functional requirements, and now we are clear on functional and non-functional. Let's see, discuss as we go. So first thing, as usual, so we need to identify core entities. So I think with these requirements it should be pretty clear what our core entities. So the core entities for us is going to be the straightforward, the users who are going to interact, and the chats that either can be two or more users in a group chats and all. The messages, each the message entity that will be sending on the turn of a conversations, and then the clients, like the devices that user have. So ideally, I think this four core entities should do to start with our requirements whatever we have. So I don't want to talk more about the entities here. Maybe as we go deep dive into discussion, we'll see what the actual schema of those things are going to be. And let's now jump to the API interface. So since this is something for a chat app, so we need to have very high frequency updates, meaning there should be a case for bidirectional socket communication. So it is not going to be ideal REST API, so it's going to be a WebSocket, so which will really help us open the connection between client and server, so that we can send messages, send and receive commands, which really represents here those as an API. So we will talk more about in terms of commands. So first command is going to be creating chat command. So it can be here create chat command, and then so here we will what the participants, list of the participants that needs to be part of the chat, and the name of the chat, and then we'll just return the chat ID. So this is going to be first command, creating a chat, and then sending a message command. So this sending it to sending a message to that chat whatever was created. So chat ID for which the message needs to be sent message, and if there is any attachments, list of that, and whether success or failure. It's going to be a simple thing. And then next thing is creating attachments, straightforward, able to attach any file or whatever the media is there, so body and some hash, and then we return the attachment ID. And then modifying chat participants command. So here either adding or deleting participants into the chat. So it's chat ID, user ID in operation, either add or remove, and then success or failure. And the chat update command. So basically these are like more or less of a commands received, kind of an acknowledgement, those things. So that's why the representation is there. So for the chat ID for the participants, we just acknowledge or update with the received status, and then new message command. So here this whenever a message is received, we will try to acknowledge the same chat ID, user ID, message, and attachments, so that we ensure that acknowledgement is there and a guarantee of message delivery is taken care. This is more of a like these are like commands, whatever we have here till 4 commands. There's a like command sent, and these are like chat update and new message are like commands received. So we'll see what these things are. So we'll try to this is a way for client and the server to acknowledge, so that we ensure messages are delivered. All right, now we are clear at least on at a high level the commands, what are their ideally the commands are. Now let's try to take one functional requirement at a time, and give a decent good start of with a single host and server normally, and then we'll see how we can scale it up to meet our requirements. So the high level discussion. So first the requirement is it should be able to start group chats with multiple participants. So that's the simple criteria that we should try to meet. So it's going to be very simple. So what we'll do, so we need a way for user to create a chat. So here the client, and then we'll try to open a WebSocket connection, and we use L4 load balancer. So I'll just try to and this load balancer will try to talk to our chat server, and assume like we are sticking to DynamoDB or any DB should do, but this is just a simple key value store should do it in our case. So database, and we have like chat entities. So maybe it might just ID of the chat and the name of the chat and many metadata that we wanted to maintain related to the chat, and the chat participant. So the chat ID that it is linked to, which is the sort key, and the participant. So it is a global secondary index, which will really help us to find So this chat ID helps us to find all the messages for that chat, or all the participants for that chat, and this participant will help us really find all the messages of that particular user. So the steps are here simple. So user, what it does, so he connects to the server and sends the create chat message. The service inside this will try to this chat server will try to create the chat record in the database, and also creates a chat participant record for each user in that chat. Then the service will return the chat ID to the user. So this is what it's going to be a simple flow. Yeah, like I said, the indexes on here, why we need indexes on this, helps us to retrieve the chats for the specific user, and then it helps us to receive all the chat participants of the specific chat, and then messages of them accordingly. So that's why we have an index, and I think this is a decent start for us to able to start group chats with multiple participants with a couple of entities and tables. So now let's go to the second requirements. User should be able to send or receive messages. I think this is the simple, straightforward. So we'll just straight away leverage WebSocket connection that we have established before. So here what we need to do is we just need to maintain a simple hash map with user ID to WebSocket connection mapping, so that we will know which one if user is connected or not, and accordingly we will try to send that messages to that specific user. So the flow is ideally it's going to look like this. So user sends a send message command to the chat server. The chat server looks up all participants in chat table, whatever we have, via chat participant table, and then the chat server looks up the WebSocket connection for each participant, whatever it has extracted in the previous step in its internal hash table. Maybe it's assume we are maintaining that, and then it sends message via each connection. So this is going to be simple, but here we have a lot of bottlenecks. We are just assuming that strong assumptions. Yeah, we are assuming all users are online and connected to the same chat server, and then that they have a WebSocket connections for each of them, and assuming all of this are in place, and this is the points that we are talking about. And given those assumptions, this will work. We'll see how can we mitigate those assumptions and then achieve all the functionalities that we have. But to meet the basic requirement is something we will try to do, leverage the simple this WebSocket connection that we already have. So now let's go to the next point, that is should be able to receive messages sent while they are not online. So this is something maybe let's say we need to maybe store up to like 30 days or 60 days depending upon the days that we wanted to keep it in our storage. So here we need to store, not just rely on WebSocket, but we need to store the messages in our database somewhere, so that we can deliver them to the users even when they're offline. So what we'll do, we will try to add additional tables here, something called messages section called inbox and the messages entity. So here maybe inbox will have recipient ID and the message ID, and the message will have ID, contains creator ID and the timestamp. So this is how the flow is going to look like. Let's say that user sends a message to our chat server. The chat server looks up all participants in the chat via this chat participant table. The chat server will create a transaction. Now it will try to write a now message to our messages the table, and also creates an entry in the inbox table for each recipient. Then the chat server returns a success or failure to the user with the message ID. This will return to the user with the message ID, and the chat server now looks up the WebSocket connection for each the participant. So whatever the hash table that we were having, it will try to look for a WebSocket connection for each participant and attempts to deliver back the messages to each of them via new message command, whatever we have from the server to this. So this is a command sent, and the commands received is from server to the client. Okay, so this now upon this receipt, the client will send an acknowledge message to the server to indicate that they received the message. And the chat server, now what we can do periodically, get rid of entries in that inbox table, so that it will lighten our storage. I know this is something vaguely discussion, but at high level this is what it's going to be. And that's the case of connected things. If users are not connected, we'll try to look up the user's inbox and find any undelivered messages IDs, and then for each message ID that we have, we will look up the messages table and write those messages to client's connection via that new message command that we have. And then again we'll send via this new message to the client, and then this will acknowledge the same to the server, and then delete those conversations. So this way we are guaranteeing offline delivery to the users, and make sure that even when they're not online, we store the messages in our tables and deliver them. So yeah, I think maybe there might be confusion, but just the intuition is to give an idea and take it from there. Okay, so this is how we will try to achieve if offline delivery is guaranteed or not. Okay, fine. Now the other thing is they should be able to receive or send or receive media in their messages. I think this is something should be quick discussion. So there are again some approaches here. What we can do is directly keep attachments in DB. So here this approach is the worst one, because we are planning to send attachment media over a WebSocket connection and save it in our DB. So this is not good solution, because databases aren't optimized to store the connection medias directly, and also the bandwidth towards chat servers will be occupied with this media, and it's something very dumb storage and retrieval. So something this is not preferred. That's why it's a straight a big no. So this is something, it might look something directly through chat server and store it in database. Okay, fine. So now as an alternative for that is we can send a chat attachments via chat server. So here what we'll do, we will try to send the attachments to the chat server, and then this chat server will write media to our some blob storage, whatever it is, and then this is basically we're trying to go through the chat server. That's something we want to store it in blob storage, and if users wants to retrieve, he can directly query the blob storage via the pre-signed URL for the authorization and all that stuff. And so still here again our chat servers needs to handle the incoming media and then forward it to the blob storage. It's something that wasted step, and I really don't want to put a load on chat server. So this is again we don't want to choose here, and the ideal ultimate thing is just to manage attachments separately all in all. So that's the simple thing. So here what we are going to do, we will give users permission. So basically example via the pre-signed URLs to upload directly to blob storage, and then that once we get the URL, we send this get attachment target. Once we get this URL, and then we send that URL through chat server, store it in our database. And if we wanted to send that attachment to the user, so then we might send a get attachment target message to chat server, which will get the pre-send URL from this database and return to this user, and then we can accordingly showcase it to the other user. So this is really good solution, because it just offloads the load onto our chat server and completely delegating it to a blob storage. So this is something we will try to choose for storing the blob, the media and all that stuff, and this way it's taken care of. Yeah, this is how we'll try to achieve this minimal functional requirements. I know there is a lot of confusion in the design and all, but this is how it's going to be. And now let's go to the GDrive sections, and then see we have here first point is how do we handle a billion plus users with high throughput. So here we have till now we were all discussing about single host and it's convenient and all, but it's not realistic. If you want to handle billions of users by a single machine, it is really not possible, and it would something, let's say we, even if we have 1 billion users, we always expect at least 200 million plus users be connected at any point of time. So we need to serve all of those things, users. So how are we going to do? The problem here is adding more chat servers. We can just say put a load balancer and add a more chat servers and all, but that's going to introduce a lot of problems here. Let's see here the simple problem. So user A, user B, and user C, assume we have this many users, and we have currently in a chat server 1, chat server 2. So if a user A wants to send a message to user B and user C, user A is connected to server 1 and user B is also connected to server 1. So we send a message to chat server 1, and since user B is connected, and we will it be WebSocket connection, and we will emit the event to this user B, and he will receive that message is delivered to B. But user C can't see that message because it's not connected to server 1. So how is it? This routing is something that we need to make sure, no matter whatever the server that user is connected to, we should make sure there's messages are sent. So let's see the approaches here. So first is natively horizontally scale it. So here what we're thinking is just to put a load balancer in front of a chat servers and scale horizontally. This really won't work because a given server might accept a message to be sent to a chat, but we are no longer guaranteeing it will have the connections to each of the clients. So which again, the point that we have here, guaranteed delivery, that's also one point, non-functional requirement. So if we choose this, we will not meet this. So that's why we will not choose and not go ahead with this. And the other approach is we can keep a Kafka topic for each user. So here what we'll do, whenever user tries to connect to a chat server, they would subscribe to topic for that for their specific user ID. So when we need to send a message to a given user, we would publish that message to that topic for that user, and this message would be received by all the chat servers that have subscribed to that topic, basically for that user ID. Then message could be passed on to WebSocket connection for that user. So something that we can try to choose this, but this again, this is something that really doesn't work because Kafka is really not built for billions of topics which really carry significant overhead, and there are we cannot go on and create each topic for each of the users. So that is something that's why we don't want to prefer to this one. And let's see, the other thing is consistent hashing of chat server. So here what we do is basically we will design in such a way that users to specific chat so users always assign themselves to specific chat server based on their user ID. So if we try to do this hashing consistently and better way, so we always know that which chat server is responsible for a given user. So when we need to send them messages, we can do so directly. So to do this, what we need to do, we need to keep a centralized chat registry of like how many so here chat registry, like we need to keep a mapping of how many chat servers we have, their addresses, and then which segments of consistent hash space they own. So here again we need to rely on something like etcd or zookeeper to do this. So when a request comes in, we will connect them to the chat servers they are assigned by looking up through this the address and to the specific the chat server. And when new event is created, let's say if some new event is created, the chat servers whatever we have will directly connect to that respective user's chat server through this etcd lookup, so using the chat registry, and then it will send directly to that chat server, and then that will send the command to the client so that he'll also receive the message. So something it might look as this, looking up the addresses here and etcd coordinating the mapping, storage, and all those things, and we will look up these things and send directly to that respective user chat server, and then that communicates to the client. So here the challenge is, here we need to maintain again connections with each other. Chat server will require the lookups using this etcd and chat registry, and also and we need to even think of scaling and downscaling, upscaling and downscaling. So basically careful orchestration of dropping connections so that users reconnected to other servers without triggering confusions among the other chat servers. So these are the problems that it really comes up and we need to take care. So this is something we can also skip this method. The ultimate method is going to just offload everything to PubSub. So here it's something like we'll try to bounce messages between servers. So here we'll try to use Redis PubSub. Simple good examples here is we will try to create a subscription for a given user ID and then publish messages to that subscription, which are received at most once by the subscriber. So here on connection, what we'll do, when a user connect to our this chat server that we have, the server will connect to this PubSub to subscribe to the topic for that user, that specific user. So any messages received on this subscription, so basically on this, are then forwarded to the WebSocket connection for that user ID and then to the chat server, and then that user will receive. And when message needs to be sent, then we publish the message to this PubSub for that relevant specific user ID. The message is received by all the subscribers. The chat servers then forward that message to the user's WebSocket connection and all. So this way we can heavily offload everything to PubSub, and we just subscribe to that things, and whenever we wanted to just listen to that specific user ID, we will be subscribed anyhow, and then we'll chat server will pick it up and then showcase it to the user. So only thing is here every there should be all-to-all relationship between chat servers and Redis cluster servers. So that's something, but this is a great solution for us to handle this higher number of users that we have, and this is the approach that we'll stick to. And let's discuss the second point. How do we handle multiple clients for a given user? I think I'll try to keep it short. So here now we assume now user has a single device, and but many, again, ideally they'll have multiple devices. So how do we handle multiple clients or devices? It's something we need to think through. So what we'll do now, we'll try to introduce a new clients table. So here we'll have a clients table here, which might have, let's say, ID and user ID to keep track of clients by user ID. So when we try to look up the participants for a chat, we will need to look up all the clients for that user. So here the chat ID and the participant ID, so we will need to even update our inbox, not now to the recipient ID, but it's going to be recipient client ID. So it should be now per client rather than per user. So then when we send a message, we need to send a message to all of the clients for that user. So anyhow we'll be looking through this recipient client ID, so we'll get all list of the client IDs for that user, and then we, using the commands, we need to now send it to all of the clients for that user. So on the PubSub side, it is just going to remain the same because chat servers will continue to subscribe to that topics of user ID and all. So here maybe we can add a limits on like 3 clients per user or so on, so that we can avoid blowing up our storage and throughput and all that stuff. So ideally, though the discussion was vague and not very much in detail, but this is how it's going to look like. Just having a helpful load balancer in the chat servers, Redis PubSub to handle a high number of users and throughput, and then separate tables like clients and the others in inbox, message for offline guaranteed delivery and all those things. So this way, at least I hope I might not have conveyed a lot of informative info for this use case, but I think it gives you decent idea of how to think through, I guess. Yeah. All right. Yeah. All right. Now let's discuss about Help. So Help is basically a simple online platform that allows users to search for and review local businesses, restaurants, any other services. So it can be any category. So that's what at a high level Help does. And now let's see the basic functional and non-functional requirements, and then we will see how we can break them down and discuss in designing a system. So the requirements, the functional first thing. So here user should be able to search for local, so basically you should be able to search for businesses by name, location, or category and all that stuff. So that's the basic this thing. So you should be able to search for those businesses name by name, using name, location, latitude and longitude, and category, whatever it can be. And then the second requirement is you should be able to view businesses and their review. So basically view a list of businesses, the business details and the reviews on that specific business and all that stuff. And the third requirement is you should be able to leave a review on that specific business. So those are the three core requirements that we should try to meet when we are designing the system for this use case. So coming down to the non-functional thing, so the search operation, whenever they're trying to look for specific business search, the results for them should be within the bounds of like less than 500 milliseconds. So it should be very fast. And then the availability is given higher priority than consistency. It's okay if we are not able to showcase the review immediately or left on the business, but something it should not be lost or something on those lines. So it should make sure that our system is also always up and give better experience. And then coming down to load of our system, we should at ease handle 100 million daily active users and at least 10 million businesses on our platform. So these are the numbers. At least when we are designing a system, we should keep in our as it as an upper bound and then try to design a system. All right, now we are clear on this functional and not functional. So looking at this, I think the basic entities also should be clear for us. So that's the second point. So the basic entities that we have here is the business. So basically the service, whatever is listed on our platform, it might include details like name, location, category, average rating, and all that stuff. We'll discuss what and all schema fields will be there exactly as we go into our high level discussion. The other is the user, so just the user who can search for businesses and leave reviews on our platform. The review, again, that entity is something which includes a rating, optional text, and all that stuff for a specific business. So these are the like core entities at least we need for us while we are trying to design for this requirements. Now we are clear on this entities. Let's discuss on APIs or system interface that we need to provide to our clients. So first is the endpoint to search for businesses. It can be as simple as the get endpoint. So maybe some businesses and query params here, some searching by name, description or location or another category, whatever it is. And here we have location, category, and the pagination, because we might have a large data set. So it's always good to do a pagination to give a limited amount of data once at a time. So this might return the list of the business list. So this is one simple endpoint searching for businesses, so that their homepage will be populated with the list of businesses. The other thing is, once they see business details, they click on that specific business and they should be able to view the details of that specific business. So it can be either maybe single endpoint like business ID provided, we give business as well as review details, and so that business page gets populated with the basic info and then the reviews of it. Or we can separate it in these two ways, just one endpoint providing the business and the other endpoint providing the reviews for that business with the pagination logic and all, so that it gives it is properly isolated to each other. So we can design in this way or else this way. It's up to us, whichever it's easier for us to implement. That's something that we can prefer. So that is the second endpoint, just to view business details. The other endpoint is, so now we need to provide an endpoint for user to create a review on specific business. So that's going to be simple post endpoint. So with the business ID, the reviews endpoint, so you can leave ratings. Maybe it can be on the scale of 1 to 5 or 1 to 10 depending upon the stars that we wanted to showcase. Ideally it is going to be on the scale 1 to 5. And the text, if you wanted to leave any comment or text on that thing, this is the field that you can just fill it here. So these are like, core endpoints that we need. So now let's take one point at a time from functional requirements and see how we are going to go from all the way from simple system to handling the numbers that we have seen in the requirements. So the first high level discussion point is you should be able to search for businesses by name, location and category. So it's going to be simple, the same the client, and we have the API gateway which will most cases handles auth related things, rate limiting, routing and all that stuff. And we have here business service. Assume that user, the client will trying to hit with the endpoint like businesses, query params and other things which are optional, and it hits our business service, and this tries to query our database. So here business entity can have something like ID, name, description, location, address, category and all those details and all. So these are like core critical components. So client sends a GET request through API gateway to business service, and this queries the database for you on this business table. The results are returned to the client via this API gateway. So that's the simple the realization of the first point. Should be able to search for businesses by those name, location and category. So let's move on to the second point, which is you should be able to view businesses and their reviews. So this also it's going to be pretty much straightforward. Same client, API gateway and same service, business service. The difference is only the endpoint is going to be get businesses passing in the business ID, and again we'll try to query the database of a business table and then reviews table, and reviews table can have a user ID, business ID for which business ID has given a review, and the rating number, and then the text of it. So we'll just do maybe joins between these tables and give the written results to this client of business along with the review details for that business. So here we are trying to keep it in the same service because the pattern here is both are read heavy, and we wanted to keep it in the same service unless the pattern is very different and something only then we can think of writing a separate service for that. So that's the one main reason keeping it in the same service. So now let's go to this the other point. We should be able to leave reviews on businesses. So this now we will try to separate service into review service. So here the endpoint is going to be post endpoint, businesses passing a business ID and reviews. So why we separated into here the separate services, because the read write ratio, if you see clearly observe, the read is always going to be something like on the scale of like 1000:1. So it's we know that traffic for this service is going to be high, and this for this it's going to be less. So I don't want to have it in the same read heavy services. So that's why we decide having separate service. So it can be simple as review service, and then here we'll just add an entry into this reviews table that we have. So it should be simple. This review services core responsibility is to handle creation and management of reviews, and then because usage pattern is significantly different, like I said, reading and writing ratios. So that's why it's fair to separate in this way depending upon our reasonings, whatever we have. And once the review is created and the confirmation is sent back through API gateway to the client that the review has been created. So we can also maybe discuss here why not have separate database for review service and all. I think given the numbers that we have here, we always should try to aim to have a simple design at meeting all our requirements. Since our numbers are quite smaller, meaning here we have 10 million businesses, assume like each business might get 100 reviews each. So how much? 10 million businesses multiplied by 100 reviews each, it sums up ideally to 1 TB, which is modern databases can handle in a single instance. That's why like we stick to tables in a single database rather than complicating our design. So again, it's up to our own choice. If you wanted to have separate database, we can have, but it's all again falls back to operational overhead and other the trade-offs that we wanted to make depending upon the business requirements. So this is the main reason. So I think the 4 simple functional requirements are met using this simple design whatever we have discussed. Now let's dive deeper and see potentially discuss deep diving of critical points that we need to address in our non-functional requirements. So first thing here is how do we efficiently calculate and update the average rating for businesses whenever users search for that specific businesses. So ultimately, let's say whenever user is trying to look for some businesses, the thing that is going to look for is the rating of that specific business. So it will be very inefficient if you try to do the average rating calculation on every search. It's like repetitive calculating of the rating for the same search query n number of times, which is something not efficient. So yeah, naive approach is, this is what we do ideally now. We try to do join between the business table and reviews table by this thing, and every time we try to query and then calculate the average rating. So this is very naive approach, and this is very inefficient. So that is something that we wanted to avoid. Every time we don't want to strain our database. So because as the number of reviews and businesses grow, the query is going to be immensely slow and it's going to affect the user performance. So this is something that we don't want to prefer. So what is the alternative then? So other alternative is we can have some periodic cron job, which can be running for every couple of hours or of a day or night or whatever it is. So what this does is this periodically updates average. We'll introduce now average rating column in our business table, and periodically it queries this database business table and calculates the average and tries to populate into our business table. So this is ideal, but again here what is it that we are facing the challenge is these reviews again are not real-time changes. So businesses people might again feel the reviews are not updating immediately, and it is something that users will not agree or accept for this kind of use case. So that's why this cron job of introducing this delay of whenever we are running this cron job for immediate reflection is something it's not supporting. So this is why we don't want to go with this periodic update with cron job. So what is the other approach then? So we can go with synchronous update with optimistic locking. So this is something like the question is we need to do both that, adding new review to the review table and also updating the average rating for business in the business table at the same time. So here we have now the average rating and the number of ratings. So this is something, the new rating can be something calculated in this way, like old rating, whatever the average rating that we have here, and multiplied by this number of reviews plus new rating whatever the user has given, and divide by this number of reviews plus 1. So this way we will try to calculate this new average rating. So this just a few CPU cycles, so it can be done synchronously for each new review. So here again the problem here, what if two users tries to do the review at the same time, so there is a chance that we might end up not considering specific users 1 or users 2's review. So let's take an example. Let's say business has 100 reviews with average rating, let's say 4 rating, and now user 1 reads the number of reviews as let's say 100, and average rating is 4. So user 2 also reads the same number of ratings as 100, number of ratings as 100, and the average rating is 4. Now user 1 submits 5 star. So what is going to be? Average rating was before 4 and multiplied by this 100 plus 5, and here 100 plus 1, 101. So it approximately it became 4.01. Same time user 2 also submitted a 3-star review. So now this is going to be 4 multiplied by 100 plus 3 divided by 101. So this sums up to 3.99. So user say updated completes view with the number of reviews to 101 and the rating as 4.01, and users 2's average rating to 3.99. So the final state here, it will be now whatever user 2 has done, which is 3.99, and it is incorrect because it actually doesn't take users 1's rating into consideration. Ideally it should be 4 because you both has submitted, and it should balance and it should be ultimately back to 4. So to solve this issue of two users trying to do the updating of the rating at the same time, we can use this optimistic locking, whatever it is. So here, what is this optimistic technique is basically, we first read the current state of our business. So basically here the state can be here number of ratings, and then attempt to update it. So if while we are trying to do this, if the state has changed since we read it, our update will fail and should fail. So we'll often had a here, that's the something called version number. In our case, it is going to be number of ratings. So that is the something that we wanted to lock on, and we check if the number of ratings have changed or not, and if it is changed, we will just not update, meaning the update will fail, and if it is not changed, we will update. So that's how we take care that no matter what, the concurrency is taken care with optimistic locking. So that's the simple check in our just the update in our SQL query, whatever we will be trying to do in a transaction. Yeah, so yep, that's the simple discussion. So here again, we can also think of like why not push it to message queue and then have some consumer pick up that, calculate the average rating and update your business table. That also can be handled, but it's again more of an operational complexity. And even if you see here, given the numbers that we have, the traffic here, we have hardly, let's say it reads to write 1000 to 1, and with 100 million users, we hardly have how many writes per day. It's something 100k writes per day and 1 writes per second. This database easily is going to handle that 1 writes per second. It can easily handle in the magnitude of 5k to 10k with decent hardware is what I'm talking. It can go up to 25k or 50k writes per second. So that's something easily we can handle with this, and that so this average rating calculation is something we can do or calculate in that way. That's how we are going to address this point. So let's talk about the second point now. Now we need to enforce a constraint like user can only leave one review per business. So why this is important? There might be some competitors that they wanted to of course want to give lesser review for its competitor, 1 star, and obviously bring its rating down, and people preference is going to change as well. So how can we ensure that we can user can only leave one review per business? So a couple of approaches here. Simple application level check. So what we do here, I'll do just some let's say in my application layer, service layer, I'll just do check try to get reviews for that specific business ID, and then check if that user ID is present in that list of the reviews for business or not. If it is so, I'll just not proceed with the writing to reviews table. If not, I'll proceed it to that. So it's something I'm trying to do, enforce the check in my application layer. So this is something, it's not ideal in this case or not preferred. Let's assume there are multiple teams trying to update our table. So maybe some data engineers or whatever, they wanted to update the reviews. So they will not be aware of this application level check, the logic that we have. They will be solely using just the database. So it's something, if something there is a data constraint, we should always tilt back towards closer to persistence layer, see if we can add a strict data constraints there. If not, only then look in the direction of application level. So that's what exactly we are trying to do here. Here we are trying to do here the add a database constraint. All we have to do is basically on table reviews, we need to add a strict constraints here, unique user business constraint on user ID and business ID. So this at any cost, make sure that even if you're trying to insert multiple reviews for specific user, it will not allow the entry, because we have a strict unique constraint per combination of user ID and business ID. It should be one review for that user. So this way we make sure that a user can leave only one review per business. Yep. And now let's talk about the other requirement. The search operation should be with as much as less latency, and in our case here it's ideally 500 milliseconds. So currently whenever we try to search, ultimately how we will do ideally is just do simple query, select star from businesses, and here in our case it's a search by latitude and longitude, and it can be naming wildcard search or description and all, something like this. This query is ideally very slow because even if we had indexes on latitude and longitude, the B trees indexes, they are ultimately good for single dimensional fields, not for multi-dimensional fields here in a case longitude and latitude. So and also the number of rows and the reviews are going to go very high in number, and this query needs to do full table scan and all that stuff, which is going to significantly slow the results to the users and lot of buffering for them. It's not going to improve the experience, and results are not met in the 500 milliseconds latency. So let's see the approaches again. Like I said, basic indexing, it doesn't work out. Like I said, the btrace indexes ideally doesn't work on multi-dimensional in the fields. So here the other approach is we can choose the Elasticsearch. So the Elasticsearch is basically now if you see carefully observe, we need three types of indexes. One for location, so kind of like geospatial index I might need, something like geohashes, quad trees or R trees, and we need a full text search on fields like name or descriptions. So that might use that we need something technical called inverted indexes to quickly search for terms in a document. Then other we need for category, so we need something like simple b-tree index to search by category. So those three indexes are something, or there are many that are supported out of the box by Elasticsearch. So it's ideal to choose Elasticsearch. So we can now search by name and search by this geospatial things, and also search by category. So everything we have whatever we need, and that's why this is an ideal solution to go with to use Elasticsearch for our searching things. So after considering this, it might look as simple as this. So Elasticsearch here, and we have geospatial index for location, inverted index for full text search, index and category. And here to sync our data, whatever the entries that we have inside our database, we can periodically do CDC logical replication, or then introduce a queue, and then from queue we can try to push it to our Elasticsearch via our worker or consumer, so that the eventual consistency is data will be getting pushed to our Elasticsearch. So this way we can ensure that our search latency is met, and also we have taken care of all types of different indexes. Even now if we don't want to introduce additional Elasticsearch infra or something external dependencies that we wanted to rely on, there is still the other approach that we can go ahead with. So that is with Postgres extensions. So we need the geospatial the indexes. So we have an extension called Postgres, which exactly provides us that, and we need full text search on name or descriptions. So pgtrgm is something that really helps us with. So now it's like we are trying to keep ourselves within the same Postgres ecosystem, so no additional infra or dependencies that we wanted to introduce any components into our system. So it's going to be as simple as this, and this really makes our the development way faster and be efficient, and it's going to be something simple and yet effective to meet our latency of whatever we have. So this also can be taken as a one of the choices things. So there might be scenarios that they don't want to straight away prefer Elasticsearch, and that's the one thing that we can talk about. And also you can just check different types of indexes, like geohashing, quad trees, R trees, and which is preferred. Something like quad trees, because here updates are very infrequent, and businesses are clustered into very densely populated areas. And so, and also, like, how do we do the distance calculations here? So we should need to calculate the distance between users' latitude and longitude and the business's latitude and longitude. So there is something like we need to calculate distance using Havelsin formula, which is like a Pythagoras theorem, but really optimized for calculating distances on a sphere, which is Earth is like a sphere like object. So that's something kind of like we more of a questions or discussions that we can go ourselves into and see which one to go ahead with. Is it Elasticsearch or our own this, and then go into intricacies of the details which I just talked about. Yeah, this is how we'll try to improve our latency. And the other point is let's discuss now. So the allow searching by predefined location names, like such as cities or neighborhoods. So this is basically currently what we are doing. Our design currently supports searching based on businesses latitude or longitude, But however, mostly users never will try to search in more natural language terms, like for example, let's say pizza in Bay Area or some other things like that. So there now whatever user is just searching, they're not just zip codes, states or cities. So it's something like exact neighborhoods, and then specific points in a location. So here with this search, it's a straightforward that simple radius from a central point or center point is not going to do the work for us. So because city or neighborhoods are not perfectly circular and can have widely different shapes, so it's something that we need a way to define something called polygon, so for each location. So here polygon is nothing but it's going to be a list of points, and it can come from variety of sources. So here, to achieve this searching by predefined location names such as cities and neighborhoods, we need to achieve two things. One is going from location name to polygon. So polygon something the example, the list of points, like I said, can be GeoJSON. Here type, feature, geometry, and then we can store properties here. So we need to try to maybe let's see how can we achieve this. And the other thing is, once we have that polygon, then we need to filter set of businesses that exist within that polygon range. So let's see how we can see. First thing is, to achieve first point, what we can do is we can just try to create a simple locations table with a name, let's say like Bay Area or Bangalore, whatever it is. And type can be, is it a city, neighborhood, and all that stuff. We can just specify various types here. And here the points, list of points sourced publicly. Example, there's a geo AP5 which will give us all the polygon points which I just specified for a specific area and all that stuff. So, and we need to populate this points with that specific details. There's a something we'll easily get public data based on those areas and the type that we have mentioned. So once we have populated here all of our sources that we really wanted to maintain in our locations table, then we can just use that polygon to filter the business that exist within it. So to do that filtering, it's something that we this Postgres or Elasticsearch, whatever we have decided to go with, they really help us to support this using geo shapes or geo points. So here we can simply add geoshape field to our business documents in our Elasticsearch if you have chosen that, and then the query can be something like for using this bounding box. So geo bounding box, location top left and bottom right. So this is something like this we can search. And also here doing this bounding box search for every request is also not efficient. So to still make it way efficient, we can pre-compute the areas for each business, like whenever we're trying to create or add an admin is trying to add a business or something like that into a platform. What we can do, we can try to pre-compute the areas for each business and then store as a list of location identifiers in our business table. Something like maybe in our Elasticsearch it might look something like this. Let's say business name is startup and location names can be Bay Area, Silicon Valley, SF and all that stuff, and category is something like technology is something I can create here. Okay, so yeah, so this is something like this. If you pre-compute and store it in an Elasticsearch, and now it will become way easier even whenever user searches by pre-defined names or neighborhoods, and then we try to give them good list of results that they will be satisfied with. So this is something we can think through as well when we are trying to discuss of this design. So ultimately the design of our this final design is something it's going to look like this. So client and API gateway, and then we have business service and we have review service, and the database and CDC we'll try to populate this Elasticsearch. And then yeah, we have business entities, reviews entities, and location entities, and multiple indexes on our Elasticsearch. So this sums up our discussion on help. Hope at least we covered some good decent points, and hope this might have helped you